डॉक्टर वैदेश्वरन, अनम्यूट है अपना, अनम्यूट करो।
I'm starting. Welcome to the technical session 5. This session has 2 invited talks followed by 3 oral presentations, 12 to 40. The first invited talk is by Professor Ravi S. Kumar. He is Research Professor, Department of Physics, University of Illinois at Chicago. His area of expertise is high pressure physics, energy materials, and synchrotron experimental techniques. The second invited speaker in this session is Dr. Leonid Dubrinsky. He is from Bayreuth University, Germany. He has expertise in structural studies at high extreme conditions and material synthesis at high pressure and temperature, and high pressure mineral physics. He is recipient of many awards, including Medal of European Mineralogy Union, Dr. Honoris Causa, Linkopin University, Sweden, and Gregory Aminov Prize in Crystallography. This session will be chaired by Professor G. Vedisharan. We have listened to his talk in the last session. So without much delay, I invite Professor G. Vedisharan to chair this session. Professor Vedisharan.
Yeah, thank you.
Over to you, sir.
Yeah, thank you very much, madam. So, madam, is there a timing which you have there, or I should fix the timer?
Sir, we will also do, it is 25 plus 5 minutes.
Yeah, 25 plus 5 minutes. Okay. So, already Professor Ravi Kumar is here. So, Ravi Kumar, you can start sharing your slides. Yeah, can you allow him to share?
Yes,
You are muted. Unmute yourself, Ravi Kumar.
Okay.
Yeah.
Let me share my.
So it is 25 plus 5 minutes, na, madam?
Yes, sir.
Okay. So 22, I will inform you, Ravi Kumar.
In a minute, let me. Yeah, let me share my screen because
yes.
I have some issues. Are you able to see the screen?
Yes, Ravi, yes.
Okay. I'd like to thank the organizers and the session chair for this opportunity. In this talk today, I'll be presenting the experimental results and observations on the effect of pressure on various correlated materials using X-ray spectroscopic techniques. Understanding the behavior of strongly correlated materials such as cuprates, heavy fermion materials, and iron-based superconductors remains one of the major challenges in condensed matter physics. These materials are promising systems for obtaining high temperature superconductivity, and by considering the quantum critical point where the ground state of the material becomes unstable due to strong quantum fluctuations, complex properties and exchange interactions can be visualized. However, the theoretical problem of quantum criticality is very difficult, and many fundamental questions remain unanswered despite years of intense efforts and impressive progress on the topic. The interactions between electrons are by means of spin, charge, lattice, or orbital order. The competition between different phases and interactions induces a great variety of magnetic phenomena, ground states, and phase transitions. They exhibit exotic electronic magnetic properties that cannot be sufficiently accounted by the non-interacting properties of individual constituents. The simple picture of a non-interacting electron gas no longer applies here. The strong Coulomb interaction is non-negligible. High pressure in combination with magnetic field or temperature can be used as a clean tuning parameter with which one would change the electronic properties. In this talk,
Kumar, your slides are not moving.
Yeah. In this talk, I'll provide
Okay.
a few examples, and the outline of my presentation provides a general overview of the different materials using various high pressure techniques using X-ray spectroscopic methods. I will present few specific examples taking ion-based systems and ytterbium Fe2Ge2 as a model example system. A combination of X-ray spectroscopic techniques that could provide more insight into the properties of these materials. I'll then show the effect of pressure on the valence state of cerium at low temperatures around 10 Kelvin in cerium to nickel 3 germanium 5, and further provide evidence for a structural phase transition observed through low temperature high pressure X-ray diffraction. Besides the well-studied cerium copper to silicon 2 heavy fermion system, we now show here the critical valence fluctuations occurring in this compound around the pressure-induced superconducting dome for the first time. I'll then present our recent results on zinc PbAs2, a topological material under high pressure, which shows pressure-induced superconducting transition along with pressure-induced structural transition. I would like to acknowledge the contributions from all our collaborators in different projects. The single crystals and polycrystalline samples for the experiments were grown in different labs. For understanding the high-pressure experimental results, we collaborate with theoretical experts. They use DFT methods, self-interaction corrected local spin density calculations, VASP, structure search algorithms for explaining our experimental observations. I would like to acknowledge the support from CDAC, NNSA, and Russell Hamley. And also I would like to thank HPCAT, GC course members and funding support from NNSA and DOE. Correlated materials discovery is continuously evolving right from heavy fermions, high TC materials, transition metal oxides such as some manganites, cobaltates, iron-based materials, etc., including the recent topological systems. Various degrees of freedom of strongly correlated electrons in solids which respond to external stimuli are shown in the second cartoon. These strong couplings lead to the emergent functions with the cross correlations among the different physical observables and to developments towards the application of emergent functions such as motronics, magnetoelectrics, topological electronics, and quantum computing, etc. The contemporary avenues in the quantum materials include topology, strong correlation, and dimensionality, which are the gateway for obtaining properties on demand. Potential applications include high temperature superconductors, graphene, topological insulators, rail semimetals, etc. Understanding how the different orders state in connection with superconducting pneumatic and magnetic properties in different superconducting materials is still remain challenging. Key issues remain unsolved, such as the origin of pneumaticity in Fe chalcogenides and the role of the magnetism in pnictides. Moreover, it is still unclear whether quantum criticality, which is a common phenomenon observed in heavy fermion materials, is a central ingredient of iron-based superconductors. Topological insulators are also new materials which can be classified into two bigger classes. Insulators and semimetals are based upon band crossings in electronic band structure based on the signature of topological materials. Some examples are also shown here. Advances in theoretical and experimental techniques offer the possibilities to gain the better understanding of the effects of high pressure on the materials and thereby observation of exotic properties. So pressure has proven to be an effective and clean means of tuning the lattice and electric freedom in these materials. And for the past several years, we have looked on various materials that we have investigated so far, and they all show very interesting properties, such as pressure-induced valence changes, low-spin, high-spin transitions, pressure-induced amorphization, new high-pressure phases, re-entrant valence behavior, suppression of magnetic order, phonon density of states, and vibrational properties. The mechanisms shown in this figure are interconnected, and pressure can change the hybridization among them. So by tuning all these interactions, we have a better insight of the properties of these materials. So collectively, a range of techniques shown here can be used to understand these problems, from the search for new materials that challenge or extend the current understanding to advanced measurements that reveal in detail the behavior of electrons and excitations in these systems. These techniques provide opportunity to test theoretical methods that seek to explain current observations and suggest new directions. In more detail, besides the conventional elastic quasi-elastic scattering methods, in elastic X-ray scattering measures the dynamic structure factor, which is a function of momentum transfer and energy transfer. The dynamic structure factor contains information of all electronic excitations, including phonons, magnons, core electron excitations, plasmons, the collective fluctuations of valence electrons. So with proper instrumentation, high pressure techniques can be coupled with synchrotron to be effectively probe the material properties. So when we look on the phase diagrams of each class of material and compare the emergence of superconductivity, the first one is the Doniak phase diagram for the correlated systems. When both localized itinerant electrons exist in the system, yet another mechanism of exchange interaction mediated by conduction electron appears. If the bandwidth of the conduction band and the corresponding Fermi energy are large, this mechanism is known as the RKKY exchange. This can be expressed as a function of exchange and density of states. The interaction between F electrons and conduction electrons has two consequences. A magnetic state due to the screening of F electron local movements by conduction electrons, also known as Konde effect, or a long-range magnetic ordering due to RKKY interaction. Most of the cerium-based systems fall in the category of any one of the PT phase diagrams shown below. Most of these materials, cerium, indium-3, cerium, palladium, silicon-2, are all fall in this category. The second system is a PT phase diagram of an iron arsenide system. The iron-based superconductors provide a great opportunity to identify the important ingredients that are common to both families of high TC materials and to test the theoretical models that have been formulated for cuprates. The last example is the phase diagram of a topological material, and the superconductivity appears once the topological insulating state is suppressed under pressure. The phase diagram of the heavy fermion systems and the pnictides and the topological materials all are similar in some aspect. If we compare all these materials, we could see a common overlap. The application of pressure modifies any of the competing mechanisms, such as magnetic orderings, spin density wave, charge density wave, crystal structure, valence state, etc. So as we discussed before, the application of high pressure X-ray spectroscopic methods could shed light on most of the competing interactions. I'll explain some of these synchrotron techniques that can be effectively combined with conventional diffraction to get better understanding of these various properties. So I have shown here the high pressure X-ray spectroscopic experimental setups to APS, more specifically at HPCAT in sector 3 and 4, nuclear resonant inelastic X-ray scattering, which probes the partial phonon density of states for selected elements. nuclear forward scattering, which gives information about magnetic ordering, local symmetry, and valence materials. Resonant inelastic X-ray scattering, which gives the information of spin and valence. X-ray Raman scattering, which gives the bonding information. X-ray magnetic circular dichroism, which is element specific and orbital specific information, and also electric dipole in transition, etc. At a resonant incident X-ray energy, the atom absorbs a photon exciting an electron from tightly bound core state to an unoccupied state. And this is called resonant inelastic X-ray scattering excitation. And the valence of the materials such as ytterbium and cerium can be calculated using the simple formula. And the spectral collections can be had from two different methods, which is a partial fluorescence yield mode, which is very similar to the conventional X-ray absorption spectroscopic technique, and rates 2D mapping where the incident energy and the analyzed angle is varied so that the energy difference is plotted as a function of incident energy. So when we talk about the ion-based superconductors, there are four classes, 11122 system, 111 system, and 1111 system, which are all basically based on the chemical composition of the material. So since the discovery, the underlying mechanisms are very unique and different. And there are a lot of competing mechanisms undergoing in these systems. We started with understanding the system of FESC, which offers a unique possibility to study the interplay of superconductivity with the purely pneumatic as well as magnetic pneumatic ordering by pressure tuning. So we synthesized this system, and the TC is most likely connected to the formation of FESC layers and the antiferromagnetic stations. And we performed two kinds of experiments. Among these materials, the structurally simplest FESC derived materials have attracted enormous interest because they show the unique properties such as the bulk FESC single crystal. It shows a relatively low TC, and when we apply pressure, the TC goes up to 20 Kelvin at 1 GPa, and then achieve highest TC around 36 Kelvin. We did the low temperature, high pressure X-ray diffraction on this material up to 30 GPa at 8 Kelvin, and you can visualize pressure-induced structural phase transition around 2.3 GPa from the tetragonal to orthorhombic transition. In addition to this, to understand the phonon density of states, we have performed the Hendrix measurements. The experimental data, the results are shown here. The measured and calculated phonon density of states at high pressures for FESC shows four prominent regions: the transverse acoustic modes below 10 millieV, and longitudinal acoustic modes labeled around 15 millieV, and the B1G Raman mode around labeled as C, and the optical modes about 30 millieV in the 3 GPa spectrum. Upon increasing pressure, the intensity of these acoustic modes reduces rapidly due to anisotropic lattice compression inherent to the layered structure, and following the tetragonal to orthorhombic structural transition. So the synchrotron diffraction and also Hendrix techniques elucidate that there are the Fermi nesting that is happening around about 10 GPa for this material, in addition to the pressure-induced phase transition observed at the low temperature, high pressure conditions. In addition to these two properties, main competing mechanisms, there is another important spin ordering change observed in the system. X-ray emission spectroscopy is directly sensitive to the magnetic structure of transition metal, and it can probe the evolution of the spin state of the metal ion as a function of pressure. As the Fermi surface of FESC is dominated by Fe3D electrons and that have a strong hybridization with interacting SE orbitals, it is important to understand the Fe spin state. We have used X-ray emission spectroscopy, and the diamond in itself is which is an excellent technique to study the spin state of the elements under high pressure conditions. We have performed the DFT and the spin movement calculations as well. Our results show suppression of Fe spin state under high pressure near the TC. This has been verified by independent study besides our experiments, and more recently a re-entrant behavior where high spin state is also observed in some of the samples. Combining all our experimental and theoretical investigations on FESC, there are a lot of competing mechanisms such as pressure-induced structural transition, spin transition, Fermi surface nesting, and also magnetic ordering collapse and optimal anionic height parameter that affects the superconducting state. And the second system, what we have studied is the LAFEASO system, which reaches the maximum of 21 Kelvin under pressure, similar to optimal F-doped LAFEASO system. That shows a large positive pressure dependence of TC. And here we have performed a series of experiments, high pressure X-ray diffraction, and also the synchrotron mass bar spectroscopy, nuclear forward scattering measurements. And both of these experiments imply the crystal structure and the magnetic ordering becomes more vital in this material. Most importantly, at pressures where the superconductivity emerges in this system, we show a pressure-induced increase in the anionic height parameter, which is measured from the cation plane, in addition to continuous suppression of antiferromagnetic ordering, as shown in this SMS spectra. We can see that around 10, 11 GPa, the magnetic ordering is completely suppressed. This shows that this calculation shows that the Fermi surface of LAFEASO has 2 electron cylinders along the MA line in 4 corners and 2 hole cylinders around the gamma Z line at the center. And at 12 GPa, the hole-shaped Fermi surface exhibits a star-like topology. It has a 2D cylindrical character, but remains constant nesting factor between electron and hole Fermi surface sheets in the line zone. And this is a striking correlation between anionic height and the superconductivity of this material along with the magnetic ordering, which vanishes completely under pressure about 20 GPa. Moving on to the 122 system, which is one of the 122 classes which exhibits superconducting.
Kumar, you have 5 minutes.
5 minutes? Okay.
Yes.
Okay. Yeah. Okay. I'll show quickly a few examples of this one. And this shows a pressure-induced valence transition around the superconductivity in the system. And based on all these X-ray spectroscopic techniques, the valence fluctuations in the cerium-2 germanium-5, we have investigated at low temperature, high pressure conditions, which shows a superconducting transition temperature around 4 GPa. This is an orthorhombic system, and when we apply pressure in this system, we map the cerium valence as a function of pressure. You can see a critical valence fluctuation happening around 5 GPa where the superconductivity appears in this material. And the high pressure X-ray diffraction shows a pressure-induced structural transition from the tetragonal to the monoclinic phase, and theoretical calculations on SIC-LSD calculations of this material, which gives the critical valence fluctuations along with structural phase transition strongly support the critical valence fluctuation may play a dominant role around quantum critical point where superconductivity observed. The final example in the Wales semi-metal, zinc PbAs2. This is a chalcopyrite structure type of material. This is a topological system, and we have performed the resistivity measurements at high pressures up to 60 GPa. And we can see from the resistivity plots that it shows a pressure-induced superconducting transition around 24 GPa. And the X-ray diffraction in conjunction with the system, what we have shown here, clearly indicates a close correlation between the structure and the TC observed in the system around 24 GPa. You can see a clear transition from the ambient structure to a more simple structure, and around 45 GPa where the transition goes down, you can see another pressure-induced transition happening, and around 70 GPa more a different structure, which is different than that of 48 GPa. And when we decompose this material, it remains in a high pressure phase. So with these all examples, I would summarize my experimental observations and the results. Combined high pressure X-ray spectroscopic techniques provide important insights such as spin, valence, crystal structure, transport properties of unconventional, strongly correlated materials, such as iron-based superconductors, heavy fermions, and topological materials. We show critical valence fluctuations and transitions induced by pressure play an important role in the pressure-induced superconductivity observed in the cerium-2 nickel-3 germanium-5, and pressure-induced superconductivity is observed in the recently discovered the topological material zinc PbAs2. With this, I end my presentation, and thank you for listening, and I'm happy to answer if you have any questions. Thank you.
Yeah, so now we have time to take a couple of questions. Sorb. So can you unmute Sorb? He wanted to ask something.
Glad to see you, Dr. Ravi Kumar. This is Ashok Kamani from University. Okay. Now the point is there any connection between the quantum critical point lies in some cases dividing the superconducting dome and the Fermi liquid behavior, or anyway that you see the thing coming down, and then the QCP lies exactly in between. But in some of the most of the maybe uranium, germanium too, heavy fermion superconductor, it lies the QCP lies within the superconducting dome, right? I mean, maybe you may not remember everything, but is there any correlation between the quantum critical point, whether it can be shifted by applying pressure or by applying magnetic field?
Yeah, in some cases, it happens when we combine magnetic field and pressure tuning, and also even doping with different materials. It's possible, but the basic difference is like the 4F systems, the cerium systems, and the uranium systems are quite different in a few cases. So if you can see the phase diagrams, what I have shown earlier for the cerium systems, there are 4 different phase diagrams. You can see some of them, you have the superconducting dome, which is exactly having a single dome-like structure, and you have like a multiple dome-like structure, and the ytterbium systems and cerium systems and uranium systems are fall in any one of the categories, but maybe a little bit different when we consider the phase diagrams and also the quantum critical point. So basically, to answer your question, it is possible to tune this quantum critical point by doing some like external applying pressure, magnetic field, or doping conditions.
I have 2 more questions. One is you showed the Donash diagram. There are the competition between RKKY interaction and the Kondo, right? Now this particular diagram also is interesting. The correlation you are showing, that interesting in the sense that when the structure changes, you see that the correlation between let us talk about the Donash diagram, the exchange integral J greater than 1 or less than 1, the competition between RKKY and the Kondo, right? Now, is it something anyway related to the quantum critical point?
Yeah, of course, the quantum critical points lies in the, as you see in this Doniak phase diagram, the quantum critical point, of course, lies in between these two competing interactions, RKKY and the counter.
That's right.
So,
right.
yeah,
Right, okay.
yeah.
Well, the basic question is, in the whole doped superconductor, he wrote FESC. Is it not FESC 1 minus X? Because your FESC wrote it is for people to understand SC SC 1 minus X, right? It is not FESC is not a superconductor, if I remember right. FESC 1 minus X is a superconductor. Is that right?
So, yeah, FESC itself is a very low TC superconductor.
Okay.
Sir, we are running out of time, sir. Sir, we can discuss through email.
After
Yeah,
samarium,
Saurabh is waiting.
one last question. After samarium system, any other ITC system has been born in the iron-based superconductors after samarium?
No, not
Okay. Okay, thank you. Then the correlation that you showed us very good, extremely good, and maybe I'll see your paper. Okay, that will be. Or I will.
Saurabh, last question by Saurabh.
Thank you.
Yeah, thank you.
Thank you.
Yep. Saurabh, please unmute.
Okay, good.
Can you please unmute, sir? He's muted. Yeah, we cannot hear you, sir.
Sir, you have to unmute yourself.
You have to unmute. He's unmuted only, sir.
You are asking me?
No. Saurabh Yesudas.
Okay.
Can you put it in the chat box? Otherwise, we cannot hear you.
Okay, I have a quick question in the meanwhile.
Yes.
So, Professor Ravi Kumar, what is the pressure marker? It's a quick question. What is the pressure marker that you use these pressures, 60, 70 GPa?
We use two pressure markers. One is gold, and also we use ruby actually inside. So depending,
signal will be very low, I suppose, after 50, 60 GPa.
Yeah. Well, that's the reason why we use gold actually, internal pressure marker.
Gold, okay, you will have to do XRD. Okay. And what is the kind of error bars you get? I mean, you expect on your pressures?
Above 50 GPa, a couple of GPAs, error will be there always.
Okay, thank you.
Yeah, sir.
Sure.
Your question is still there, sir. We can't hear you. Maybe you can put it in chat box. I don't know, sir.
Yeah. Saurabh is somehow not able to unmute himself.
Yeah, connectivity is a problem. So then please send your questions through email, okay? Because we are running out of time and the next speaker is already there.
Now
okay, Ravi Kumar, please stop sharing your slide.
Okay.
We have to present a memento to the speaker. So on behalf of you,
Yes.
the chairman of this conference is presenting a memento to speaker, Professor Ravi Kumar.
Dr. Ravi Kumar, sir, we are pleased to present you the memento from the conference, sir. It will be
Thank you.
sent to you.
Thank you very much. Appreciate it. Thank you for the opportunity. Thank you.
Yeah. So the next speaker is already Professor Leonard Dobronsky is there. So Professor Leonard, please start sharing your slide.
Morning, I hope you see me.
Yes.
So, can I start already?
Yes, please.
Okay. Hello, everybody, and thank you, organizers, for the invitation and opportunity to speak about the most exciting for us topic, high-pressure crystallography. Today, I will present something which is kind of a progress report, what we are doing and what we achieved so far and what we hope to make in the near future. So, when we are talking about the in situ study materials at static pressures where only real device which we can use is diamond anvil cell. Diamond anvil cell introduced in the early 60s, late 90s, early 60s of last century. By 2010s, allow comfortably work at the pressures over 200 GPa. In fact, there are several groups which are work at the pressures as high as 400 GPa by 2010. But if you compare these values, let's say 200 GPa, with pressure which have been achieved in the single crystal X-ray diffraction, it was a very strange situation. It was hardly achieved 15 GPa. So were several reasons why it's happened. Where destroying the samples from single crystal when we go to the powder under compression, where limitation imposed by the diamond anvil cell are the same. But we should not forget we always dealing with extremely small samples when we go to any reasonable pressure range. The measure of smallness of materials object in the human impression is the diameter of a human hair. If you compare this with the size of a typical sample and the let's say 100 GPa pressure, you see that we are dealing with something which is about 10 times, maybe 20 times smaller than the size of human hair. So, and this requires special development if we are going to analyze our material with X-ray diffraction. The advantage in the powder X-ray diffraction, which was done over the 90s and 2000s, allow to very comfortably work with a relatively simple structured materials, like, for example, iron hydrides. This is an example from a nice publication by Lubet group on the iron hydride when with a well-indexed powder diffraction and in assistance with the theoretical calculations, the group managed to solve the crystal structure of material, at least locate the heavy iron atoms. However, when we are talking about something more complicated, like, for example, geo-related materials or even material science, when we synthesize something new which we do not know, we have a 20 diffraction peaks and five phases, some of them are low symmetry, large unit cell parameters. This methodology become basically unreliable. How to move forward? We should not also forget that the other technique, like, for example, very interesting in advanced dynamic compression technique in nuclear ignition facilities, for example, now also allow to produce the powder diffraction, but the quality of diffraction which we're getting so far are very close to what we got, let's say, 40 years ago. And on our own experience, we know that such a very poorly resolved and very bad in the future's diffraction pattern very often interpret wrongly. So this is also not a real, at this stage, a real method of study materials in ultra high pressure. The alternative is a single crystal diffraction. And we all know the principle. We should rotate the crystals located in the diamond anvil cell, collect the series of diffraction patterns, which we call the step scans, then process these step scans frames in the standard software. We are mainly using the Chrysalis Pro software, but there are many different others. And in this way, we can precisely determine the unit cell parameters, space group, and from the intensities, solve and refine the crystal structure. The problem is, of course, that we are dealing with the real life, and the pattern which we normally have or which we normally see in the reciprocal space, analyzing data from the diamond anvil cell are awful in the terms of normal crystallographer, where full of junk reflections due to diamond, due to spikes on the detectors, they are extremely complex due to presence of many different phases. So it requires special methods of their analysis. Over the several years, we developed these methods. A few years ago, Yegor Koimets and Maxim Bykov proposed the special advanced filter now incorporated in the Chrysalis Pro program, which allow to separate, to delete the obvious junk reflections like diamond reflections or pressure transmitting medium reflections. But we're still struggling with finding the domain in this very difficult data. And it actually, to a certain extent, limited the application of the technique which we pushing forward. Now, basically, these days, we are presenting to a community new software developed by our PhD student Andrei Aslandukov and his brother Matvey Aslandukov from Ukraine. He is actually a programmer, which should help anybody from the student level to use methodology and be able to do the same things which we are doing after years of training. So the idea is that we, as usually, collecting the raw frames, when we making peak finding with the Chrysalis, creating peak table, if necessary, clean it, and going to the program which we call DAFI, Diamond Automatic Finder. After this program, we load the output again to the Chrysalis, and then working with the data as a standard crystallographer way. So I would not go into details of the algorithm. To be honest, I would not be probably able to explain all details. The idea is just simple. We're analyzing all directions, finding the rows in the reciprocal space, points in the reciprocal space, which contain most of the reflections. When we checking if these reflections forming the lattice in one dimension, and if we find it, check if it's working for a whole data set. Here on the left, you see how the classical or typical for us example of yttrium heated in the nitrogen. We have around 70,000 reflections. Blue one, around 20,000 reflections are cleaned by a special filter, which I mentioned today. And just in the few clicks and about 1 minute, we can get from this messy data set where domains, as the one as on the middle slide or picture which I showed you, on 10 altogether shown in different colors, and all of these domains with 100 of reflections corresponds to the phases we have in the sample, and this allows to actually quickly online analyze the data and extract information. In fact, today at 17:00 Berlin time, Andreas Lundukov on the user meeting at ICREACH will present his work and introduce this program. If you are really interested in this, you're welcome. You will get all necessary information. So that is about the development in terms of data analysis, which from our perspectives, for now, at the stage where everybody can use it. What about the limits with high pressure? I already mentioned that the diamond anvil cell by 2010s become so advanced that it allowed to work everybody at pressures range around 200 GPa. Some groups work higher, 300, 400, but it was considered as very unlikely that we will be able to go even to higher pressures. In 2010, Natalia Dubrovinskaya, co-author of this talk, and myself synthesized the nanocrystalline diamond balls from the glassy carbon. We explore the idea to break these spheres on the two half spheres, put them in the diamond anvil cell, and use effective of a double stage diamond anvil cell. Already in the first experiments published at 2012, we reported the pressures over the 600 GPa measured from the gold pressure scale. Over a few next years, we further refined the method of the synthesis of nanocrystalline diamonds, introduced the gasketed double stage assembly, and reported a generation of a pressure on the order of 1000 GPa, again based on the gold pressure scale. A few years ago, our French and United States, America, colleagues explore the idea to modify the shape of the anvils to make some kind of a toroidal cullet. In fact, as Agnes Duvalier, author of this work, mentioned, this is very similar in some respect to what we are proposing with the double stage. So we have actually a secondary stage mounted directly or produced directly on the surface of diamond. It's probably easier sometimes from the preparation, but we experience our group, I mean myself, experienced the problem in the generation with this device pressure above 400 GPa, while we know that the 400 GPa was already used even at experiments with nice experiments by Paul Lubert on hydrogen. So, in order to improve the technique in terms of preparation, stability, and the ability to get a little bit larger sample for very high pressure X-ray diffraction studies, we decided to add on top of the toroidal part, or flat part of a toroid, our usual half sphere from a nanocrystalline diamond. And it paid off. We were able to generate pressures over the 900 GPa, 900 GPa according to the rhenium, conservative rhenium pressure scale of Anzolini. I will talk about this a little bit. And you can see here the schematics of what we are doing, how we are preparing these anvils for the experiment. Here you can see the examples of the data collected at ID11 nano focusing beam line at ESRF. Here is an X-ray diffraction map, and each pixel is one of such a diffraction pattern. In fact, in each point which we consider as interesting and important, we can perform the step scans and analyze the data, trying to find the single crystalline domain and solve the structures of found phases. Interestingly enough, you can actually see here the same plot, but in the different colors. We observe this particular diamond anvil cell, three components: rhenium at the low pressure surrounding rhenium, which is obvious, and it was around 100 GPa. Rhenium at much higher pressure, which is shown here in the yellow, and new phase. The rhenium, for rhenium at high pressure, we got the latest parameters, which corresponds to the pressure of 900 GPa according to pressure scale of Anzolini, or above 1100 GPa according to our pressure scale by rhenium. I will not go into details of discussion which pressure scale is, from our opinion, more effective, but in order to avoid further complications, we'll use all this value from the Anzolini pressure scale. I would like to attract your attention for even for simple and highly symmetric material. We have a 75 reflections and make the refinement to R1 about 6%. It's something which we would expect even at ambient conditions, not in 900 GPa. Moreover, in the same cell, we found the new material synthesized due to laser heating from rhenium and nitrogen. It is known structural type thorium 7 C3, but it never was reported in the nitrites, and especially in nitrites of rhenium. And we now see some similarities in the crystal chemistry of heavy transition metals with transition metals of lower group elements like cobalt, iron, chromium. So what is important for our discussion now? But we have by this day, by this time, at least 3 experiments on the different diamond anvil, double stage diamond anvil cell on the rhenium nitrogen system. We have a diffraction data on the HCP, single crystal HCP rhenium at pressures from 650 to 900 GPa, different points. It's not systematic, but it's something which we can present, and we can prove that it actually exists. We twice reproduced the synthesis of rhenium 7 and 3 at pressures slightly above 800 and 900 GPa, and we analyzed in details its crystal chemistry, and we synthesized the novel FCC-based rhenium nitrogen alloy at pressures above 730 GPa. What I would like to say with all this demonstration, I'm not talking about the interest to the material or some observation about chemical bonding. I'm just talking about the methodology and ability to perform experiments at pressures well above 500 GPa. I would say that with all what I showed you now, this fact is established. In much more moderate pressures, we found that there are a lot of interesting things which can be discovered with a high pressure crystallography. We investigated boron modification, boron-rich borides, silica and silicates, oxide and oxyhydrides of iron and other materials, carbonides of different materials, carbides. We start to work on the hydrides. I will show a couple of examples today. So, of course, I will not talk about all of this, but I want to also demonstrate to you that in some cases, when we have a more or less systematic studies, we already may start to see some regularities. And such regularities we notice particularly in the behavior of dinitrides. Here, nice for me, I hope for you as well, pictures of a series of compounds we synthesized starting with nitrides of sodium, calcium, strontium, and barium. What is important for us that all our observations and theoretical calculations prove that these materials are ionic. And for ionic compounds, we should expect certain, let's say, charges of cations and anions. So far, before our synthesis of calcium, strontium, and barium, potassium, sodium nitrides, people believe that the charge of N2 groups should be integers, 3, 4, 2. What we found that it should not be, or maybe not be integer, and moreover, where the nature of this non-integer charge is translated to the metallicity of this, or connected with metallicity of these compounds. We found that there is a very strong correlations between the crystal chemistry, mainly nitrogen-nitrogen distance in these compounds and their formal charge, as you can see on this graph. Moreover, there is, as in the classical ionic compounds, correlation between compressibility of the materials and their formal charges.
Dobronsky, you have 5 minutes.
Yes, I will try to be fast. Okay.
Thank you.
So,
Thank you.
plot like this, you can see in the works dedicated to halides, oxides, silicates coming from the middle of the 90s of the last century in the work by Pruitt, Finger, Hazen. But now we can extend same understanding, same type of analysis to classes of materials which never exist at ambient conditions. Little bit on the very hot topic of superconductors. Of course, this is very interesting. If you have a room temperature superconductors, you have a flying cars, computer in the supercomputer in the pocket, green energy, everything. And at first glance, it seems that the dream is coming closer. People reporting the room temperature superconductivity at pretty high pressures, but still looks like the temperature not really limited. So the problem is that all these works are based mainly on the Raman spectroscopy characterization of the materials or some powder diffraction. And it contributed poor characterization of material, contributed to questions which is raised by some members of the community. Is this real effect, or it is a kind of artifact? We should not forget that the whole gold rush for high temperature superconductivity started from a publication by Dian at co-authors, where reported the possible superconducting transition H3S at pressures at temperatures around 200 K. The point is that Duan in fact predicted a lot of different sulfur hydrogen compounds which never was observed in the consequent powder diffraction studies. I will not describe what people talk about this, but in fact we have seen something like H3S, but probably not other compounds. So we decided to investigate with our methods sulfur hydrogen interactions using sulfur loaded in the paraffin. Already in pressures as low as 40-60 GPa, we found formation of a number of materials with very large unit cells containing dozens of sulfur and hydrogen atoms per unit cell, which are even cannot be considered at the current state of the ab initio search algorithms. Just to make the long story short, we found that there are at least 3 different novel additional to the cubic IM3M H3S compound other materials. And what is important that all these materials are present all together in the diffraction patterns. So if we consider just powder diffraction images, still images without rotation of a sample of a significant degree, let's say of plus minus 30, like we are doing, you can easily miss the complex materials, like for example this hexagonal face with 112 atoms per unit cell, which in fact in the still images that gives just few single spots. You can misinterpret these spots as dust on the diffraction pattern and just see only powder rings of cubic compound. In fact, looks like for us a similar situation take place for Valentanium hydride studies. This is a pattern from Drozdov and all famous publication in the Nature, and you can really see the presence of small peaks in the patterns. Well, without going to any details, where interpretation of this pattern was performed based on the theoretical calculations which predicted existence of uranium H10 compounds. But in fact, when we started to look for this, we found that lanthan H3, lanthan H3X plus, lanthan H4, lanthan H5 something, and in total for now we have 7 different lanthanum hydrides. What is interesting and important for us, that all what people so far considered as a basically one phase, in fact presented for different phases from lanthan H6 to lanthan H9 and lanthan H10. This may be a significant effect on all measurements which were reported so far in the literature. And before I will finish, it looks like theory make a good guidance to what to look for synthesis, but it's failed to predict for now at least, as we can see, the full richness of the material. First, look for lanthanum hydrides where was only 3 compounds. We have now 7. And what is interesting, we see the structural analogies of these compounds which we synthesize in many other lanthanides and rare earths. And it means that we should reinvestigate accurately all these systems. So instead of conclusions, I did not have time to talk and show. What we see in high pressure crystallography, chemical reactions. We see that its chemistry not expected, not predicted so far. We see formation of open structures, and we see the structural complexity. All of this promise us unlimited interest to the high pressure crystallography in the coming years. So thank you very much for your attention. This work was supported by a number of funds, and a lot of people contributed to this work. I even cannot mention all of them on one slide. Thank you again for your invitation and attention.
Yeah, thank you, Professor Leonard. So, any questions?
I have a question. Now, do you suspect the work done by Ranga Dias in obtaining the so-called room temperature superconductor, is it not reproducible? What is the problem?
Well, there are many layers on your question. I do not know what is reproducible. Maybe synthesis of a material is reproducible, but doesn't mean that this is only one single phase or many different phases. And there is a combination of phases which give interesting properties. Second question, if there is really superconducting transition, or we are observing something else, for example, consequent metallization of the different phases. Or we have one phase which can demonstrate several structural transitions upon cooling. So as for me, it's nice that some people look for this problem and trying to investigate it. I'm not convinced yet that we really have the bulletproof of superconductivity. By myself, I work a bit on the resistivity measurements, and I know how fragile conclusions which you can draw by mainly resistivity measurement. I am not expert in the other type of measurement presented on these works like susceptibility, but if you work in the publications by Hirsch, for example, who reanalyzes, even if we forget about the claims about the manipulation with the data, still the absolutely clear problem is the very tiny, very ambiguous signal. That's what I can say for now.
I think this is definitely opposing the, he calls it rather scientifically, using words that which are aggressive words. He's just telling that they are not acceptable, something like that. but metallization should have been observed. But the same group, or Rutgers group, they did not observe metallization. Metallic hydrogen also they failed because it could not be reproduced by them. But of course, later it was obtained, and metallic hydrogen is known. But I don't know about LaH10 is proven, and this carbonyl compound metallization has been seen. If metallization can be seen, that is one step ahead.
Sir, we are running out of time. So we can discuss through email. So,
Okay,
Professor Menon, I
okay.
have one question. So this, how about this barium azide, strontium azide you are telling now? Are they new or already known?
I did not get your question. You're talking
No,
about
this-
strontium azide. Okay.
Yes. Yeah. Strontium and barium.
Yes.
I think they are already synthesized, or this is the first time you are trying to synthesize?
Strontium and barium azides, which we presented here, these crystal structures and arrangement, are new phases where not exist so far. It's dinitride, it's nitrides, it's not azides or dinitride.
Yes.
Yeah. Okay.
Yeah, because normally the earlier one was N3 twice, but it is N2 thrice. What you are doing?
Exactly.
Okay. Thank you very much. So, any other questions? So, if there are no questions, let us thank Professor Leonard for a very wonderful talk. So, now I will give it to the chairman.
Professor Dubrovsky, on behalf of the organizers, we are pleased to present this memento. It will be mailed to you.
Thank you.
Thank you very much, sir.
Yeah, thank you.
Thank you. Yes, acknowledging his own way.
So now we will start oral presentations. First presentation is by Dr. G.M. Bhalerao. He is a senior scientist from UGC DAE CSR Kalpakam. He is an expert in carbon materials, electron microscopy, and structure property correlation. Today, the title of his talk is High Pressure Studies on Core Shell Carbon Nanostructures. Over to Dr. Bhalerao.
Yes, ready. Sharing the slide.
Yeah, am I audible?
Yes, you are audible. You are speaking from where?
I am speaking from UGC.
Very good. Please go ahead. Yeah.
Okay, my presentation is visible?
Yes, sir.
Yes.
Okay. Good afternoon to all. First of all, thanks for considering my giving me opportunity to present this work. So this is some high pressure studies, XRD and Raman studies on core shell carbon nanostructures. And first of all, I would like to acknowledge my collaborators and my student Srinivas Reddy, and all these collaborators, without which this work not have been possible. So first, some background. So carbon under pressure has been studied since long. First reports of effect of pressure on carbon is the transition from graphite to diamond, which the ballpark figure we can give at more than 10 GPa and about heating at 1500 degrees centigrade or more, it converts to diamond crystals, and it is well known. But the story doesn't end here. There are a lot of allotropes and a lot of effects and a lot of interplaying between the hybridization of carbon, which gives rise to so many reports, which many times are conflicting, as well as at so many places there are some holes which we need to fill. So I'm touching up on a couple of more recent studies, like for example, a study reported in 2019 states that graphite to diamond transition is also possible at sub-GPa pressures at room temperature, subjected to shear. So they have used shear diamond anvil cells. So graphite can be transformed to diamond at sub-GPa pressures. Whereas diamond itself was investigated as a high pressure calibration standard where the Raman line of diamond as a function of pressure is given here. I think that the reference is hidden somewhere here, but it was in Nature Communications. Then one step ahead, there are amorphous carbon phases. So amorphous means you have a mixture of different hybridization of carbons, sp2 and sp3. However, the interesting mechanical properties have been reported in a physical review letter studies in 2011. So the schematic is like here, a 70 micron diameter carbon, amorphous carbon particle, spherical particle, was compressed between two diamonds. And so these polar sides, it was touching to those diamond anvils, whereas on the equatorial region, it was under hydrostatic pressure. So hydrostatic pressure media was measured by Ruby, and it was showing a pressure of 57 GPa, whereas on the polar region, the pressure was shown to be 127 GPa. So what they're reporting interestingly is that shear stress of 70 GPa was present here. And and after calculation, they told that it forms amorphous diamond. They have shown some Raman spectra, and the amorphous diamond where strength is 130 GPa, which is kind of surpassing that of diamond also. So it is again not a very, because there were some rebuttal studies also afterwards. But interestingly, the thing is that now you can see that on the polar axis, there on the polar position, there is huge 127 GPa stress, whereas on the equator, it is about 60 GPa. So there is some pressure gradient, of course, right? Now, this pressure gradient, it was very interesting, and we tried to measure it. I mean, axially, how much pressure gradient it can withstand, or how much some measurement. Right? So our study is kind of first of its kind study where we tried to devise experiment where, like here it is a amorphous carbon shell, and at the core of it, if I put a pressure marker, okay, and put hydrostatic pressure around the surface and measure both the pressures outside and at the core, then we can know the exact pressures of outside and at the center, right? So it will give a qualitative, more quantitative. I mean, it may not be absolute, of course, there may be chances of several errors, but this is the first kind of study that we have devised this kind of experiment. So what we have synthesized is, we have synthesized core shell carbon nanoparticles. At the core is gamma Fe2O3 megamite particle of around 5 nanometer diameter, and it is surrounded by amorphous carbon shell, which goes from diameter up from 20 to 40 nanometers, sort of. I will show the TM pictures later. Now, this is our experimental object. Now, what is the control object? Control object will be the same nanoparticle which is at the core, but all the shell removed, the same material, same particles, the shell removed by some method. Now, what is the method? The easiest method what we observe, what we can devise is oxidation, but it was not possible because at the oxidation temperature of amorphous carbon, the gamma Fe2O3, which is the original core particle, it will convert to, it will phase transition, high temperature phase transition to hematite. So that was not possible. So we have devised something which is RF plasma treatment. Now the scheme for the experiment is as follows. We do high pressure XRD. So and we compare for these both cases, shell removed and with shell, the despacing of the marker material, which is Fe2O3 at ambient and we compare it at ambient and high pressure. So in the easiest words, okay, if at all there is any pressure difference from outside to inside, right? So the core material, which is Fe2O3, its bulk modulus will show us variation in both the cases. So that's what we wanted to see. Now, the material was synthesized like this. So it was a very simple thing. The olive oil as a precursor with catalyst of Fe2 with ferrocene, it was burned in a lamp flame. And it was deposited here on a substrate, which is glass slide. we simply scrap it. So it is like that kajal, no, lamp black. So we scrapped it and then sonicated in propanol, and then we started the experimentation. So this is the Raman spectrum of the starting material. So clearly you can see the D and G peak. And here it is the core material, Fe2, gamma Fe2O3. These are the see this left side bottom. It is a simply shell without core. So it was synthesized without using ferrocene. So it is almost spherical amorphous carbon particles, and towards the right it is the core shell particle. So you can appreciate it is here. If the individual particle which is sitting, it is typically of 14 nanometer diameter. Okay. Now, these are the results after the oxidation. So left side, it is the starting material. Anyway, one thing I would like to share is there have been many iron oxide particles which we first did chemical treatment and removed it. So there will be only core shell particles for experiment, right? So this is the core shell particles. And after plasma oxidation, the plasma oxidation was carried out by RF plasma in RR cat Indore. With oxygen RF plasma, and that blackish appearance becomes grayish. So there is a lot of removal of carbon. So most of it is brownish grayish appearance. And so this is the these are the two materials, right? So this is control material. This is our experiment, and we did XRD at Indus 2 at 0.633 angstrom wavelength. So the top is the core shell particles, and the bottom panel is only core particles. The pressure calibrant was internal standard, no, not internal standard, silver standard. So silver peak was calibrated for to obtain pressure. And when we fitted and obtained the pressure variance of its unit cell. So what we found is here, and after the fitting, this blue line is the core shell particles, and the red line is shell removed iron oxide particles. So we can see with the pressure, its unit cell is getting compressed more. And what we obtained is the effective bulk modulus of gamma Fe2O3 core particles was showing indeed a drastic change. So with shell, actually, with the surrounding carbon shell, it was showing about 266 GPa bulk modulus, whereas without shell, it was showing typically of 200 GPa. So this without shell, it is matching the literature value of this thing, iron oxide particles, which is of the order of 180 to 200. It falls in that range. And since we are using our own blank sample, so we did not, we don't want to compare it quantitatively directly with the gamma Fe2O3 bulk modulus with literature, since it is a relative. Okay, so you notice the relative change here. And if you focus in this figure where we are showing the 311 reflection of gamma Fe2O3, so without shell here, we see that between the ambient and about 5.6 GPa, it is at about 5.6 GPa, the shift is huge, okay, as compared to with shell. So definitely this is a clear indication that the pressure is restricted due to carbon shell. So there is some pressure drop. Okay, so that nanoparticles above 20 to 40 nanometer amorphous carbon, they are say restricting the pressure to travel to the core. Now what may be the reason? So in order to prove that, we did Raman spectroscopy, because amorphous carbon is not showing XRD peak, so we don't know what is happening there. And the Raman experiment, Raman spectroscopy is the best way to probe carbon materials, especially in sp2 and amorphous carbon. So here it is the G peak, which is shown here as a function of pressure. The left panel is showing the loading sequence, whereas right panel is showing the unloading sequence here. Now, what we can see is this GP consists of two peaks, G1 and G2. Mostly G1 is considered as a principal peak, which.
Kalirao,
Yes, sir.
you have about 2 minutes.
Okay, sir. So you can clearly see that the G peak is blue shifting here, and the reversible changes are there. Okay. So there is no phase transition and all, except the small peak is coming here. We are still under analysis, which is still under analysis. So here it is plotted as a function of pressure. So we get a gradient of this thing, G peak position as with respect to pressure, 3.79 centimeter inverse per GPa. Now, if we compare, the red one is our work, 3.6 centimeter inverse per GPa for G peak. If we compare with the graphite G peak in two different from two different literatures, which is more? So that graphite is more soft as compared to our nanocarbon black. Okay, whereas it is our nanocarbon black is harder than graphite. It is still softer than the diamond. So it falls in between. So just as a schematic, I mean, if you simply take consider that omega proportional to under root k by m formula. So some interplay between the two sp2 and sp3 hybridization of carbon in amorphous carbon is playing a role. One more thing, what we obtained is a compressive stress gradient of about 100 megapascal per nanometer inverse, which if you compare with that reported experiment of shear stress, where they are obtaining in a shear 1.3 gigapascal per micrometer inverse. So units are actually the same, megapascal per nanometer, and this is same. So our we are showing the compressive strength is almost say 50 times more than that. So which makes sense. So, but this is the first time reporting of this thing. So as a model, you can consider that here in your right, it is a high resolution TM image of this thing. At the center is core particle surrounded by amorphous carbon. And interestingly, graphene and diamond, they have similar Young moduli, about 1050 GPa. But they are intermixing, they are percolating into each other. Okay, so that but their angular their geometries don't conform. So they may be restricting each other and consuming that pressure part, which is causing this kind of huge compressive stress gradient. So there is one experiment reported where they are showing that a supportive structure of to a single wall carbon nanotube, it makes it to support higher pressure for buckling, against buckling. Whereas if there is something which is not supporting but protruding like nanopods, the collapse is at earlier pressures. So in conclusion, what we found from these studies is carbon black particles having core shell structure are studied under high pressure up to 25 GPa.
Your time is already up. Bolero, Dr. Bolero.
Yes, I am winding up, sir. Carbon shell is structurally stable up to applied pressure of 25 GPa, and there is no pressure, no phase transformation observed. And phonon mode variation with pressure suggests that an interplay of sp2 and sp3 type domains might be resulting in a microscopic fatigue, resulting in the observed pressure drop across the amorphous carbon shell. Thank you so much. Thank you, sir. Thank you for listening. Can I unshare this?
Yeah, please. So
Any
next will be
Any
Dr.
questions? If there are no questions, we can move on to the next talk. It is by Dr. Chitra Murali from Bhabha Atomic Research Center. She is a senior scientist working at Bhabha Atomic Research Center, Mumbai. She has been working on hydrogen bonded under pressure using Raman studies. He has done systematic studies on inter and intramolecular hydrogen bonding in materials to understand their effect on various properties and also provide input to computational modeling. A recent interest is in the study of high pressure and low temperature behavior of benzoic acid derivatives using spectroscopic methods. So over to Dr. Chitram. Can you hear us, Dr. Chitra?
Can you hear?
Yeah, we can hear you.
Please share your presentation.
Thank you. I have already sent the presentation. Should I share here from here? Or can you show?
Yeah, you
Can you
can
show?
share.
No, better you share it, madam, because otherwise I will say next slide like that.
No, it is
I'm
being shared
sharing.
from, no,
I'm
it is being
sharing.
shared from here.
I've sent. Share.
Ma'am, due to some technical issue, can you share it from your side?
Yeah, we are sharing now.
We are doing.
Can you see your slides now?
No, sure. Start.
Thank you very much. Thank you very much for providing opportunity for presenting my talk in this conference. Can you hear?
Yes.
Yes, we can hear
Can
you.
you hear?
Yes.
The title of my talk is Benzoic Acid Derivatives Under Pressure, a Raman Spectroscopic Overview. Next slide. Collaborators for this work are all my colleagues from High Pressure and Synchrotron Radiation Physics Division, BARC Mumbai. Next. Benzoic acid derivatives are large molecular systems. They are characterized by hydrogen bonded dimers, and also large non-bonded interactions are found to play an important role in these materials. Benzoic acid itself is a pharmaceutical compound, and its derivative salicylic acid is also used as a skin cream. And aspirin is the most widely used drug for pain, inflammation, and fever. And many of these molecular systems are used as co-crystals in pharmaceuticals for various pharmaceutical applications. It's of interest to explore polymorphs of these molecular systems at high pressures and low temperatures. We have in this we have carried out a number of spectroscopic and diffraction studies of some of the molecular systems, and also using DFT calculations, we have tried to understand the non-bonded interactions in these materials. Next slide. Next. Depending on the position and nature of the functional groups in benzoic acid, one can obtain diverse properties. One can see that there is a significant difference in the melting point depending upon the use of the position and nature of the functional groups. In the case of aspirin, which is acetyl salicylic acid, there are a number of polymorphic forms found even at ambient conditions. Next slide. At ambient conditions, it exists as intergrowth of form 1 and form 2. And there is a recent study which has carried out high pressure. They have found that there is a transformation of ASA1 to ASA3, whereas ASA2 becomes a disorder. Can you go back to the earlier slide? Sorry, next slide. Next slide. Next, yeah. In the case of aspirin, ASA1 transforms to ASA3 across 2 GPa, and it goes into a disordered phase above 7 GPa. And many of these benzoic acid molecular systems, they are having good phase stability even at the pressure of up to 15 GPa. A number of high pressure crystalline phases are obtained. Mostly Raman investigations have been carried out on these materials, and they have in fact suggested a number of subtle changes in the case of benzoic acid 0.6 GPa, 3.7 GPa, 11 GPa. However, X-ray diffraction studies do not reveal any structural transition. In the case of salicylic acid, we have carried out Raman and X-ray diffraction studies. In fact, we have observed a first-order structural transition across 7 GPa and also subtle transition across 1 GPa. And orthothalic acid, which we are at present working on, we have found subtle changes across 0.5 and 6 to 8 GPa, and isothalic acid also show some subtle changes. And in the case of, as we see in aspirin, the polymorphic forms, there are only subtle changes in one polymorphic form to another. So it's of interest to understand the nature of subtle changes, which are mostly using Raman spectroscopic studies. It's more, one can get better insight. Next slide. Salicylic acid, we have carried out X-ray diffraction studies. We see that there is a lattice parameter crossover across 1 GPa and also first order Traxeros transition across 7 GPa. And in the case of Raman, we see a splitting of the lattice modes. Next slide. Also, the OH stretching mode, which is associated with intramolecular hydrogen bond in salicylic acid, we see a reduction in the frequency prior to the transition pressure. And also we see broad bands, CH stretching bands above 7 GPa. Next slide. In the case of orthothalic acid, also we observe structural transitions are across 0.5 and 6 to 8 GPa. Next slide. In the case of orthothalic acid, we have also carried out DFT calculations. We see that the CHO interactions, the increase, reduction in the CHO parameters are observed across 7 GPa, 6 GPa. There is a change in the angle, which suggests there is a change in the configuration of CHO bond parameter across this pressure. Next slide. When we compare the behavior of benzoic acid and othalic acid, actually across 0.5 GPa, when you look at the carbonyl stretch modes, at ambient conditions, one can see 2 bands in the carbonyl stretch region. However, as you increase the pressure across 0.5 above 0.5 GPa, the right shoulder disappears. The reduced intensity is appearing. Similar, the ring stretch mode also, the shoulder of the ring stretch mode also disappears across 0.5 GPa. Similar changes are observed in benzoic acid also. And at low temperatures up to 5 Kelvin liquid nitrogen temperature, they have actually tried to interpret these changes using neutron diffraction studies. And they say that this is because of the existence of 2 kind of configurations A, B at ambient conditions, which at lower temperatures and higher pressures, one of the configuration ceased to exist. This is the interpretation given in the low temperature studies. Next slide. When we compare the behavior of othalic acid with salicylic acid, this kind of anomalous changes in the carbonyl stretch mode is not observed in the case of salicylic acid. This may be because of the presence of intramolecular hydrogen bond, which may due to which even at ambient conditions there may be only one configuration which is present. Next slide. Currently, we are trying to look more carefully into the non-bonded interactions in these molecular systems. We have tried to compare all the Raman modes. There is actually a good match of theory and experimental data for deformational modes in comparison to the CH stretching modes and C double bond carbonyl stretch modes. Which suggests that in DFT calculations, one has to include more non-bonded, non-bonded interactions have to be included to further refine the DFT calculations. Studies on salicylic acid and benzoic acid in this context is in progress. Next slide. I would like to conclude with this. Benzoic acid derivatives, actually there are a number of high pressure crystalline phases found as revealed by spectroscopic studies due to the presence of hydrogen atoms due to the difficulty of diffraction methods. It's spectroscopic methods give a good insight into the nature of hydrogen bonds in these systems. And the high pressure behavior of salicylic acid is quite distinct from both oxalic acid and benzoic acid due to the presence of intramolecular hydrogen bond. And using the spectroscopy obtained in our experimental investigations, we have using DFT calculations, one can further refine the potential in order to get more accurate high pressure structures, and we can use this for predicting high pressure structures of these large molecular systems, which are otherwise difficult to study using diffraction studies. Thank you.
Thank you, Dr. Chitra.
Thank you.
It's time for questions.
Start video.
Only has to ask.
Any questions? Or no questions?
There are no questions, then we can move to the next oral presentation by Dr. Kamali Joshi. And he's from CSR Institute of Minerals and Materials Science, Materials Technology, Bhubaneswar. Her area of research is Raman spectroscopy, high pressure studies, X-ray diffraction of various systems, including metal oxide framework systems. Over to Dr. Kamali. Please share your...
Good afternoon to all. Thanks, Dr. Gurpreet, for the warm introduction. So I'll just share the screen. So is it visible?
Yes.
Okay, my voice is audible?
Yes.
Yeah. So that thanks for the organizer for giving this opportunity to speak in this prestigious forum. The topic of my current talk is high pressure Raman high pressure structural and chemical changes of adsorbed water in MIL47 metal organic framework. So as we all know that what is metal organic framework, because it is a combination of central metal ion and the organic linker which constitutes itself to form the big three-dimensional framework. So the name of the MOF which I am going to study here is MIL47, where the central metal ion is a vanadium atom and the organic linker is a terephthalic acid. So in the high pressure, I am going to use a water as a pressure transmitting medium. Now under pressure, what is happening when we increase the pressure, what is happening with respect to structure and chemical changes which is happening inside the MIL47 framework. So this is the overall view of my talk. So with this, I'll just give the brief introduction. Brief introduction about the MIL structure, how it looks like that. So you can see here. So here is a vanadium atom which is surrounded by the oxygen, and this forms a vanadium octahedron, and these two vanadium octahedra is connected by the hydroxy bridging group, and these vanadium octahedra in turn connected by the terephthalic acid linker. So this is how it looks and forms a three-dimensional framework, and the whole one-dimensional framework is being shown here. You can see the vanadium octahedron and connected through the terephthalic acid linker. So when we synthesized as such, there is a hydroxyl bridging octahedron as well as some free terephthalic acid which is sitting inside the pores. So this is the two aspects which I am going to show here. Very important thing, when we synthesize it, the vanadium is in +3 oxidation state and it is a hydroxyl linked, and some free terephthalic acid which is present inside the pore apart from the linkers. Okay. Now in the MOF terminology, there is something called activation. So when we activate the MOF, the free terephthalic acid which is inside the pores getting evaporated, and it will be no TPA will be present inside the pores. So this is the activated form. In the activated form, the hydroxyl link is replaced by the oxygen group, which means it gets oxidized, and the vanadium will be in the +4 oxidation state. So this is a difference between the two, that is asynthesized and the activated form. I'm not going to spend much time on the activated and the asynthesized form, but I just want to say that in asynthesized, it is a PNMA orthorhombic, and its activated state, again, it is the same structure, not much change here. So now the motivation slide comes here. So this high pressure XRD in presence of water has actually been done before, but please remember that here the two vanadium octahedra is linked by oxygen, and of course there is some free terephthalic acid is present. This is neither activation process nor the asynthesized. It is in between the two. Okay, so now with this structure they have done the high pressure XRD, and they found that there is a transition which is occurring around 1 GPa, and this 1 GPa transition is due to the water molecule which we use as a pressure transmitting medium is gushing inside or entering inside rapidly at 1 GPa, and it is going to the IMCM structure, which is again the orthorhombic structure, and as a result there is an increase in the unit cell volume due to the expansion of pore cavity, which accommodate the water molecule and replaces the free terephthalic acid which is present inside the pore cavity. So this is the chemistry which they have explained. Now my question is, if this oxygen group is replaced by hydroxyl group, that is one.
I think Kamali lost the connection.
We'll wait for a few minutes.
Yeah, definitely, sir.
Done, and it is shown here. The now next step is Raman studies, and you can see the difference between the activated MiL47 and it is a asynthesized form. When it is activated, the hydroxyl is getting oxidized, and that is why it is showing the Raman mode at 940 centimeter inverse. This is a difference between the two forms. Now again the comparison plot of this activated asynthesized pure TPA, commercially available TPA, just in order to show that this free TPA molecules, the Raman modes corresponding to free TPA is lying around here. The shoulder which I'm showing as arrow, this Raman band corresponds to the free TPA molecules. Okay. Now the next assignment is to do the Raman assignment, and these assignment I just borrowed from different isostructural groups material which is available, and these are the assignment being done here. Okay. So now high pressure Raman experiment has been done on the movable diamond anvil cell, and these are the different pressure parameters which I have used for this. And of course it is a MOF. It will not sustain after much higher pressure. So I just stopped around 5 GPa with increasing and decreasing cycle. So this is a high pressure Raman experiment. With increasing pressure, this is a Raman plot which shows a different spectra of MiL47 in presence of water as a pressure transmitting medium. So visually we can see a two transition at 0.3 GPa and 1.1 GPa. So you can see at 0.3 GPa there is a disappearance of lattice modes. So there is some kind of change in the pore cavity here. And at 1.1 GPa, there is emergence of new mode, and there is a new mode around 1100, which corresponds to ring breathing mode. So the conclusion is we are getting a two transition. We are suspecting two transition at 0.7 and 1.3 GPa. Now, since we are using water as a pressure transmitting medium, of course, we are getting the OH stretching band of water around 3000 to 3500 centimeter inverse. I would like to emphasize, which means that the previous XRD's plot on this oxy link to vanadium octahedra shows a sudden gushing at 1 GPa. But at microscopic, our Raman spectroscopy is a microscopic phenomenon, right? So at 0.1 GPa itself, the water molecule is slowly entering inside the pore. That is why we are seeing the word stretching frequency of the water molecules. So slowly it is entering inside the pores. So it is slowly entering as well as exchanging the TPA molecules which is present inside the pores. So this is the thing which we are getting. Now the next slide is, this is the TPA, free TPA molecule, which I shown as a shoulder at the previous slide. Just plotted the TPA versus pressure. Here comes our exciting, beautiful chemistry which we get from this Raman plot. So if you see around 0.3, 0.6 GPa, there is a change in slope. You can see the change in slope, which shows a rapid hardening, which means that water is slowly entering inside and the pore cavity remains the same. TPA is also same. It feels some congestion and shows a hardening. It shows unusual hardening in this pressure state. Of course, at the 1 GPa, it attains a critical pressure limit. It undergoes a phase transition, and the pore cavity got expanded. Now the water molecule is sufficiently, it is moved around and it is forming a hydrogen bond with the free TPA molecule which is present inside the pore. So because of which the interaction, because of hydrogen bonding interaction, we can see the sudden decrease around 1.1 GPa, which is due to the expansion of pore cavity during transition. So after that, it again follows the hardening with respect to pressure. And after 1.5 GPa, we could not trace out the TPA mode, which means that all the TPA molecules are completely replaced by the water molecules. So this is a beautiful chemistry which we are getting from this plot. And of course, the conclusion is there is a hydrogen bonding interaction which is happening between this water as well as the free TPA molecule. That is where the sudden decrease is happening with respect to the pressure transition stage. So again, this one I would like to show that we have done the experiment very carefully, that water inside the framework and water which is present outside the framework by defocusing. Okay. So water, Raman, that is word stretching frequency of water which is outside the framework look like this, and it is inside the framework which looks like this. And from literature, we say that the low frequency components are corresponding to hydrogen bonding component, and the high frequency component, which is nothing here, is due to the least associated molecules. Okay, since water which is available more at the outside the framework, that is why it is the spectral bandwidth is very high, which means there is a more hydrogen bonding interaction. That is why it is huge and broad. But within the framework, since it is narrow and confined, it shows a narrow spectral bandwidth with respect to the low frequency component, which corresponds to the high hydrogen bonding interactions. Now I am just showing the plot, water inside the MAL47 and outside. And this is a low frequency component, this is a high frequency component. Since we can see during the transition stage, there is a rapid, we can see the decrease or softening, which means that the water which is present outside the framework are forming some kind of intervibrational coupling due to the delocalized nature, and it is softening. But in water, which is present outside.
Kamali, 2 minutes left for you.
Yeah, yes, sir. I'm going to finish. Yeah. So which is fine, inside the framework is not going much change. Of course, there is a hardening changes there, which means there is a kind of the suffocation which is happening with respect to the interaction with the TPA molecules and the water. So this is the thing which you are speculating or conjecturing from this plot. And we say that there is hydrogen bonding interaction either between water and the free TPA molecules or with respect to the hydroxyl linked framework itself. That is one paper showing that the binding site for the water molecule will be near to the this is hydroxyl linkage. So there may be a hydrogen bonding interaction also, which causes the phase transition with respect to the hydroxyl linkage. So in order to confirm the structural evidence, we have done the high pressure XRD in electrosynchrotron with Dr. Bobby Joseph, who has given a talk yesterday. And we see that when we seal in water, just in put in a DSC seal in water, we get a free terephthalic acid reflection peaks, which again says that there is a water molecule which is slowly entering inside our cell, inside our framework. Okay. And also it confirms that 0.6 GPa, we can see the current new peaks are coming, and 0.7 GPa, it is forming to the new phase. This XRD pattern exactly matches with the earlier oxygen linked pattern. But at 1.3 GPa, we are getting extra peak, which means there is a lowering of symmetry. Because of that, we are getting the peak. And at last, I'm going to confirm that there is two transition occurring at 0.7 and 1.1. And we done a ritual refinement, and unit cell length with pressure has been done. And here also at 0.7 GPa, there is a unit cell volume expansion occurs due to the water molecule is being entering inside the pore cavity, and it is going from PNMA structure to IMCM structure. This is also the evidence which show the structural change happening in that. So at last, I want to conclude that, of course, if you change the oxy-linked bridging group by hydroxyl link group, there is a change with respect to chemistry as well as the structure. That is why the framework shows a two transition at 0.7 and 1.3 GPa, which we explained through a Raman spectroscopy, which is a microscopic probe, and later on an X-ray diffraction, which confirms the structural transition, phase transition. So thank you very much for giving this opportunity. And I would like to at last acknowledge DST SEOB fellowship, postdoctoral fellowship. During this period only, I have carried out this work under the mentorship of Professor Chandrabas Narayan JNCSM, and DST for carrying out the high pressure synchrotron experiment, travel support, everything. And presently CSR IMMT for giving for permitting me to present this work in this forum. Thank you very much.
Thank you, Dr. Kamli. Now, any questions?
For your one question, Gurpreet, Dr. Vaideshwaran, that this electrosynchrotron, what was the energy like you used?
Sir, it is a 0.4754 angstrom unit.
0.54
angstrom unit, sir.
Any other questions?
Any
specific reason why you have used that energy?
Sir, in metal organic framework, D spacings are large, so we have to go a low wavelength to capture the reflection peaks.
Okay, thank you.
Thank you, sir.
So Kamali, I have one question.
Yes, sir.
So are you able to get the hydrogen positions precisely?
No, sir, I could not get the hydrogen position precisely, but there was one recent computational work with respect to some hydrocarbons, acetylene, ethylene. With respect to this framework, they found that the binding site is near to the hydroxyl is more feasible when compared to the other site.
Okay, but these are not single crystals.
These are not single crystals, sir.
Okay, fine. Thank you.
Thank you, sir.
So if there are no more questions, we can thank Professor G. Vaideshwaran for chairing this session. Thank you, sir.
Kamali, you can thank me.
Thank you.
Thank you, sir.
So thank you, Professor Vaideshwaran, for chairing this session.
Thank you, Gurpreet.
With this,
and nice to see Kamali after a long time.
Formally, let me acknowledge Professor Vaideshwaran's contribution in managing this session very well within time. And I'm very pleased to present this memento to Professor Vaideshwaran on behalf of the organizing committee and MRSI.
Yes, sir. Thank you. Thank you very much.
so with this, we conclude the technical session 5. We will break for lunch and we'll be back for the 6th technical session at 14:00 hours Indian Standard Time.
Okay, bye.
Thank you. Bye.
Dr. G.D. Mukherjee, are you there?
Yes.
Hello.
So we can start the session?
Yeah, hello. Can start the session. Can you hear me?
Yes, sir.
Yes, sir. Very much.
Welcome to the technical session 6. This session has 2 invited talks and 1 plenary talk followed by 2 oral presentations. The first invited talk in this session is by Professor S. Raju, Director, Material Science Group and Metallurgy and Materials Group. He is an expert in field of material thermodynamics and physical metallurgy and is well known to us. The second invited talk is by Professor S. Arumugam. He is professor at at Bharati Southern University.
Bharatidasan.
Bharatidas University. Tiruchirappalli. Professor Arumugam has established the first center for high pressure research in the university. He has been awarded many medals and awards, including Dr. APJ Abdul Kalam Lifetime Achievement National Award, NISCD Bangalore 2021, Lifetime Achievement Award, Indian Spectrophysics Association India 2020, MRSI Medal Lecture Award, Material Research Society of India 2018, Tamil Nadu Scientist Award in Physical Sciences. He was a visiting professor at Institute of Solid State Physics, University of Tokyo, Japan. He received the ICU Fellowship, Osaka City University, Japan 2006, USA Exchange Fellowship, DFG, Germany 2005, and he is twice recipient of JSPS Postdoctoral Fellowship, Japan. The plenary talk in this session is by Professor Michael Eremetz. He is from Max Planck Institute for Chemistry, Germany. His area of expertise is high pressure physics and superconductivity. He is famous for critical temperature 250 Kelvin for superconductivity in lanthanum hydride under high pressures. He is recipient of many awards, including Bernard T. Matthews Prize for Superconducting Materials 2022, James C. McGrath Prize, American Physical Society, the Bragg Lecture at University College London 2020, Breakthrough Winner in Physical Sciences, Falling Walls Berlin 2020, Rigman Award AIR APT 2017, Honorary Doctor Degree from Leipzig University, Germany, Hugo Fano Gold Medal 2015. He also appeared in the list of Nature's 10 people who mattered that year in 2015. This session will be chaired by Professor Gautam De Mukherjee. We listened to Professor Mukherjee's talk yesterday when he delivered a wonderful talk in the first plenary lecture in this conference. He is from Indian Institute of Science, Education and Research, Kolkata. As we know, he is an expert in studies of novel physical transition at extreme conditions of pressure and temperature and physical properties of material related to geophysical interest. Now I invite Professor G.D. Mukherjee to chair this technical section.
Thank you. So we have 3 high-profile speakers for this session 6. I welcome you all to the session 6 session. And I think their introduction have been quite nicely said. So without waiting, I would like to invite Professor Raju to start the first talk. And it is 30 minutes talk, so 25 minutes for talk and 5 minutes for discussion.
Fine,
Okay,
sir.
time starts.
Thank you, Doctor. You are able to see the presentation, right?
Yes, we can see the presentation. Thank you. Yeah.
Thank you, Dr. Gurpreet, for a very serious introduction, and thank you very much, Dr. Gautam De Mukherjee, for agreeing to chair this session. So before going further, let me formally acknowledge my indebtedness to the ICREACH 2022 committee. A wonderful thing to be a part of this highly motivated team. And I also acknowledge Director ICREACH Dr. Venkatraman for his constant encouragement and support to host this event. Take this work further forward. And I am personally beholden to Dr. Chandrasekhar, my friend and Associate Director and colleague at MSG. In fact, he has been constantly nudging me, the thermodynamist in me, to look into high pressure domain. Because I wouldn't have agreed to be a part of this high pressure community where I consider myself to be an outsider. Okay. The plan of this talk is like this. This is going to be a simple, straightforward thermodynamic analysis of alloys under high pressure. And I am sure that most of us have some amount of background, but yet it is customary to have a little bit of pedagogy on pressure as an influential thermodynamic variable. Then I will follow it up with a brief description of the essential aspect of thermodynamics of alloys under the combined condition of high pressure as well as high temperature. Then we will develop a framework on how to deal with the volume effects of alloying. Whatever framework that we have developed in this study, I am going to show you an illustrative application on uranium zirconium solid solution, which incidentally is an important constituent for our metallic fueled fast breeder reactor. And then we will have a very brief concluding session. I will try to complete it within 25 minutes. And since this is an online talk, I'm sorry that you will not be having the freedom of interrupting me in between, but I will be available for very detailed comments through email or otherwise. The first and foremost of the personality in any thermodynamics is Dr. Josiah Willard Gibbs, probably the first theoretical physicist of United States of America, and in all probability, had he been lucky, he should have got the Nobel Prize, first Nobel Prize as well. Well, the influence of pressure as well as temperature is nicely spelled out in the Gibbs phase rule. P plus F is equal to C plus 2. At plus 2, we know the P stands for the number of phases, F stands for the degrees of independent degrees of freedom, and C for the number of components, and 2, which is important for our present discussion, stands for temperature and pressure. Please recall, this rule strictly holds good at thermodynamic equilibrium only. So how does this Josiah Willard Gibbs justify this phase rule? He is a master of what is known as the establishment of the law of chemical equilibrium, which roughly says for a system to be stable, for an equilibrium, the delta G has to be less than or equal to 0. And it's trivial to note, you can decompose this Gibbs energy change for any process into its enthalpy and entropy. Please remember this, the T stands for temperature, hyphenated P is pressure, and X is a very generalized composition variable. And what I have listed down beneath is a very standard textbook level thermodynamic relations, which can be obtained from Maxwell relations. But the important point that we should note here is that pressure and temperature influence Gibbs energy in an independent but related manner. The final word is the catch. So here I have, in this view graph, I have illustrated two things. One, the Gibbs free energy variation as a function of temperature for two select pressures. Okay. This is a case in which the free energy for the alpha phase intersects with the beta phase at a reference point at T equal to TR at P0. And as a function of increasing pressure, the transformation point is shifted further. And on my right, I have shown one of the latest computed pressure temperature phase diagram for pure iron, in which you will see the slope for various BCC to FCC, BCC to SCP. You will see both positive slope as well as the negative slope. And I will. Can you make it disappear? This is the second case in which the transformation point is shifting to the right upon the increase of pressure. And again, you will see on the right side, you will have a phase diagram in which you see a phase boundary, namely that BCC to liquid ion, which shows a positive slope. How is it generalized? The very most generalized way of understanding is that you should know how don't do it. Gibbs free energy changes as a function of temperature and pressure. Here I have written a very generalized thermodynamic relation. All that you need to know is the two integrals, that VdP as an isothermal trace, as well as the SDT, how the entropy varies as a function of temperature, and if you happen to know accurately one reference Gibbs free energy, then in principle the entire pressure, temperature, horoscope of the material can be cast. And the slope of this line dP by dTV is given by the Clausius-Clapeyron relation, and which is nothing but the slope of two fundamental variables. That is, the temperature dependence of Gibbs free energy is ratioed over the pressure dependence of free energy. And just I have also illustrated a very simple, extremely crude approximation. If you assume the slope del S by del V is a constant, then you can very easily write an expression for pressure variation of the transformation temperature as a function of pressure. Well, I am continuing this analysis a little further. In the top portion of the view graph, I have shown how do you generally calculate the trace of the Gibbs energy, both as a function of the change in temperature as well as the pressure. This is normally done in two ways. If you have the reference point, then you calculate isobaric trace and then sum it. Second step, the trace over the isobaric trace. If you look at it, at the bottom of it, the pressure derivative of G is given by the volume change. The temperature derivative of G is given by the entropy trace. And the reference state data, as I said, it is very important. Fortunately, for most of the system, this data is now well established. There may be some uncertainty for a few metastable phases or extremely complicated rarer systems, but for most of the general systems, you get into the reference book, this data is available. Right? You can refer to co-data sources. And if you go to the PVD equation of state data, thanks to the DAC, the plethora of DAC experiments, you also have a fairly reliable pressure, volume, temperature data. Where you really lack is the calorimetric high temperature, high pressure CP data. So if you were to experimentally calculate, if you had to calculate the PT trace as a function of composition, you should necessarily have the combination of thermophysical equation of data as well as the thermochemical calorimetric data. But unfortunately, the second part, namely the calorimetric data, is still woefully lacking for many of the functional material. Therefore, I would also take this opportunity to stress this point to the high pressure community that it is all right to work with a very interesting, physically interesting compounds, but you should also take a little bit of what you call sympathy towards generating data towards functionally important engineering alloys, where you would be in a position to tune the properties by high pressure if you literally, if you really have some amount of control over this high pressure calorimetric or thermochemical data. Right. This is a view graph in which I have summed up what I have said today. If you have all the data, both, as I said, equation of state as well as calorimetric data, then there is no difficulty in calculating the pressure temperature curve at all. But then oftentimes, as you know, that these data are sort of a priority for many people here. Therefore, what the next step is that you go to ab initio calculations and then do that. Try to generate what is not available through experiment. The scheme something goes like this. You split up that into a two superposable component, that is a function of volume as well as a function of temperature. One is known as cold pressure term, another is a thermal term, and there are other terms like magnetic or diffuse, etc. You have a variety of choices for writing this cold pressure term, and you also have an extremely well-proven ab initio phonon spectrum or Debye-Einstein Brunetian quasi-harmonic variants depending on the system, and you also have recipes of various technical sophistication for estimating the magnetic contribution and defect, etc. Then ultimately, at the end of the show, what do? You have a recipe for enumerating this Gibbs data for all the competing phases. And once you have this data, then you input it into a Gibbs energy minimization. Just, for the humorous sake, I have written it as Gemini, nothing to do with the astrological Gemini, Gibbs energy minimization routine. And then at the end of the day, if you do all these steps, you will get phase equilibrium PTX diagram. So the gist of this view graph is that pressure, temperature, composition data are in fact calculable. But then what is missing is, in all these things, we know how to calculate, but do we know how to understand it? To do that, we need a conceptual framework to understand, and that is the purpose of this talk. See, in this view graph, I have picturized a very simple system, that is namely two elements A and B combined in the proportion of X and 1 minus X atom fraction to form a simple substitution solid solution. The treatment is absolutely general. It is applicable to liquid, solid, or whatever it is. And we also know that the Gibbs free energy of mixing can be written as a sum of the pure term plus a solution or a formation enthalpy or formation Gibbs energy term. And if you take the pressure derivative, it is nothing but the volume. It translates into additive law for volume. And we also know the Gibbs energy can be decomposed into enthalpy as well as entropy. Therefore, if you take the derivative, then you see the pressure effect on Gibbs energy translates into volume, and that translates into two distinct contributions, one based on enthalpy and one based on entropy. But the important point to note is not only it has two terms, but these two terms are very sensitively dependent on temperature, pressure, and composition. Now, if this volume term is positive, that is dou G by dou P is positive, then the free energy increases with pressure. Therefore, the system would be unstable. If the volume effect is negative, then the high pressure stabilizes the system. But how does you generalize this inequality in terms of thermodynamics? It says that if the pressure effect of over enthalpy is dominating, then you get positive volume effects. On the other hand, if the pressure effects on entropy of mixing is dominating, you end up with the negative enthalpy of mixing. And the second point is, it is not only the lack of compensation between the entropy and enthalpy that decides the effect of influence of pressure on the system, but more importantly, they are composition dependent. There are 2 points. One is that in very, very few systems, you will come across a situation where the volume effects are zero, where the pressure effects on Gibbs energy is almost negligible. In other words, popularly in mineralogical literature, it goes by the name of Zen's law. And in metallurgy, we have a similar law called the Vigat's law. But though it is a little bit of common sense, I used to tell people often confuse between Zen's law and Vigat's law. One is a cube derivative, another is a primary linear lattice parameter, and they are not one and the same in the thermodynamic sense. And the second point, namely the lack of compensation between enthalpy and entropy, it is extremely important in multi-component system, because today there's a lot of uproar about high entropy alloys. You add about 5 element, 10 element in equal proportions, and people say it lifts the entropy. I will blow up this myth in a matter of minutes, but the point is it is a very strong chemical interaction. If they happen to prevail between atoms, then this pressure effect on entropy and enthalpy are extremely non-trivial to calculate. Okay, so this is a schematic view in which I have shown a simple binary system. You can have both positive deviation of volume from the linear additive law and as well as a negative deviation in different regime. On the left, you have the enthalpy dominating over the entropy effect. On the other one, you see that entropy dominating over the enthalpy effect. A very classical example of the system is iron chromium. Unfortunately, I have not brought that corresponding data. If you see the very simple binary iron chromium, as well as in some portions of iron nickel chromium, you will see both this scenario are operating. Okay. Then how do you estimate thermodynamically? Yes, this entropy as well as entropy contribution to the volume change. If you look at it, this derivation is quite rigorous, almost like a textbook, but I have just listed it for those, for the benefit of research scholars who would like to have a look at it, how I have done it. See, if you know thermodynamically, this pressure effect of enthalpy is governed by the thermal expansion effect. If you do the substitution into the primary, you will get a very straightforward relation which says that the enthalpy effect on volume change is a very sensitive balance between the thermal expansion of the alloy over that of the composition weighted pure element. And vice versa, if entropy is also given by a related expression, but the important point is, if you see, both entropy and enthalpy are interrelated. They play independently, but they are not acting totally independent of each other. See, I have summed up here by saying, if the dou V dou T, that the temperature derivative of volume happens to be greater than that of the volume weighted temperature coefficients of expansion of the element, then the entropy effects dictates a positive effect. If it is the other way around, if the thermal expansion of the alloy happens to be less, then entropy effect supports a volume contraction. And the final point is that I have taken it up for one temperature and composition, but in principle, it can be generalized to any temperature and composition, except that you need to have very accurate thermochemical and thermophysical data. This only stresses the point that high pressure, high temperature thermophysical data and alloy systems of practical interest are indeed needed. If you actually have this data, for example, if you are able to deconvolute the high temperature, high pressure diamond anvil and get a reasonably credible data, then it is in principle possible to estimate the effect of pressure and temperature on Gibbs energy as well as the volume effect. Now, how do you phenomenologically interpret this effect? Normally in in material thermodynamics, this formation enthalpy is split it into the strain energy contribution because of the volume difference effect. And then another contribution that arises because of the extremely strong interaction that is prevailing between the atoms. And if you neglect other hyperfine interactions like magnetic or defect and all, they have to be superposed. And this is basically stems from the Hume-Rothary's rule. In reality, but actually you should remember this is only hypothetical splitting. Both chemical as well as elastic interaction effects are not two different contributions. For convenience only, they are treated as a separable components. Here I have taken this a very simple picture where you see the volume upon alloying undergoes a decrease. From pure element volume of A to B, the volume of formation is negative. And I have also added an intercept at a particular composition, and this is known as a partial volume. That is V star A is the effective volume of element A in the alloy. Similarly, that V star B is the effective volume of B inside the alloy. If you see it, they are distinctly different from the pure element volume. It is because of this volume change, the system has to do some amount of energy to accommodate, to induce this volume change. That is known as the strain effect. On my right, I have picturized two empirical potential energy curve, where I have marked down delta EB and delta EA, which corresponds to the energy or PV work involved in changing the volume. So how do you estimate this? It's very simple. There are various ways of doing it, like the very rigorous way, like SLB. But I have taken here a very illustrative route, namely that for extremely small volume changes, you can write it as a series expansion and then truncate it at a convenient position. And then if you do so with the caveat that at equilibrium, that first derivative has to 0, the second derivative, namely the internal pressure, can be expressed as a ratio of the bulk modulus to volume, and higher derivatives can be expressed in terms of the pressure derivatives of bulk modulus. If you do all this substitution, you get a finally very beautiful, appealing approximation, namely that the elastic contribution to the formation enthalpy can be written as a function of the square of the volume change. Actually, I have taken this approximation because this is exactly mimics the approximation that is done by SLB way back in 1956 using extremely complicated argument, but I have done it in my own way through thermodynamics. But it only shows that the energy involved is independent of the sign of the delta V because it is proportional to the square. And another important point, that thermophysical property, namely the ratio of bulk modulus to volume as well as the normalized pressure derivative of bulk modulus, these two are key parameters, equation of state parameters governing the elastic effect. Then how do you know the chemical interaction effect? Admittedly, this is the most complicated factor to be evaluated for any system. Ideally, you should do it by an ab initio method, depending upon the complexity of the system, but that cannot be done for a general system. Therefore, what I have done, I have adopted a method called Miedema's model. Way back in the 80s, Miedema has proposed a semi-empirical model for calculating the enthalpy of formation. It essentially depends, it is a parametric way of calculating the formation enthalpy in terms of the electron density difference, the electronegativity or chemical potential difference. It only, I am skipping all the details, and this is such a standard model that if you get into web, you will get all the required information. And in my published paper, you will see all the required data are also listed there. The chemical interaction term can be reduced into, if you see again, that VA star 2 by 3 by BA minus VB star 2 by 3 by BB, that is the ratio of the molar volume to the bulk modulus. And then ratio of the molar volume of the solvent atom. That is, if A is the solvent and B is the solute, it depends on the difference, and then multiplied by a free factor, namely the x into 1 minus x, that is a composition ratio. And the sign and magnitude of this essentially governs the chemical interaction term. If it is positive, then you have a enthalpy gives a positive effect. If it is very negative, the enthalpy gives rise to the negative effect. And please recall, these are all not very difficult terms. If you have very accurate PV data, this can be estimated, and it's a matter of Excel spreadsheet to get all these things. Now, how do we estimate the entropy contribution? Again, I go back to the analogous way in which I have estimated the entropy, the enthalpy, namely the configurational entropy, the vibrational part, the magnetic part, and the other parts, if it happens to be the defect or superionic solids, that entropy due to ionic disordering also have to be incorporated. The most important point now is the configuration. If you have an extreme, ideally random solid solution, that entropy of mixing is independent of pressure. Therefore, for a totally random system, entropy does not at all contribute to volume effect. If you have an high entropy alloy, which is absolutely random, there is no way that you can generate high entropy. The high entropy part must necessarily come from the vibrational, magnetic, or other. Right? And then how do you estimate the vibration? As a vibration entropy, if you have the accurate data of the phonon spectrum, then absolutely there are no issues at all. Failing which, if the temperatures are very high, you invoke Debye-Einstein Brunetian approximation, and I have just listed the essential thing. All that it requires is the knowledge of Debye theta, and the Debye theta variation as a function of volume, which is given by the Brunetian parameter, and the reference value, you can estimate the vibration entropy. And you take the pressure derivative, all that you require is the pressure variation of the Brunetian parameter, and which is not that difficult to estimate if you have a very accurate data. And in the CalFORD community to which I belong, all these things that I have said now are tackled in a semi-empirical manner. See, this is an illustrative case study where I have made an attempt to estimate the pressure effects on the Gibbs energy, namely the volume effect for a solid solution called gamma uranium zirconium. This is a BCC system. Gamma uranium is BCC above 667 degrees centigrade or 1050, and alpha zirconium also has a high temperature BCC phase, and they form a continuous solid solution. And unfortunately, this solid solution is not stable at room temperature. If you do a fast quenching, you can retain it metastably for some of the compositions. Why this system is important? This is important to nuclear energy because this is one of the constituents for uranium-plutonium based metal fuels for a fast breeder reactor. So again, unfortunately, the required equation of state data and high pressure, high temperature thermophysical data are not available for the system on an experimental basis. Fortunately, there are pretty good ab initio results from Landau, Soderlind, and also from other groups. And I have taken the data from the Landau's group, and I have shown, I have done all those Excel spreadsheet calculations where you can see that the total volume effect as a function of composition for zirconium uranium system is fully dominated by the enthalpy. The bottom curve, namely the triangle which denotes entropy, which is multiplied by a factor of 10, you see they are extremely small. For all practical purposes, the uranium zirconium is governed by enthalpy considerations, not by entropy. I mean, this is a very general statement. One should not generalize this for other alloy systems, and this is also at an hypothetical temperature of 298 K. If you were to do it at a very high temperature and high pressure, certainly anharmonic effects would be there, and therefore entropy effects will certainly attest into it. But even then, a system like uranium zirconium is bound by enthalpy considerations. Okay, what is the take-home message? The take-home message is the effect of pressure reflects very subtly through volume change. And we all know that volume effects are both temperature and composition sensitive. A comprehensive thermodynamic analysis of volume calls for explicit treatment of both enthalpy and entropy effect. And it is possible to have both positive and negative deviations of delta Vm, or the both positive and negative effect of pressure on Gibbs free energy depending upon the sign of the delta Vm. The chemical interaction term can be modeled through a variety of ways. For example, if you are working with a transition metal system, the parameterized tight binding model or Petitford scheme, or what do you call, even if you have a rigorous embedded atom potential, this can be done. And the strain energy contribution can be done if you have very accurate equation of state data. And finally, I would also say that what I have done here is only the tip of the iceberg. We really need to do lot more in depth. And for those who wanted to know further on this line, a paper of mine is coming in the Transaction of Indian Institute of Metals in a matter of months, and where you will find more details. I think with this, I thank the organizers for giving me this opportunity, and if there are a few questions, I am pleased to answer.
Okay, I must thank Professor Raju to finish in time, so you have sufficient time. Yeah, so questions. It's excellent talk, basically. Yeah. There's some question. Who is? Yeah.
Chandrasekhar. This is Chandrasekhar.
Yeah. Please go ahead. Yes.
Thank you, Raju, for a wonderful and fundamental talk. Initially, I was a bit enthusiastic about your suggestion of taking up these experiments. But when I look at the delta V versus X, the delta V is very small.
Normally, the pressure effects on volume are very small. So you need to have very accurate measurements.
Very accurate.
Very accurate. That's why I have said. Nowadays, the X-ray data, in principle, you are able to get it up to third decimal. The one that I have used with the ab initio data, which is normalized with available experimental data. Though I have not gone into detail about the experimental sources, our own data is also there.
I'm really happy that maybe some of the young researchers can take up.
The essential point is people work on novel systems, but that should be done. But there's a lot of scope to work on engineering systems.
The other question was that you said that high entropy. You said the high entropy is a misnomer. Are you?
I don't say, see, simply because that you happen to cook 5 element, 10 element, the entropy of the system increases. It works for cabbages, radish, everything. So that is not science. It has to come from strong physical interactions. Anybody who talks of entropy, devoid of energy interactions, they are talking something else. You cannot think of entropy in isolation with the fundamental interaction. That is a message. So the high entropy alloy community, they say, if you put copper, nickel, aluminum, zinc, the same entropy. Titanium, tantalum, vanadium, niobium, same entropy. Does this sound sense?
So the thing that random alloy doesn't mean it is high
entropy. Yes. So if you incorporate structural order, order normally brings down entropy.
Thank you.
Okay. Any other question? So if there is no more question, I have a question myself, Mr. Raju.
Yes, sir.
So if you suppose you have an excellent talk, must say that the very fundamental talk, but basically it is highly useful for high pressure, high temperature studies. The materials related to when you are looking for geodynamics,
Absolutely, sir. Absolutely, I agree with you.
Yeah. So just one question. So suppose you see a phase transition under high pressure.
Yes.
So you will see that. So what we'll see, so in that case, so if you don't see the volume change that you see, so from there, can you calculate the elastic part? I mean, what is the elastic change in it, or the entropy part?
Sir, actually, I have not included in this. There is a way to estimate the entropy of phase transformation from the slope. What I'll do, I have written a paper in 2002, a couple of months back, it appeared in Metrans, where it is possible to see, ultimately, sir, the rigorous thermodynamics, the field is totally closed. It depends on how judiciously you invoke approximation depending on the system. So, if you know accurate value for one of the system, there is a scaling philosophy. I don't know how to put it a little more subtly, but for example, if I know a system called NIAL, and if I know accurately, there is a way to get some of these things for FEAL also, if they belong to the same structure. I would summarize it this way. Ideally, it is desirable to have very accurate high pressure, high temperature equation of data in conjunction with thermochemical data. That is what I keep saying. But if you put a lot of stress on volume measuring, to a large extent, the deconvoluted thermal expansion values, which suffer from quite a bit of uncertainty. But then it is not that difficult. I agree it is very difficult, but it is not that difficult to do a thermochemical measurement. For some reason, there is an apathy among calorimetrists. If somebody tells you, the pressure variation of enthalpy, it is a terribly useful information for ab initio fellows. For some reason, it is now almost 35 years I am running into this field. I am yet to come across a couple of papers on how to determine enthalpy of formation or entropy of formation under high pressure. And I have not come across an experimental study, not much.
Yeah, I think that's a very important part that you have mentioned.
In fact,
Yeah.
I agree to this talk only to make this message alone.
Okay. Yeah, there's a question from Dr. Ashok Mani. I mean,
Yes, sir.
yeah.
Yes, sir.
You have to unmute yourself.
No, I have, yeah.
No, Dr. Ashok Mani.
Sir, unmute.
I have to unmute Dr. Ashok. Can you unmute, or if you can put the question on the.
Professor Ashok Mani was one of our very old contacts. For some reason, I think we could not meet in between.
So he has written something I don't understand. Furnish parameter as a function of Vegat's law, James, something he's written.
Sir, what is?
Can you unmute Professor Ashok Mani? You need to unmute.
Okay. Dr. Raju,
Yes,
Weber's law, people say it over-enjoyed its application. One point. Second point, how far it is strict. And we use the Zen's law because apart from cubic phase, we went to zirconium alloy, which is of importance to nuclear reactors and cladding and so on. And we use the Zen's law because the SCP structure. So Zen's law, because you got the C and D, both are compressed, and so we use the Zen's law. So any comment on that? And the second point is you made a mention about the Grunheisen parameter. I took the Grunheisen parameter to calculate the average phonon frequency long back, or even the double temperature. And I used a paper by R. Chidambaram, Sikka, Godwal, and they are given the Grunheisen parameter as a function of pressure. And they are given three different equations. Which one is more accurate? And the Grunheisen parameter is a function of pressure and temperature. Is there any relation connecting pressure and temperature? Grunheisen parameter being used as a function of pressure and temperature. And Diffon times CalFad, the Diffon times thing, which is the latest one apart from CalFad. There are three questions.
Okay, sir. One by one, I will answer. The Zen's law, I mean, that Vygots's law, you know.
Yes.
As far as I know, it is the only law which is not obeyed by 99% of the system and still called a law.
You are right. I agree with you. Right.
I mean, it's a very convenient approximation.
That's an approximation,
yes,
right?
But fortunately, I mean, there's a small advantage because Vygots's law says the bond lengths are additive. For example, the bond lengths are additive. And if you go back to pseudo-potential description of bond length, you know, there's a very classical paper from Russian group, 1960 or 70, which shows that the Pauling's linear scaling of bond length with respect to bond order, you know, is, that way you can relate this Vygots's law to the what you call fundamental interactions with a little bit of addition the bond order thing. Zen's law says that volume is additive. What does it say? Zen's law says the pressure derivative of Gibbs energy is additive. See, oftentimes for small excursions in pressure, you know, we use it. Around 1 bar pressure or 298.15 Kelvin, we use this Vygots's law without much error. As Chandrasekhar has pointed out, oftentimes this works to our favor because the volume effects are extremely subtle.
Okay.
If you wanted to study the electronics, what do you call that, effect of electronic interactions on delta V, you know, then the subtle effects are very important. And then the Vygots's law would obscure the physics.
Okay.
So if you have experimental data, it is better to cross-check and then use the experimental data rather than Vygots's law. But again, for most of the system, we may not have it. Therefore, we substitute it.
Anyway, choose was intelligent to put replace lanthanum by yttrium and raise the temperature. It is because of Weber's law. The contraction, because the size of the atom, there's a very advantageous thing. Second thing is the Grunheisen parameter. Has it been written as a function of pressure and temperature? Can it be written?
Sir, I'll just get back to your third question is with regard to Grunheisen parameter. I'm not an expert on this, but to the extent that I understand, See this, there are classically three equations are floating around that
Right.
volume theory, and then the original Slater's that what you call pressure dependence, independence of the Poisson ratio, and all those things are continuum mechanics approach to pressure variation of Grunitian law is well established.
Oh,
But
okay.
incidentally, it is also possible to trace Grunitian parameter as the pressure volumetric dependence of the vibrational frequencies that is summonable to ab initio interpretation.
Okay.
For some simple metallic system, for example, the tight binding model systems, there is a way to relate obtain Grunitian parameter from the electron density distribution.
Okay.
I don't have ab initio knowledge on actinide systems, but I myself have written a paper on how to estimate Grunitian parameter from electron density for transition metal systems.
Okay.
For oftentimes, I think that gamma by V, that for small excursions in volume, that normalized Grunitian parameter is amenable to certain scaling.
Right.
What amount of Russian work is there on this? You can consult. And as far as the Calford community, so the Calford community, to which I have been working for past 30 years, we don't pay too much importance on absolute values of Gibbs energy. What we bother about is the relative values.
Okay.
If you have seen, I will just show one of my presentations here. Can you move to the second presentation? It is not. Actually, sir, the point is this. You may have two different Gibbs energy curves, but then they will give the same phase boundary if the point of tangency is the same.
Okay.
So the Calford community operates like this only. They will have consistent Gibbs energy set, but not the correct Gibbs energy set.
Okay.
So it all depends upon the point of common tangency.
Oh, common tangent construction. Right.
Tangency. So if you have the correct starting point, namely the reference value system, and if you position the Gibbs free energy curve properly, you may still get the same phase boundary.
Right.
So it is very important, you should have some amount of experimental data and then use theory to do the interpolation and get the correct.
Okay, Professor Raju, I think let us, we'll continue with this after some time. Okay, so since time is going, so let us invite the second speaker, Professor S. Arumugam, for the talk. Professor Arumugam.
Sir, my colleagues are giving me this, sir, on behalf of the.
Okay, thank you.
I am pleased to accept, sir.
Let us thank Professor Raju for this nice talk. And let me now invite Professor Arumugam. Hello.
Yes, sir. Good afternoon, sir. Everyone. I'm just sharing my slide, please.
Yes, it is visible.
Fine.
And you are audible.
Could you see that? My slides?
Yes, we are able to see.
Yes.
Okay, sir. Thank you.
We can see that.
I am Arumugam from the Center for High Pressure Research, Bharadas University, Tiruchirappalli. My topic lecture, experimental facilities of the Center for High Pressure Research and important results of some strongly correlated materials. So I thank Dr. N.V. Chandrasekhar and other organizing committee members for giving me this opportunity. I chosen this topic because I would like to expose our facilities and our last 23 years of effort at Bharadas University to the people, those who are listening, to have to utilize our facilities and have a good collaboration. And for that reason, I chosen the topic more generally about to go ahead with our facilities. This is a unique center because the center was established in 2008 by Bharadas University, and this is a unique high pressure center in India, and this was established in 2008. These are our group members, while foreigner Dr. Geeta Balakrishnan visiting for a 1 week visit to our lab. And I am planning to give we are working on different materials. like high temperature superconductor, iron-based superconductors, CDW materials, topological superconductors, semi-metals, manganites, Heusler alloys, and organic materials. And what is the role of pressure? Before going into this center, till now we have published about 190 papers in the field of high pressure physics, and 15 PhD has produced. There are 10 students are currently working, and about 45 foreigners visited to our center in the last 20 years, and we established very good facilities. That is the brief introduction about our center. The importance, the role of high pressure, the origin of mechanism of superconductivity, and in the unconventional superconductor, and also understand the correlation between or the competition between the superconductivity and magnetism, and correlating with the structural and superconducting properties to understand the similarities and differences between the various superconductors like iron-based superconductors or 2D superconductors or bismuth-based superconductors, etc. And also we work on the magnetocaloric effect, pressure effect on magnetocaloric effect, and also it helps to find out the giant magnetocaloric effect, new materials, and also to understand the mechanism of colossal magnetoresistance. As we know very well, everyone, that calcium element shows the 25 Kelvin with applied pressure of 160 GPa. The iron shows a superconductivity of 2K at 20 GPa. And the maximum record of 164 Kelvin was observed in the mercury-based superconductor under high pressure of 30 GPa. And the recent lanthanum-based LOOFEA superconductor shows 43K under pressure. The TC was increased more than 15 Kelvin, and record of 9.1 Kelvin per GPa was observed in the iron selenium layered structure of cerium based compound. And the recent hydrates shows many hydrates were reported, and those shows the TC close to around room temperature, but the pressure is more than 150 GPa to 200 or 250 GPa. And the pressure helps to find out many new superconductors, and also even as we know the lanthanum barium copper oxide with application of pressure, and it has a drastic increase in TC, it leads to invention of YBCO. So like that, the many pressure induced, this is an example for pressure induced superconductivity in Ba2SC3, and these are hydrates. The first one was imported in H3S, and then the recent one was at 150 GPa with the lanthanum hydrate, and this is a phase diagram, and now the TC increases close to the room temperature under pressure. So this is the evolution of TC on till date, and we are working on mostly the combining the pressure, low temperature, and high magnetic field. It is an effective combination because we have been working on uniaxial pressure, hydrostatic pressure. Now started working on diamond anvil cell quasi hydrostatic pressure, and with the high magnetic field, of course, we have up to only 9 Tesla magnetic field, and low temperature 2 Kelvin. We have the setup. So with this combination, we can do the various materials. And as you know, the pressure, static and dynamic, and the static is hydrostatic and uniaxial and quasi hydrostatic. And we have been working on piston cylinder and cubic anvil. Of course, we are not working on cubic anvil, and we are working on modified Bridgman anvil technique. And uniaxial, we are working on direct uniaxial method, and quasi hydrostatic we have the Bridgman anvil, and also we have a diamond anvil cell for structure under pressure or resistivity under pressure. So, and also now we are planning to set up a shockwave facility very soon in the Center for High Pressure Research. So hydrostatic and uniaxial pressure technique, as everyone knows, that when you apply a pressure on, put a sample in a liquid, and with application of pressure, the pressure is apply in all direction and makes it uniform. And uniaxial pressure apply in only one direction, and there is a Poisson effect applies on when you apply uniaxial pressure. And recently we also developed a method without Poisson of without Poisson effect, we can also apply uniaxial pressure, and this is the simple principle behind that. And the facility that we have, we have established the 9 Tesla physical property measurement system with the AC DC transport with a multifunction probe, Hall effect measurement and heat capacity measurement, and with the temperature range from 2K to 400K with a 9 Tesla magnetic field. And this is the PT410. This is the one PT410. It is a one time you have to fill up the liquid helium. Once we fill up the liquid helium, then we have to use the high purity helium gas and use the PT410 and maintain the level of liquid helium about 80%. So if you, for any reason, the system is switched off for 48 hours, the whole helium will go away. It is not completely cryogen-free system. So these pressure cell, this PPMS, which can mount, we can mount the pressure cell 2.5 GPa, 3 GPa pressure cell, and 3.5 GPa pressure cell, which can go into the PPMS. With a multifunction probe, we can mount 2.5 GPa. Without multifunction probe, we can put 3 GPa and 3.5 GPa pressure cell. We can put into that. And also this is a VSM, vibrating sample magnetometer, which we can incorporate. We can make use of 1 GPa pressure cell for magnetic measurements under pressure. And also we developed the uniaxial pressure device for which can go into the vibrating sample magnetometer, which can go up to approximately about 10 kilobar or 1 GPa by magnetic measurements. This is the system which is now, after long gap, we are about to start the system in the center. And this is the cryogen-free 9 Tesla superconducting magnet with a custom-made variable temperature insert with a 50 mm bore diameter to suit the piston cylinder and modified Bridgman anvil about 40 mm diameter and the diamond anvil cell, which can incorporate. And this is a 9 Tesla magnet. This is totally cryogen-free system. And once you switch on the system in 36 hours, it can reach 1.8 Kelvin with all the measurement facilities. We are just arrived at our lab, and maybe in a couple of weeks we are installing the system. And this is the cryogen-free VTI, and 4K to 800K. We can do resistivity and AC susceptibility. And hydrostatic pressure, or we can put modified Bridgman anvil, and also we can put any piston cylinder pressure cell. This also have a 50 mm bore and without magnet. And with this system, we can do the uniaxial pressure work by incorporating the uniaxial pressure device from 4K to 300K with the AC or DC resistivity measurements, the maximum 1 GPa. And also we have made almost 4 or 5 samples on using the modified Bridgman anvil up to 8 GPa using resistivity measurements, which can go to 400 to 800K. And all the program and everything we have written using the LabVIEW, and it has been working for the last more than 10 years. And this is the hydrostatic pressure cell developed after the long struggle. And this is the pressure cell, which can, we have developed 3 types of pressure cell, which made of beryllium copper outside and a special steel alloy inside. And this is the outer is the beryllium copper alloy, which can go up to 2.5 GA. So these are the pressure cells, for example, piston cylinder and 1 GPa magnetic measurement. This is a cubic pressure cell, and we used it plenty of times in Japan during our visit. And this is a hybrid hydrostatic piston cylinder. So these are all the possible pressure devices for doing transport and magnetic measurements. The cubic anvil, which we have used in Japan, which can go up to 8 GPa. It's a very huge system and very difficult to have it in India. That is why we developed 8 GPa modified Bridgman anvil, the same, whatever the cubic press does, the same thing that we can do with the modified Bridgman anvil with a pure hydrostatic pressure, and it was developed in collaboration with Institute for Solid State Physics, University of Tokyo, Professor Watako's lab. And this is a piston cylinder pressure cell, and we have the easy lab pressure cell, and also we have developed our own pressure cell with the titanium copper as well as beryllium copper alloy. And this piston cylinder pressure cell, we can do the magnetization measurements using the PPMS VSM. The applied pressure in the pressure cell, you can do to use a tin as a manometer, as an in situ manometer, and you can put the sample inside the Teflon capsule along with the sample, so that first you can measure the TC of the tin, and then we can measure the TC of sample, because the tin has a very even 100 ISS, the superconductivity is completely gets suppressed. So we use the tin as a manometer and fluorinated 77 as a a pressure transmitting medium, and this is the calibration curve which can go up to 1 GPa. It has been, many times this has been done and calibrated using this equation. And maximum pressure we can go up to 1 GPa. And this is a piston cylinder hybrid pressure cell which can go up to 3 GPa or 3.5 GPa. And this is with a multifunction probe which shows in the bottom, which can go up to only 2.5 GPa. We use a conventional pour probe method and use a 100 micron diameter copper wire, and obturator and Teflon. Obturator is made of beryllium copper Teflon capsule which is filled with the Daphne oil, either 7373 or 7474 as a pressure medium. And we calibrate with a bismuth, generally use a room temperature bismuth calibration with these structural transitions. So this was developed here, and we use the generally we can do 4 samples, but currently we are working on simultaneously we can do measurements 2 samples at a time. And this is the actual picture of the pressure cell, and this is the R versus you can see all the transition and pressure versus load, and you can get the calibration with this. So the actual pressure was calibrated by the structural transition of bismuth as a function of pressure with the fixed points. And this is the various types. Completely we can make with the special steel alloy, both inside as well as outside, or we can use the beryllium copper outside, inside as a special steel alloy. So this is the holder to apply a pressure, and which is hardened in a typical atmosphere, and it works very well. And we have been using the pressure cell for about 4 or 5 years, and without any problem. And we use, this is a imported 20-ton hydraulic press from Riken Kiki, Japan, so that we can apply a pressure and we can release the pressure in terms of hours. We generally apply a pressure of more than half a day. For example, if you want to calibrate the pressure, it takes 1 day to apply a pressure and 1 day to release the pressure. So any application of pressure, for example, 1 GPa, we usually take about 3 hours. So we need a very precise system to apply a pressure. Normal pressure which has 100 ton or 200 ton, which is available in India, to my knowledge, is very difficult to apply very slowly. Otherwise, easily the piston breaks, either application or releasing the pressure. So this was imported from Japan, and it works very well for the application of pressure in the piston cylinder pressure cell. And this is a modified Bridgman anvil pressure cell, which I said earlier, which has been developed in collaboration with the Institute for Solid State Physics, Tokyo, Japan. And the advantage is this is about 39 millimeter diameter, which can easily go into the 50 mm bore of the new system or the old CCR VTI. And the difficulty in this, those who knows very well how to mount the sample in the cubic press, is easy to do that. The inner diameter of the capsule is 1 millimeter. The restriction is maximum of 4.4 millimeter is the length of the sample is allowed, because when you apply 8 GPa pressure, if you use more than 0.4 millimeter, you will get failure. So we use a 0.4 millimeter and length, and 0.1, 0.2 thickness, and width is about 0.2 or 0.3 millimeter. So this is a sample approximate diameter that we use, and three of our students successfully calibrated. 3 or 4 times, and we the up to 8 GPa. This is a typical diagram, pressure calibration. And also when I did first time, I could even reverse the hysteresis. Also, I took it back to the atmospheric pressure. With the hysteresis, I took the data, and this is the complete assembled setup. And we have to use 110 hydraulic press for application of pressure for this system. Whatever the cubic press, because you need a liquid helium of even about 50 liter or 60 liter, and more than 300 liters of nitrogen to cool the system and do the measurements in cubic press. It's a very expensive experiment and experimental setup even to buy. For this reason, being in India, so we have developed this and we have started using it, and the paper is, it is on the way. And we use this beryllium copper and tungsten carbide made of the pressure cell. Anvil is a tungsten carbide. Outer cylinder is hardened stainless steel. We use a gold wire, gold foil, platinum wire. And it's very expensive, 10 micron gold wire and 10 micron gold foil. Rarely we use a 20 micron gold foil and 10 micron platinum wire and 20 micron platinum wire. And the gasket made of stainless steel as well as pyroflate, because we use two different types of gaskets. And capsule is a normal Teflon. Use a pour probe method, and the Daphne use the pressure medium. Use do 2-pound silver paste, and the sample mounting generally takes, at least experienced students, it takes about 10 days to complete one set of mounting, because every mounting you have to give a curing time for about 24 hours. So it takes about 10 to 15 days to complete assemble. After the sample mounting, it takes about 10 to 15 days. Then you can load it into the system. Then you can start doing the measurements. So it's a tough job, but three of our students, one student is now in Cambridge. He left, and currently two students can do this. Other students could not do this experiment because it is very tough to do it. And adhesive, we use a Sticast and rapid rollite. We use, the advantage is less than the cubic press, and we use the same bismuth as a calibrant, as a standard, and we apply a pressure at room temperature and lock it and transfer to the CCR VTA with the magnet or without magnet, and we can do the measurements. And we need a very good microscope, at least with our 500 magnification, to mount the sample easily, and we can assemble it. So this is a quasi-hydrostatic pressure cell which was developed for alloys and metal samples. And this is the 2D assembly, and this is the top nut is made of hardened steel, and the cylinder hardened steel. Spacer is tungsten carbide. Sleeve is again hardened steel. Piston is a tungsten carbide. The another sleeve, hardened sleeve, and bottom nut is also hardened steel. So these are three different sizes of pressure cell, and we calibrated up to 8 GPa, which can go to 35 mm, 45 mm, and 25 mm, which can go to 8 to 10 GPa. And this is the various parts. And this is the clamp type pressure cell, which can go up to 8 GPa. Pyroflate and stainless steel is the gasket. Steator is the pressure medium, and tungsten carbide is an anvils. We use a stainless steel wire, platinum wire, use a pour probe method, use a CCR VTA. This is a calibration curve which obtained from the setup. And recently, actually, I have been trying to fabricate the diamond anvil cell for resistivity measurements. I spent about more than 4 years, and some of the fabrication was not very accurate than expected, because doing one sample somewhere outside is really finding it difficult. And many times the diamond was broken, then I dropped it. I purchased the diamond anvil cell from the Easy Lab recently for resistivity measurements under pressure, which can go up to 20 GPa. and students, one student is expert on doing this. He has been trained in Japan for 3 months and Grenoble for 3 months. And this is a pressure cell, and recently we sent the purchase order, and we transfer the money, and soon we expect the diamond annual cell for structural analysis under pressure. This is pressure cell generally we purchase suits for the Elytra. We have now strong collaboration with Elytra Italy, and now currently one student also visiting, say as a 6 months visit in Elytra, doing the structural measurements under pressure under the ICTP fellowship, and this is from Betsa, France. And this is a laser optical system, and for the Ruby pressure calibration, which can go through the microscope, and one microscope, you can see that this is a diamond face, and you can see this whatever you put the Ruby chip, and you can focus it, and you could, this is the laser system, and you can spectrometer, you can calibrate. So with this, we have established recently, and this is the Ruby calibration graph, and this is the micro drilling machine, which can drill about with the EDM technique with a 20 micron to 10 micron to 1000 micron, which everything is working very well. And this is a sample assembly. I mean, of course, this is an old assembly. I could not incorporate the recent picture in the diamond anvil cell for resistivity measurements. And this is a uniaxial pressure device. This is a uniaxial pressure technique. Generally, we can divide into direct method and indirect method. In direct method, one is a clamp type and another one is continuous type. In indirect method, there is a high resolution thermal expansion, hydrostatic measurements on supported film grown with a different orientation, changes produced by deforming the substrate, measurements on oriented epoxy crystalline in an epoxy medium. That are the way. And now we are using the, actually we are using the direct uniaxial method. This is a schematic diagram of the uniaxial pressure technique, and this is the first project that we obtained in 2001 from AICT New Delhi. We took about 3 years to develop this pressure cell. Is a 10K closed cycle refrigerator, which you can put this pressure cell here on top of the cold date model. This is a cold date model. We are a system, and this is the inner design, and this is the design of the pressure cell, and here is the sample. No pressure media ball, small flexibility in mounting or fixing the sample before start applying the pressure. And this is a paper published in Review of Scientific Instrument 2005 and 2007. And the first work was published in PRL 2002. And we also modified the same uniaxial pressure device for the variable temperature inset model. Because the cold date model, we are unable to go more than less than 20 Kelvin, and because it's a cold date may go bad. So we developed a system and modified same system, and you can go up to 4 Kelvin to 300 Kelvin without any problem. And you can do resistivity measurements under pressure for oriented single crystals. Why we are interested in this? Whatever the phase transition that occurs in the hydrostatic pressure, 3 GPa.
You have 5 minutes more.
Okay, so 5 minutes. So this is a pressure cell, and this is a device for AC solubility measurements. This is a coil specification, performance of the coil, and this is the how we are doing it and doing the pressure calibration. And this is the simplest system which anyone can do. This is a uniaxial pressure device developed for the PPMS VSM, which can go up to 1 GPa. And this is a pressure calibration curve for the tin and lead with the VSM system. And you know this is the neodymium doped lanthanum system. And when you apply a pressure parallel to C-axis, parallel to AB plane, TC increases. When you apply parallel to C-axis, TC decreases. The combined effect, you can see that the TC increases in one direction, TC decreases. And the same thing when you do under hydrostatic pressure, you can see the same thing. So what the advantage with in 40 or 50 megapascal, you can get the same increase of TC, the same structural transition, and you can observe using the uniaxial technique, and this also proved in the all effect measurements where the why the TC is increased, and this is the paper as first paper using the setup published in PRL 2002. The recent work that we published, the collaboration with Professor Lu, the paper was published in 2021, Physical Review B, pressure dependent modification in the LAASB to charge density wave system. This is a basic characterization of the single crystal, and this is high pressure XRD has been done with the Elytra, and DFT was done with the Professor Vagistan, Pranaya Vagistan. We have been collaborating for more than 4 papers now, DFT calculations, and this is the temperature dependence of resistivity and the lattice parameter for the system. And you can see that our R versus T data, how the CTW is getting decreased and suppressed. And this has been proved, and XRD as well as the DFT calculations, and you can see that it's a refinement data, and you can see that the variation of intensity as a function of pressure on different peaks, and you can see that pressure dependence of lattice parameter, where you can see that close to 3.8 GPa there is a change in slope, and where you observe the structural transition. This is a C/A ratio with the DFT as well as, and you can see that there is a change by up to 150 GPa by theoretical analysis. We put it, pressure significantly changes the cell ratio, and it is stable less than up to 150 GPa, and the C/A ratio is drastically changed. The volume collapse is observed. So the whatever the CDW 23K. Yes, sir. Conclusion.
Yeah.
Okay, sir.
2 minutes are there, so please.
Okay, we conclude. Okay. I thank the organizing committee for giving me this opportunity to give our to expose our facilities to the participants today. Thank you.
Thank you, Professor Mugam. So it is time for one quick question if anybody has.
Another comment. I should congratulate Dr. Professor Arbham, because I was the first person to write the project in Anna University 40 years back, and we were the first to get the rotating anode X-ray generator he would have used, and Anna University, and whatever Anna University did, he has excelled, and he has got a lot of things. I should congratulate him. And apart from that, the morning speaker from Chicago, and also Vaidiswaran, they are the people whom we grew fast. I am very happy. You can also interact with the Pannaya Vasishtan, Pannaya Ravindran also is available here. Maybe it is left to you. And I request all the people here concurrently present, and having visited a number of labs, Carnegie Mellon and Schilling's group, and many Wittig's group in Germany, many groups in high pressure. Now, I would like to say concurrently 3 megabar and a few millikelvin range, both are pressure and temperature varies. I hope India achieves that much facilities, and I, congratulate Armo for his excellent, worked very hard. And what I know from Sikka or maybe, I don't know whether he met Archadamaram, I don't know, but DST and other sources say that he has worked very hard. I'm extremely happy. Then thank you then. I don't have any questions.
Thank you, Professor. Thank you.
I think.
I would like to thank that my PhD from, even though from Anna University Physics Department, I did my PhD at ICREACH Kalpakam.
Yes, that's right.
With the help of Dr. Radhakrishnan and Shankara Sastri.
Yes, that's right. The rotating anode generator use Kalpakam.
Yeah, I think Professor Dr. Sangwani, I think let us proceed.
Okay,
yeah, so
let us proceed to the next talk. Thank you, Dr. Arabagam.
Yeah, thank you.
Thank you, sir.
Okay, good.
Now it is my pleasure to invite Professor Mikhail Erimets from Max Planck Institute of Chemistry, Mainz, who is a very old friend of mine, and it's nice to see him for a long time. And I have seen him working in the lab, and in my opinion, I think he's the best experimentalist I ever seen. And they work overnight, and he's expert in superconductivity, mostly high pressure superconductivity, and he's published so many seminal papers. So I'd like to invite Professor Erimets for his talk. Professor Erimets, you have a total of 45 minutes. So 40 minutes talk and 5 minutes for discussion, but I allot you around 35 minutes. Okay.
Okay, many thanks. Many thanks for introduction.
Yeah.
And let me just technical. It's a little bit different from Zoom, so here share is okay. Here, yeah, fine, good. I always
We can see your thing.
Can you see it?
Yes, I can see. Yes.
We can see.
Many thanks. Okay, let's start because we're out of schedule, as I understand. So let me talk about this progress in high temperature superconductivity, which recently we have. And let's start. Well, superconductivity, everybody knows here in this audience what is this. Just to remind you here from this historical plot that superconductivity normally considered is very low temperature phenomenon. It was discovered after liquid helium was available. And also another thing that it experiment always in some respect driven by theory, because there are predictions how electrical conductivity will behave at zero temperature. And so Camerlin Onnes was happy that according to his imagination, it goes to zero, but it goes to zero in a very different way. So it's some very unique phenomena, superconductivity. And it's very delicate phenomena. Only at low temperature you can imagine pairing of electrons. So, and long time it was considered low temperature phenomenon. And from the beginning, its natural question was, so critical temperature could be higher or not. It's only in mercury or not. And after that, a lot of other superconductors were discovered. And progress was very slow. It's some extrapolation, of course, it's unimaginable. So, and what is important here, great BCS Bardeen-Cooper-Schrieffer theory does not help to change this trend. So still superconductivity was very low. And Bardeen-Cooper BCS theory essentially weak electron phonon theory, and therefore it cannot predict high temperature. But later on, maybe 10, 20 years later, it was predicted basically that no bound for critical temperature. But it's also only approximation and instruct contradiction to experiment, which shows does not increase critical temperature. And this was point of disappointed of Bernd Matthias, which is great experimentalist, and he discovered more than 1,000 superconductors, but still he considered that superconductivity at room temperature is just a pipe dream. And also, he was very much disappointed with BCS theory, which is failed to predict higher critical temperatures. But of course, life is going and something happening. So what has happened, first of all, it's dramatic change in superconductivity view that cuprates, which shows that superconductivity could be very high temperature, above liquid nitrogen temperature. And also other families of superconductors appear something like this for instance, iron superconductors. And what we're talking now, we'll be talking about this hydrides. It's under high pressure, it's with critical temperature approaching to room temperature. So how it's possible? To continue, in fact, I should make some break, but to talk about metallic hydrogen. It's a different topic, but in fact, it's very much correlated with high temperature superconductivity, as you will see. First of all, hydrogen. It's our solar system basically metallic hydrogen because it's in interior of this Saturn and Jupiter metallic hydrogen, and so they are far bigger than other planets. But very interesting, this all mainly from another point, from point of view, for instance, superconductivity, which Ashcroft a long time ago he noticed that hydrogen could be a good candidate for high temperature superconductivity because of large Debye temperature, because of light element, high frequencies of phonons. It should be high temperature superconductor. He did not calculate, by the way, 300 kelvins, and he gave no numbers in his work. But in some lecture, he mentioned, as people told, that mentioned 40 kelvins. At that time, it was enormous critical temperature, and also people also talked that Mueller, he once attended Ashcroft lectures, and he listened this number, and for him it was psychologically important that critical temperature could be very high. And psychological effect, of course, is very important also. But what is also even more interesting here in hydrogen, for instance, in the deuterium, that could be superconductivity of electrons and superfluidity for deuterons, or even combination of superconductor and superfluid and magnetic field. So it's very interesting fundamental physical phenomenon could be. So, but let me start what is experimentally, what is status here now. So first of all, let me remind you that hydrogen is very compressible. So you see here equation of states of hydrogen. So at 5 megabar, it will be compressed around 16 times. So volume dramatically reduced. And therefore, of course, you can expect that molecules of hydrogen should interact each other and something will happen. And more particular, what in compression and temperature, what is happening is the so-called phase diagram of hydrogen, which is complicated and even much more complicated than here. And but in simplified way, what we see here in this very large domain of high pressure and high temperature, it's metallic liquid. And it's more or less well established with shock waves and other experiments. I think it's possible. It's established. And theoretical also. What we are interested in fact, low temperature range, because even here metallic liquid, it's very difficult to prove that this is even metal, because the definition of metal, that metal conduct electricity to the lowest temperatures. And of course, here it's impossible to fulfill this condition. So we should work in low temperature range. And of course, this is a range also for superconductivity and all other phenomena. And here, this range I show here enlarged. So mostly we will concentrate here also different phases. We'll concentrate only on this phase 3, which is stable in wide pressure range from 150 to most likely to 500. And we will see what we see on this way when we pressurize in approximately 100 kelvins. And also important is that we do electrical measurements, because only electrical measurements basically will give proof that we have metal and ultimately superconductor. And so this I will just highlight our experiment. So here it's everything of course very small, because pressure should be very high. So it's approximately diameter 20 micrometers. Inside this, it's sample of hydrogen, which is transparent at this pressure. And with pressure, it becomes non-transparent black. And here at the highest pressure, you see also black hydrogen not reflected in this case. And also here darkening, this is because diamond at this pressure start to dark, red, and really suffer a lot, and finally breaks. And so, and the measurements. Here another story, because this is really difficult measurements, and therefore progress is very slow. And what is important also for study of metallic hydrogen and prove it, because there are, I would say, many claims of metallic hydrogen, but typically it's one experiment, one claim, and then forgotten. So no, never repeated, never reproduce it, and so on. And it's very typical. So therefore, for study of metallic hydrogen is very important reproducibility. And in this respect, here we have reproducibility, but amazingly slow, because we started for first experiment was 2016, then and so on. So it's 6 years work, and we have only three published work. Slow pace. On the other hand, I'm really glad that we reproduce it. For instance, here in very first experiment, what was that? When we cool hydrogen, approximately this way, when we cool in this direction, what happened? We started in phase 5 with most likely semiconducting, and then resistance suddenly drops when we go through this boundary and go through phase 3. And in phase 3, when we cool down, it's some strange behavior. It's not semiconductor, not metal. So that time, even in title, we put semi-metal, but still it's only one experiment, not enough. And later we reproduce it. So we saw transformation from semiconducting behavior to semi-metallic behavior, but here we didn't go above 200 Kelvin. Simply we're afraid to go in this phase, because in this phase hydrogen is atomic-like, and therefore we're simply afraid to break diamonds. But here, last time we did it. So what we found here, you see black curve, it's very similar to this one. And in fact, we have much more, around 10 curves at higher pressures. But here, I want to highlight that we have also semiconducting behavior and here insulating behavior. So we see definitely transformation from insulator to semi-metallic state. It happens around 3010, 3020 GPa only. I would say, well, of course, it's very high pressure, but it's nobody expect. I would say that, in fact, expected. I will tell you in more details. But finally, what we have these green points on the phase diagram. So we have below we have conductive and semi-metallic hydrogen. Essentially, semi-metal, of course, metal, because metal is overlap of band gaps. Gap is metal, and with pressure, this semi-metal becomes more and better metal. And also, not only electrical measurements, but we have done optical measurements. In our case, Raman measurements, and Raman measuring to very high pressure. 275 GPa, and here's indications that we really were at this pressure, because diamond edge indicates us this pressure. What happened here? First of all, vibron shifts and vibron weaken at high pressures. This phonon spectra also increases, but they dramatically decrease. And if we will plot intensity of vibron and phonon, so it looks like very peculiar. So above approximately 310 or 20 GPa, intensity drops dramatically. And if we put here our data on electrical measurements, here values of electrical measurements. So it's quite good correlate electrical and optical measurements here. Also, please keep in mind here drops here, and eventually it still we have at high pressure here some signal, but above approximately 440 GPa is go to 0 to 50 to 0. So something next happening likely. And what tell us theory about this? First of all, no wonder that it could be semiconducting behavior. In fact, most theoretical works show that first it should be band closure, indirect band closure. So it's semi-metallic behavior. So here, for instance, blue mark shows that it should be in this range, this closure. And direct closure should be at much, essentially higher pressures. And you see here, by the way, also calculation which helps to understand this. For instance, in here at 4 GPa, according to calculations, so here already indirect gap closed, but still direct gap, it's still open. And here, nice paper which shows again the same. So it shows that so insulator and conductor in this calculation should be 330 to 350 GPa higher pressures that were observed, but still comparable. And also it's another thing that it's also question. So if we have conductive, so immediately we should have don't have Raman, but it's not so because indirect gap, it means that optical absorption could be low, and therefore Raman is possible only when direct gap closes. Absorption is high and Raman is impossible. So it shows that what we should see about hydrogen, it should be transparent. After that, it should be black, and only after above 5 megabars should be shiny when it goes to atomic state. So once again, we will show current phase diagram. So it started about 300 GPa to in semi-metallic state, and then something happened here, and here still it's not established, but our black data here enlarged. Our black data, remember I told you that they disappeared in this pressure range. What I should tell that it's another point of disagreement between groups and theory is pressure scale, because unfortunately at very high pressures, pressure scale is really not very well established, and therefore we should compare experimental runs in the same condition, in this case with diamond-angle cell. And then in this case, if we compare correctly, so infrared Raman from Lubera et al. And our data reasonably coincide, so it indicates that here likely something happened. So maybe this another metallic transition, and maybe in good metal, but also should be electrical measurements in this pressure range to prove it. So one why I told about metallic hydrogen, just to maybe feel that it's so difficult, really difficult experiment. So Ashcroft, unfortunately, he passed away from left us. So he was very close to experiment, and he understood that this experiment is difficult. So he proposed another thing. So instead of pure hydrogen, let's do with hydrogen dominant material, like this, for instance, a lot of hydrogen. And he put argument that it's should be high temperature superconductor, very similar to pure hydrogen. And he was right. But not, this was just general conclusion, general suggestion. In fact, it did not help much to find real good material. But fortunately for our field, at the same time, it was area of crystal structure predictions. And also fortunately for our field for high pressure, these guys who predict structure, in fact, they are not pressure. They did not work in pressure. Still, for me, it's wonder why they turn attention to high pressure. I think maybe answer is very simple, because high pressure gives really a lot of flexibility. So as soon as they predict some structure, then at high pressure it can change, go to some different structures, and these things can be checked with calculations. Let the opposite imagine that they predicted something at ambient pressure, something magnesium borate, something like magnesium borate. First of all, somebody should synthesize it, then check it. And this is really long way. It's not, but here with high pressure, I think it's very good field for application of crystal structure predictions. And so they predicted a lot. And even predicted 200 Kelvin a long time ago, by the way. And experiment did not show anything. So, but finally showed. And basically, it's the sad thing. So not only general prediction, particular calculation, but of course, experiment should be good. We should be ready for this adventure. And we are ready. And by the way, synthesis of sample at high pressure is relatively simple. For instance, here, of course, it's recent experiment. Now it's much easier, everything. Before it was much more difficult, but essentially it's easy. So if we put piece of sulfur in hydrogen on here, deuterium, and heat it with laser, sulfur will react and form hydride. And finally, it forms D3S. It can form about X-ray diffraction. And it was done in diamond anvil cell with for electrical leads deposited, typical deposit on envelopes. And a little bit more about experiment, which could be quite sophisticated if we will do it. If we go to very high pressures, around 5 megabar, of course less a little bit, it's sometimes more. So we also should put electrical leads, and difference distance between electrical leads should be only a few micrometers. So we can do it with focus ion beam. A quite sophisticated device, very expensive, and so on. But preparation of animals, we also do it by ourselves. And we are doing like 500 years ago with cast disc, this typical way. So this combination with very old technique and very modern technique, and much more in between. And electrical measurements, again, you see electrical leads. Here also we mark 1, 2, 3, just to know which electron go to the sample, which is black here, and it is surrounded with hydrogen. And we measure with van der Pol. So if, for instance, here current and here voltage, and we can do it here also current voltage. In fact, it's important to probe sample in different direction, because very often in one direction we have good superconductive step, in another not as good, but also at the same temperature. And also could be some weird resistance dependence on temperature dependence of resistance, like even here. So this van der Pol probe helps to understand what we are measuring. And so finally, we after some attempts, I skip it, we found superconductivity in hydrogen sulfide. Why hydrogen sulfide it was predicted not very high critical temperature, 70 Kelvin, but again, that time it was also huge temperature. Simply it was available, and we, in fact, it's nasty and so on, but it's possible to experiment. And we have done this with Alex Drozdov, this experiment. His thesis. And what we observe in one experiment, we observe superconductivity, pretty low temperature, but it increases to pretty high critical temperature, like 150 Kelvin. And you see here this dependence. So these black points like this. And these black points were in accordance with predictions of theory with orange stars. But most interesting happened here. So critical temperature went to already not predicted region to 150 kelvins. And so it's much higher than sulfur, for instance, which you also measured. So what is this? So we found, first of all, we found that its sample should be annealed. Unfortunately for us, annealing for room temperature is enough, and so we have reproducible step around 200 kelvins. And after that, we did a lot of measurements, systematic measurements, and one of the most important, the isotope effect. So when we change from hydrogen to deuterium, so critical temperature change lowered a lot, as should be for BCS superconductors. You see, for comparisons, this is historical plot for mercury. So this isotope effect, of course, much low. So in our case, we also measure carefully pressure dependence of isotope effect. Another thing that it's also theory, where it helped a lot for, in our case, appearance of this work. Which in this work, in fact, they considered, of course, independently, by the way. We didn't know about their work, and I did, of course, they also didn't know about our work. So they model this system, not H2S, but class rate. So, and it's stoichiometry is H3S. So they consider molecules of H2S and how it behaves with pressure. And so finally, they built very simple, beautiful structure where sulfur here and hydrogen is in between. Here, for instance, hydrogen is in between sulfur atoms. So it's very simple. What is striking, most striking even, that they predicted critical temperature was the same as we observed, very simple. Later on, it was clear that it was conservation of rather big errors. But anyway, so it immediately, theoretician immediately believed that this structure is responsible for superconductivity. I should mention also that fortunately we didn't know about this work. Otherwise, maybe we will never discover this superconductor because simply because for kinetical reasons. Because still we could not create superconductor at low temperature starting from this compound. So it should be heated. And yeah, of course, we have done a lot of experiments. I will show just a few of them. One of them, it's a study in strong magnetic field, and we have done it in strongest available magnetic field, static and pulse magnetic field. And what we found that we could not suppress superconductivity because critical temperature is around 100. Critical field 100 Tesla. But we reliably estimated this critical field. So it's around 100 Tesla. And it gives us immediately coherence length. Also, we have done a lot on structure. We always do structure afterwards. And this is an important experiment. It was done in spring 8. with our sample, we found that in this black spectrum, we found that so it consists with, first of all, blue is AM3M theoretical predictions, this cubic structure, and also very important, it's also sulfur. As we guessed, in fact, that sulfur should be, because H2S will transform to H3S and should be plus sulfur, and we observe sulfur here. And afterwards, we have done, of course, much better crystal structure, beautiful structure, which conforms this cubic structure. And another milestone was, first of all, I should tell that sometimes what happens, like in case of magnesium borate, it was great discovery and great expectations that it will be found something with higher critical temperature, but nothing happened. Everything just lower critical temperature, and this happens many times. Fortunately, in our case, it's not so, because we found superconductivity in lanthanum hydride, and it's much higher critical temperature, it's 250 kelvins. And another important thing that instead of this cubic structure, we have another structure, it's so-called glass-ride structure. So we found different family, in fact, superconductor. In fact, this most recently discovered superconductors are this type of superconductor. And another thing that what you see just visual, you see metallic hydrogen. And metallic hydrogen, because a lot of hydrogen and only few, relatively few lanthanum. So it's some kind of model of metallic hydrogen. And so no wonder if finally metallic hydrogen will be high temperature superconductor. And the next try was room temperature, because still even to find higher critical temperature. And it was predicted in yttrium H10. But unfortunately, we didn't find yttrium H10, most likely it's metastate. But even for yttrium H9, theoretical predictions predicted higher critical temperature, but it also didn't happen. So of course, calculation not always as good as you can expect. But here is some experimental demonstration. I think it's impressive. So what happened with metal, which when hydrogen goes inside? So starting from pure yttrium, so volume here, volume increases in pressure here. So volume increases dramatically. So you see H10, so its volume changes nearly 3 times expand. So sample expanded a lot. And also another demonstration here. What you see here is this X-ray diffraction in very challenging condition, 200 GPa and 2000 kelvins. And this condition we can measure crystal structure. I think it's amazing. But unfortunately, we did not measure what we expected, yttrium H10, even in these conditions. But what we found, critical temperature behave like this. It's quite typical dome. And next big part of my talk, it's magnetic measurements, because to prove superconductivity should be magnetic measurement, Meissner effect. And what you see here, first of all, coin, which is of course small things like 1 centimeter or less. So, and here diamond angle cell diameter only less than 9 millimeters. It should be this diameter because we wanted to place it in squid magnetometer. So idea is the following. So if we will create sample here, put it in desirable pressure, and put this device in squid magnetometer and measure directly magnetic moment and directly prove that this is superconductor. So this is extremely simple cell. You see all parts, and it goes beyond 2 megabars. And also it's very useful for pulse measurements, it turned out. So pulse magnetic measurements were done up to 65 Tesla. It could be more if pulse field more. So measurements. Our sample, in this case, is pretty large, 100 micrometers. And fortunately, even disk of superconductor expel magnetic field, so we should observe magnetic moment. And we really observe it. So we have observed this step in zero field cooling. And in field cooling, we did not see step, and in this particular run, we did not see any step. But it's possible that if superconductor of second type superconductor with strong pinion, it's very well known, and good consistent with electrical measurements. And we have done not only temperature dependence, also dependence on magnetic fields. This hysteresis started from here, from this virtual curve. But this we did not publish, but it was done a little bit later. What we publish here is that these measurements with temperature also, this magnetic response disappears approaching to critical temperature. And we very roughly estimate here first critical field. What happened now, but we didn't do anything. In fact, we did. We did a lot of efforts, but unfortunately we could not measure. And
Mikhail, you have 5 minutes.
I hope I will finish. Yes, thanks. And yeah, so and here, what happens now? We can do much better experiment, much easier experiment with Borate, not pure hydrogen, but Borate. And in this case, we have starting cell like this, but measure this black curve, then heat it, and we have superconductor. Measure once again, and so we have pure difference, black and red, and difference give this blue signal. The same for H3S, lanthanum by H3S. So we have beautiful steps, and even. And what we managed to in this case definitely manage first critical field, and finally we know what kind of superconductors we have, because we calculated London penetration depth and coherence length and Ginzburg-Landau parameter. So Ginzburg-Kappa tell us that we have with superconductor, 2 times superconductor with moderate type superconductor. Not this value, not very high. What also we can interesting to compare with other high temperature superconductors. What we found the only difference here in penetration depths. No, we have smaller penetration depths than high temperature superconductor. Coherence length approximately is the same. So the only difference, basically, we have just normal BCA superconductor. Uemura plot, I will not stop here. In Uemura plot, we are in the field unconventional superconductivity, but maybe it means not much, just means that coherence length here is small. Just few words of just conclusions that we have. No, this is not full list of experimental and also some reviews. And once again, we have 2 types, H3S and lanthanum hydrate. By the way, most likely covalent bonds are very important for high temperature superconductivity. In this case, they are very clear, bonding between sulfur and hydrogen. Here, less clear, this mostly ionic bonds, but covalent bonding between hydrogen atoms, but still there is some covalent bonding between hydrogen network and here lanthanum. So this is a picture. And now since things go to ternary for calculations, well, it's very difficult, in fact, for them. It's much more difficult than binary. But still in binary also there are some predictions. like here, very recent predictions, critical temperature more than room temperature in cesium and a lot of hydrogen here, pretty high pressure. And even higher critical temperature was predicted internally, 200 Celsius, some hot superconductivity. Few words about room temperatures, claims of room temperature superconductivity, everybody knows, simply everybody. Okay, so let me comment. First, about sharp transition in magnetic field. So some people, Hirsch and Marvin Cohen, noticed that it should be broadening in magnetic field, and we should see it. But unfortunately, here what we see here some broadening with magnetic field related. So here Diaz work, and here our works in H3S and so on. And just comment that it was published here, but incorrectly, because they pick up broad transitions and claim after that we also observe no broadening. Of course, it's not so, because they observe this, but in fact, our below this, so this is really not good paper. And finally, from this experimental, we did not confirm Diaz work because our points here stars and here, so it's below claimed high temperature superconductivity. We still did not publish it, but this the most essential point here. What is published was theoretical work from different groups, quite serious groups, by the way. And also they could not find high critical temperature in this system. So we should wait more until also other people confirm it. But since now shifting to not room high temperature and higher temperature, it's very interesting, of course, but more important, lower temperatures and ambient pressures. And here some progress is in calculations, for instance, in here like this temperature or 3 GPa, or even pretty high critical temperature. So things are going. And very final plot here, it's ambient pressure. So from ambient pressure, essential points the following. So we talk about hydrogen, which give high Debye temperature, but in fact, diamond also gives similar, very close to hydrogen Debye temperature, and therefore, high critical temperature could be in carbon-based materials. And here, some calculations show that in this case, it was pretty high critical temperature at ambient condition, and also experiment shows pretty high critical temperature in pure carbon doped with boron. And finally, many thanks for my group and for you for your attention. Many thanks. Bye.
Okay, thank you, Mikhail, for a nice talk. This is a chance for one or two questions. So there is already a question from Dr. Ashok Mani. Mikhail, so he's asking, can higher TC be obtained by having ternary or quaternary hydrides like cuprates and iron-based systems?
So I'm very sorry. Can you repeat? I don't
Can higher TC be obtained by having ternary or quaternary hydrides, like systems like cuprates and iron-based systems?
So I don't understand. So you think you ask why it's higher critical temperature than in iron superconductors?
Yeah.
No?
Hello? Is there a question, Dr. Ashok Mani?
Still, I don't understand questions. I'm very sorry. So.
Is there any other question for anybody?
First of all, let me welcome Professor Eramet once again after 3 months gap. He came to my international conference in October end, and my question has been, you had lithium magnesium iodide system, the ternary systems, can they show ITC at a still lower pressure?
No, that's of course it's not for me a question. A question of first of all, principally from BCS theory, it's, of course, it's for everything is possible, because for it's no fundamental bounds. Question is particular. So, is it possible to calculate, to model, to predict this system? No, for calculate for people who do calculation is quite difficult. It's just question of time, I believe, and they believe also. Question of time to deal with more and more complex system. And yeah, and finally maybe they will be able even model cuprates, but now it's unimaginable.
Okay. You mentioned about his article, his paper. You also, we have been together, his and yourself, 3 months back. And what I want to know is, he is opposing the BCS theory. And one problem is, because you are a co-author with many people both in the theoretical experiment side, and invariably in all the superride drives, now the Coulomb pseudopotential, which according to Macmillan or BCS should be around 0.1 to 0.13, but it is used as a variable and people go up to 0.4. Any comment to get the observed experimental value? They vary the Coulomb pseudopotential as a variable parameter. They go up to 0.4. Do you have any comment?
No, of course not. No, I'm not able to comment really on this. No, I think it's a question for theoreticians.
Yeah, okay.
For me, it would be interesting to check all these possibilities experimentally, what could be a difference or not. I think it's much more interesting.
Any comment from you on the room temperature superconductor, carbon, sulfur, hydrogen, and was it could it be repeated or reproduced, or is there a problem?
Because it's a big problem. We could not reproduce. Other people, as I know, also cannot experimentalists also cannot reproduce. And also another thing that already 2 years they also did not show this room temperature superconductivity again. So how it's possible? For me, it's difficult to understand. Theory does not support, except of some few small papers which are not reliable.
Anyway, I'm very glad to hear you after 3 months gap. And thank you, Professor Ramesh. And thank you.
Okay, let us thank Professor Ramesh again, and let us conclude the talk and over to the organizers.
Ciao, Gautam. Good to see you. Bye.
Yeah.
Good to see you. Very happy to have seen you.
Professor Yaramets, on behalf of the organizers, we are pleased to present this memento to you.
Okay.
Yeah, it will be mailed to you, sir.
Okay, nice. Okay.
Yeah, in absentia.
Yeah.
Okay, good.
Okay.
Okay.
Okay, so let us conclude. I thank again Professor Ramesh and I conclude the plenary talk. And I think now
it's time for oral presentations. The first presentation session, oral presentation is by Dr. Soumi Chakravarti. He is working in Condensed Matter Physics Division, Indira Gandhi Center for Atomic Research, and title of her talk is Pressure Induced by Variations of Medium Range Order in B2O3 glasses. So over to Dr. Soumi.
Dr. Gurpreet. So the topic of today's presentation from me is pressure-induced variations of medium-range order in modified borate B2O3 glasses. And my collaborators for this work are Dr. V. Shivasubramaniam, Sri Manavendra N. Singh, Dr. Anuj Upadhyay, Dr. Anil K. Sinha, and Dr. T. R. Ravindran. So to start with, I will introduce the structure of glasses. Glassy systems have broadly classified two length scales of ordering. The first is the short range order, which arises due to the nearest neighbor atomic polyhedral, here as shown for the glassy SiO2, where the atomic polyhedral remains constant and preserved as in the crystalline quartz, that is also crystalline SiO2. But in glasses, there is a next higher level of structural organization beyond the short range order, which is known as the medium range order. So here in this schematic, I have shown the medium range order in a typical network glass. It can be the connectivity between the network formers, that is the black dots, or it can be correlations between the network former, cations of the network former and the network modifier, or it can be the correlations between the network modifiers themselves. So the short range order falls in the length scale of around 2 to 3 angstrom, whereas the medium range order falls in the length scale of about 3 to 20 angstroms. Yeah, taken. So coming to the evidences of the medium range order, which we obtain from inelastic scattering experiments, be it neutron or light scattering experiments like Raman. There appears an enhancement in the vibrational density of states, and a boson peak appears in the low frequency region in the Raman spectra. This relates to the medium range order in glasses. Similar to this, there is signature in the diffraction experiments, which we observe in XRD or neutron diffraction experiments, and there appears a peak in the low Q, which has been correlated to the medium range order in glasses. So this peak is called as the pre-peak or the first sharp diffraction peak, abbreviated as FSDP in glasses, and it corresponds to the void periodicity in the network. So for analysis purpose, this FSDP is separated from the rest of the scattering function, and it leads to oscillations in the real space. So I will define two important parameters here. First is the coherence length, which is obtained from the width of this FSDP, and the next is the periodicity, which is obtained from the position of this FSDP. So coming to this work, in this work I have carried out work on the borate glasses B2O3 glass. So first I will talk about the pure B2O3 glass structure in this schematic. So B2O3 glass is a network of planar BO3 triangles, some of which group together to form hexagonal B3O6 ring-like structures, which are called as boroxols. So these boroxols are responsible for the medium range order in borate glasses. Now, what happens when we introduce a modifier cation into the borate glass structure? This 3-coordinated boron gets transformed into 4-coordinated boron. So this 4-coordinated boron gives rise to a lot of superstructures which are found in borate glasses. So these superstructures are then responsible in the modified borate glass for the medium range order. So borate glasses are extensively studied for their non-monotonic variation of properties as seen here when we increase the molar concentration of the metallic cation, metallic oxide. So the B4 fraction increases, and there comes a peak around x is equal to 0.3 to 0.4, and this is called as the borate anomaly. So what happens to the medium range order in borate glasses under high pressure? It has been shown that the FSDP position increases as a function of pressure. This implies that the length scale relating to FSDP, which is inverse of Q, decreases. That means there is dissolution of the boroxol rings, and there is a lot of reorganization of the medium range order. Also, what happens in the short range structure under high pressure? It has been shown by previous literature that with increase of pressure, the 3-coordinated boron fraction drops down as a function of pressure. And people have shown that there are basically 3 densification regimes which are found in borate glasses. So the first regime is where the BO3 triangles are predominant, as shown here. But the medium range order alters with the dissolution of the boraxol rings. Now in the second densification regime, there we see a drop of this B3 fraction. So BO4 units replace the BO3, and dissolution of boraxol continues till around 15 GPa. And in the third regime, this coordination increase of boron increases until we find a predominantly tetrahedral glass, and this process gets completed around 22 GPa. But in the literature, there is people have not seen any transition in the FSDP region, which corresponds to the short range structural changes. So the present work is on the pressure dependence of FSDP in lead borate glasses. This work is important because in literature we find pressure dependence of MRO is available only for the unmodified borate glass, and since Pb2 plus is a highly polarizing cation, it is expected to show FSDP variation differently. And these borate glasses are synthesized using melt quench technique. The experimental details are as follows. We have carried out high pressure XRD measurements at beamline BL12 of Indus 2 synchrotron RR-CAT, and symmetric cell DSC was used for these measurements using pressure transmitting medium of methanol ethanol, and pressure marker was silver. So coming to the results, here in this plot which is taken from literature, I show the FSDP of pure B2O3 glass, which shows a peak at around Q of 1.61 angstrom inverse, and this corresponds to a length scale of 3.9 angstrom. But this is the FSDP region in our borate glasses, modified borate glasses. So we observe that there are 3 peaks, 2 below and 1 above the original FSDP of the pure B2O3 glass. So for the analysis of the FSDP region, we have used a 3 Gaussian fitting plot, and we observe that just addition of 20% PBO shrinks the original B2O3 voids to around 3.55 angstrom and creates 2 more extended range correlations which correspond to 5.7 and 7.85 angstrom. These values are for the x is equal to 0.2 glass. So next I have assigned these 3 peaks Q1, Q2 and Q3. Using this schematic, I show that Pb2 plus enters the cages in the network and displays the oxygen atoms on their boundaries. So this gives rise to strong diffraction at low Q, which is assigned to Q2. Then there are correlations between this lead-lead or boron-boron cations, and this lead to correlation peak Q1. And there are some cages left where Pb has not entered, and this shifts the Q of pure B2O3 to higher Q, and it leads to the peak Q3. So here I show the composition dependent medium range order changes in the borate glasses. So I have calculated the length scale corresponding to the position. We see that the length scale corresponding to L3 shows a linear decrease. This shows that more lead in the wider cage shrinks the smaller cages furthermore with addition of PBO. And we observe that the length scale corresponding to Q1 inflates, and it is similar to the borate anomaly. So this is because at low X, that is at low modifier concentration, the conversion of BO3 to BO4 takes place, which increases the length scale. And as we add more PBO into the structure, the coordination of PBO decreases from 6 to 4, which reduces the void dimensions again, and hence there is a drop in LQ. This is the pressure dependent plot for the FSDP, and here I have shown for x is equal to 0.3. We observe that just at the introduction of pressure itself, Q1 intensity quenches, and this result has been seen for all glasses with all X. This is because the larger correlations which correspond to this Q1 are easily destroyed as a function of pressure, and the fraction of Q1 exhibits a strong response to pressure. Then here I show the length scales obtained from Q1 and Q2 as a function of pressure for various x. So we observe that LQ1 and LQ2 vary very slightly with pressure, almost very slight decrease with pressure. This shows that extended range correlations which depict the Q1 and Q2, they do not respond much to pressure. Compression only slightly brings the cluster together. That we attribute to the presence of Pb2 plus in these clusters because of the steric hindrance by the lead cation. However, when we see the correlation length corresponding to Q3, we see that it decreases with pressure, and we also observe a two-slope behavior. So this two-slope behavior shows that there is a different compression mechanism corresponding to both these pressure ranges. And this also shows that the units initially come closer together very fast, and then there is a resistance. So this may correspond to the change in boron coordination from 3 to 4, that is from layered to three-dimensional borate structure. And such two densification regime has not been seen before in borate glasses. So we propose that changes in the MRO is medium range order is precursory for the local coordination changes under pressure. Here I have plotted the correlation length corresponding to Q3 obtained from the width of Q3. So here we see an inverse pressure dependence correspond than the previous one. Here from the position we saw that dimensions were reducing, but from the width correlation length we see that the coherence length is increasing as a function of pressure. So we have tried to explain it using a schematic that LQ signifies the voids in the structure. So these voids reduce as a function of pressure, whereas L delta Q is attributed to the correlations from the network units themselves, which show an increase of correlation length with pressure. So the voids shrink, but the medium range correlation lengths increase with pressure. So I will conclude with my observations that with increasing PBO in the structure, the void periodicity in borate glass first decreases to 3.55 and also generates extended range correlations Q1 and Q2, and LQ1 okay, LQ1 shows an inflation just like the borate anomaly, and we have observed a two-slope. We have observed a two densification regime for the Q3, and this may correspond to BO3 to BO4 conversion, and changes in medium range order may be precursory for the local coordination transitions under high pressure. We also see that the voids shrink, but the medium range order correlation lengths increase with pressure. Thank you.
So we can have one question.
Dr. Soumi, do you think there will be any change in your analysis by radiation effect?
Medium range order by doing ion irradiation or some
change in the medium range order by ion irradiation?
Yes, sir. Actually, irradiation may bring the transition pressures even closer. It may, because it will be similar to what the metallic cation does to the structure. The metallic cation first changes BO3 to BO4, and further when we add the metallic cation, it again degrades the structure. So again there is a BO4 to BO3 transition. So that transition can be brought closer if we irradiate the sample.
Is there any evidence of crystallization? Experimental evidence
crystallization at high pressure.
on irradiation. Okay, thank you.
Okay, I think let us move on to next. Thank the speaker and move to the next topic.
So next oral presentation is by Ms. Rajita R. from Indira Gandhi Center for Atomic Research, Kalpakam. Title of her talk is Pressure Dependent Phase Transformations in Heat Resistant Explosive BDNAPM. So over to Ms. Rajita. Rajita, can you hear us? Please unmute.
Okay.
Okay.
Good afternoon to all.
Yes, you can start your presentation.
Okay. My presentation is pressure dependent phase transformations on heat resistant explosive BDNAPM. Outline of the talk is first I will give a brief introduction to high energy materials and the explosive material BDNAPM. Then I will discuss about a pressure induced phase transformation study on BDNAPM using Raman spectroscopy and X-ray diffraction. Then summary of the talk. Coming to the introduction to energetic materials or high energy materials. High energy materials are one which suitably triggered or initiated by external stimuli will release a large amount of stored chemical energy. These high energy materials can be classified as explosive, propellants and pyrotechnics. Our focus is on explosive materials. Explosives are a substance which when initiated by external stimuli like heat, impact, shock and all will release a large amount of energy by way of very rapid self-sustaining exothermic decomposition reaction. Explosives can be classified as primary explosives and secondary explosives. Primary explosives are sensitive to external stimuli and that can be easily initiated by external stimuli like heat, impact, shock. The example for primary explosives are lead acid, mercury fulminate and all. But the secondary explosives are relatively insensitive. To detonate a secondary explosive, shock wave from primary explosive is required. Example for secondary explosives are TNT, nitroglycerin, RDX, HMX. Coming to the importance of study of phase transformations in explosives, as we know, phase transformation in solid is a fundamental subject that is directly related to material properties. In the case of explosives also, chemical reactivity, thermal stability, crystal density, sensitivity and all depends upon its structure. So, it is necessary to map the phase diagram of explosive material at high pressure and temperature to evaluate their performance and safety aspects. Here, I have shown the phase diagram of RDX, a well-known explosive, and but even RDX is patented in 1898. Its PT phase diagram is not complete, and many of the well-known explosive is not reported the PT phase diagram. So it is necessary to study the phase pressure and temperature dependent phase transformation on explosives also. We have investigated a pressure-dependent phase transformation on bis 4-amino 3,5-dinitropyrazole methane, BDNAPM, which is also known as UMX2. This is a new explosive material synthesized in 2016 by Fisher et al. This is the molecular structure of BDNAPM. It possesses higher heat resistance with a decomposition temperature of 310 degrees Celsius. This heat resistant explosives can be used in perforating guns and also in space operating systems. Here I tabulated the properties like detonation properties like detonation velocity, detonation pressure, and then impact sensitivity, friction sensitivity values of BDNAPM, which I have compared with the well-known explosive HNS, RDX, HMX and all. Here we can see BDNAPM is having a higher impact sensitivity value. So it is insensitive compared to HNS, RDX, HMX and all. It is insensitive to impact. And also it possesses higher explosive power also. So that is the highlight of the material BDNAPM. In order to investigate a pressure-dependent phase transformation, I have used Raman spectroscopy. For carrying out experiment, our Renisho micro-Raman spectrometer is used, and 514.5 nanometer laser and 785 nanometer laser excitation also used. In order to pressurize the sample, symmetric diamond anvil cell is used, and Ruby is used as a pressure calibrant. Angle dispersive high pressure X-ray diffraction measurements were carried out at a beamline 11 of Indus 2 synchrotron. The wavelength of X-ray used was 0.789 angstrom, and for pressurizing the sample, Mauer-Bell type DAC is used. Gold is used as a pressure marker. In addition to experiment, we have done computation also. We have calculated vibrational frequencies of BD NAPM molecule using Gaussian software, and we got all positive vibrational frequencies, and visualized this vibrational modes using Avogadro software and assigned the modes. This is the simulated Raman spectra of BD NAPM molecule using Gaussian. We can see that these frequencies are matching well with the experiment. In addition to that, we have computed phonon frequencies of BD NAPM crystal using WASP. We got all positive frequencies and assigned the modes. Here I tabulated mode assignment for BD NAPM. Since BD NAPM is a molecular crystal, we can classify vibrational frequencies as external modes and internal modes. The frequencies in the range of 47 to 300 centimeter inverse is the external modes, and above that is the internal modes. Here we can see that computed frequencies are matching well with the experiment. Since BD-NAPM crystallizes in orthorhombic structure with a space group PBCA, and there are 8 molecules per unit cell, the irreducible representation for vibration can be written like this. And out of this, 93 Ag plus 93 B1G plus 93 B2G plus 93 B3G modes are Raman active. Experimentally, this is the ambient Raman spectra of BD-NAPM recorded using 14.5 nanometer laser. We got 42 Raman bands experimentally. In order to record high pressure Raman, we have used 785 nanometer laser. We have done pressure dependent Raman measurements up to 15.8 GPa. This is the external mode region. Here we can see the 57 centimeter inverse translation mode started appearing clearly from 1.1 GPa onwards due to higher pressure dependence of 8.4 centimeter inverse per GPa. And above 3.3 GPa, we can see the appearance of new modes, appearance of new external modes here and here. In addition to that, in the internal mode region also, we can see changes. Around 300 centimeter inverse, 2 shoulders started appearing, and around 602 centimeter inverse, 1 mode is appearing, and the peak at 738 and 828 are started splitting above 3.3 GPa. In addition to that, these changes can be clearly seen in omega versus P plot. Here we can see the external mode. This is the libration mode, which shows a discontinuity above 3.3 GPa. Here one new peak is appearing. Many of the external mode are showing discontinuity. Coming to the internal mode region, we can see the appearance of new peak here, and here also we can see discontinuity in the omega versus P plot. This changes in the Raman modes with the pressure is indicating a possible phase transformation beginning at 3.3 GPa. Actually, this changes in the external and internal modes like splitting, discontinuity, and redshifting occurs for bands related to the movement of NH, CH, and NO, which is indicating the changes in the hydrogen bonds of NHO, CHO, and NH and hydrogen bonds, which leads to the reorientation and thereby phase transformation, which is beginning at 3.3 GPa. In order to corroborate this Raman result, we have done pressure-dependent XRD measurements. XRD measurements up to 17.8 GPa. This is the XRD pattern with pressure. We can see the changes in the pattern, like appearance of new peaks around 8.4 degree, and here also we can see new peaks, and disappearance of peaks are also observed. These changes in the XRD pattern indicates the possible structural phase transformation at 2.6 GPa. By fitting ambient orthorhombic structure with the space group PBCA and Z equal to 8, we got ambient lattice parameters A equal to 12.378 angstrom, B equal to 9.69 angstrom, and C equal to 22.130 angstrom. In order to do read-well refinement, we have used GSAS. Here we can see anisotropic compression of lattice parameters with pressure. We were able to fit ambient orthorhombic structure up to 2.6 GPa, and above 2.6 GPa, the structure is transforming to monoclinic structure with a space group P21 bar C. By fitting third order Birch-Munaghan equation of state, we got a bulk modulus value of 13 GPa for ambient phase, and for new phase we got 17 GPa, which is matching with many of the insensitive explosives which have a bulk modulus value below 20 GPa. Coming to the summary of the talk, we have calculated vibrational frequencies of molecule as well as for phonon frequencies of the crystal and assigned all the modes. Pressure dependent changes in the Raman spectra, like appearance of new external modes and internal modes, indicate a possible structural phase transformation above 3.3 GPa. Our pressure dependent XRD result supports our Raman results, and we got a structural phase transformation from ambient orthorhombic structure to monoclinic structure with space group P21 bar N above 2.6 GPa. Thank you.
It's very nice that the speakers finished it within time. So a couple of questions maybe. So any question for anybody?
Sir Gautama.
Yeah. So if no, there is no question. Is there any question? If there are no question, I think let us thank the speaker and close the sixth session.
So
Yeah.
thank you, Professor G.D. Mukherjee, for chairing this session. I request convener ICREACH 2022, Professor N.V. Chandrasekhar, to present a memento to the chairman of this session.
Thank you, Professor Mukherjee.
Gautam sir, we are happy to share this memento for you, for all the services that you have done, sir.
Okay, thank you very much.
Thank you very much.
Yeah, thank you.
With this, we conclude the technical session 6. Because we are running short on time, so we are going for next session. We'll break.
4:30 only it is expected to start. Already 4:35. Okay.
Can start, Gurpreet.
Welcome to technical session 7. This session has 2 invited talks followed by 4 oral presentations, 17 to 20, and 6 flash presentations, 12, 14, 17 to 22. The first invited talk in this session is by Professor Malcolm McMahon. He is Professor of High Pressure Physics at the University of Edinburgh, UK. His area of expertise is high pressure structural physics using static and dynamic compression. Professor Malcolm is a fellow of the Institute of Physics and also a fellow of the Royal Society of Edinburgh. He has got many awards in recognition of his work, including Humboldt Research Award, William Penny Fellowship, inaugural Louis Delbert Prize of Canadian Light Source, etc. The second invited talk in this session is by Dr. K.A. Irshad. Dr. Irshad is beamline scientist, high pressure diffraction beamline, Express Elettra Synchrotron Trieste, Italy. His area of research is structural phase transitions at high pressure and high temperatures and high pressure instrumentation. He has received Homi Bhabha Medal for the best thesis in physical sciences 2019, Indira Gandhi Center for Atomic Research, Kalpakkam. This session is going to be chaired by Professor K. Anant Shivan. Professor K. Anant Shivan is the Director Reprocessing Group, Indira Gandhi Center for Atomic Research. He also holds the position of President, Southern Regional Chapter, Indian Association for Nuclear Chemists and Allied Scientists. His area of research are fission reactor fuel preparation and thermodynamics, nanocrystalline nuclear ceramics, fast reactor fuel reprocessing, neutron absorber materials, matrices for nuclear waste immobilization. He is recipient of many awards and honors, including Homi Bhabha Science and Technology Award 2009, DI Group Achievement Award 2013, and Development of Technology for the Production of Enriched Elemental Boron. Professor H.J. Arnikar Best Thesis Award 2003, Best Colloquium Award 1997 and 2001, Radiochemistry Excellence Promotion Trust. I invite Professor K. Anant Shivan to chair this technical session.
Good afternoon. Probably, I don't know, it must be mid-morning there for you in Germany. And welcome, Professor Malcolm McMahon. And it's been enough an introduction. I'm Ananta Shivan here as they introduced me. And I welcome you to go ahead with your presentation, which will be for about 25 minutes, followed by a 5 minutes of question and answer session. Thank you very much.
Thank you very much, everybody. Good morning, yes, from a sunny Edinburgh here in Scotland. Thank you very much for the invitation to speak to you this morning. And I'm going to discuss some work we've been doing over the last few years on the lanthanide elements. This is a group of materials I've been interested in going back 20 years. And finally, over the last few years, we managed to solve some of the problems we had known were there for a long time. So here, the lanthanides being that group of elements at the bottom of the periodic table, because they have very similar electronic structures, undergo the same or very similar series of phase transitions with pressure, but the phase transition pressures change in a regular way. There are a few elements such as europium in the middle of that figure there and ytterbium at the right-hand end, because those are divalent rather than trivalent. Those tend to have a different structural behavior. But these materials at lower pressures go through a series of phase transitions through structures which only comprise different packings of hexagonal close packed layers. Then at higher pressures, they tend to go through a first order transition to the so-called collapsed phases, the HP3 and MC4 phases, and then onto the alpha uranium structure. And these have lower symmetry and they're not close packed. And the thing I'm going to focus on in this talk is the identity of this MC4 structure, which appears in many of the lanthanide elements at 100 GPa or so. So here is the MC4 structure. It was first seen in cerium back in the late 1970s by Zachariasen. It's a distortion of the FCC structure, and you get this very complicated diffraction pattern. This is a diffraction pattern from cerium we collected at the SRF with lots and lots of lines and lattice parameters here. And the key thing I just want to point out here is this beta angle, the monoclinic angle of about 113 degrees, but it's a very complicated pattern with this monoclinic structure. If we then go to the, all of these lanthanide elements have been studied, and here are the diffraction patterns from the reported MC4 phases of terbium and holmium. You see the beta angle is 105 degrees rather than 112, so different to the cerium. But the thing I want to point out is the peak identified by the arrow in both figures there. It's not very clear in terbium, but much clearer in holmium, and that's not predicted by the MC4 structure. There is no peak there in the MC4 structure, and we noticed that a while ago. If we go up to dysprosium and erbium, there it is again. It's this feature on the right shown by the arrow. Again, the feature shown on the right of this peak here. Beta angles again, 105, 106 degrees. Now, this is not a very small deviation from the predicted peak positions of the MC4 phase, but it still shouldn't be there. There is an additional weak peak on the right-hand side of that peak, which is not predicted by this MC4 structure. Gadolinium is one of the few that has a very nice weak belt fit. The problem with gadolinium is it was done in an argon pressure transmitting medium, and that peak, that shoulder that can't be explained, is somewhere in this mass of argon peaks here. So we can't see it, but you also notice the beta angle is very different to the beta angle in dysprosium, holmium, terbium, etc. So if we go back to the lower Z members, neodymium and samarium, well, supposed to be this MC4 structure again, but a very different beta angle again in neodymium, almost 120 degrees, whereas samarium's 112. But the key thing is, if I summarize here, we seem to be able to group a bunch of the lanthanides with 105 degrees. There's a few where it's not, 118 and 212 in cerium. So there's something not quite right, and we've got that extra peak to explain. And we collected some very, very good data at the SRF a good number of years ago now, and this is the thing that we were worrying about. It was this right-hand peak here. So this was done at quite low pressure, 64 GPa, in helium pressure transmitting medium, and this peak, which is just a kind of shoulder on the previous study of terbium, is now a peak well out on its own. And if you try and do a fit of the MC4 structure to our data, it just doesn't fit very well. It doesn't do too badly at low angles, but it certainly doesn't fit at high angles. And that's where we got to years ago. It was wrong, but we didn't know what the right answer was. And then a couple of years ago, we were playing one Friday afternoon, the last thing you do before you go home, having yet another go to solve this structure. And the answer just dropped out that afternoon, that what the structure of this phase is a big orthorhombic structure with 16 atoms per unit cell, with this rather unusual space group, FDDD. If you go and look in any database for the FDDD structure in elements, you'll find it in gallium. The other material you'll find it in is plutonium. So this is the orthorhombic structure of one of the phases of plutonium, but in that case it has 8 atoms rather than the 16 atoms we're seeing here. So it's isosymmetric with gamma plutonium, but doesn't have the same structure. It's got twice as many atoms. But you can see in OF16, this shoulder is beautifully accounted for, and it fits right across the pattern. And you can see the relationship between the MC4 and OF16 structures here. If I make this MC4 structure with 105 degrees and go up 1, 2, 3, 4 unit cells, I get back to where I was before. So it's this big superstructure of the MC4 structure with much higher symmetry and very different symmetry is the correct solution to these high pressure phases. Okay, so what happens if we go to neodymium and samarium? Well, the pattern's actually quite different to the ones we see in the other lanthanides. But my student Sarah noticed that if you look at this pattern, you can see there's 1, 2, 3, 1, 1, 2. So you've got 3 peaks, then a singlet, then a doublet in neodymium and samarium. And if you look at the work that's been done on the actinide americium at high pressures, you've got 1, 2, 3, 1, 1, 2. And this then is the gamma plutonium structure, the OF8 structure, seen in plutonium and also other actinides at higher pressures. So, we saw, well, this looks as if it's the OF8 structure, also seen in americium, curium, and californium. And it's also a superstructure of the MC4 phase, but you only need 2 unit cells this time. And this explains this much larger beta angle we saw when previously people had tried to fit neodymium and samarium with the MC4 structure. They got a very different beta angle because it actually has a different crystal structure, OF8 rather than OF16. So we went and had a look. So here's the Rietveld fit of OF8 to samarium. Here's the OF8 fit to neodymium. All these data were collected at the Petra synchrotron in Hamburg. We've also looked at yttrium, the rare earth metal, so not a lanthanide, but always reported to have very similar structural phases to the lanthanides. And yes, it does indeed have the OF16 phase. And this is the phase of yttrium that people are compressing to before they try and synthesize the yttrium hydride superconductors that Michael Erametz discussed earlier this morning. So let's have a look at these structures. So as I said, at lower pressures, HCP, DHCP, FCC, these are all stackings of hexagonal close packed layers, just different stackings, the type of thing we teach undergraduates in elementary crystal structure courses. These structures, OF8 and OF16, and also the HP3 structure, which has been seen in other high pressure phases of the lanthanides, it's still these HCP layers, but instead of each layer being above 3 atoms in the layer below or the layer above, they're displaced slightly. So it's got 2 nearest neighbors in the layer above and 2 in the layer below. So the total coordination is 10, 6 in the layer, 2 above and 2 below. And if you look at these structures, and this was the insight of my colleague Graham Ackland in Edinburgh, instead of looking at A, B, C, A, D stacking sequences, if you say, I'll call the layer 0 if it's the same as 3 layers above or below, and 1 if it's different to 3 layers above and below, then these are the 3 simplest structural stackings you can get: 0, 1, and 1, 0. Okay, so I just talk now a bit about equations of state. So I've seen that in several talks over the last couple of days. People fit Birch-Murnaghan, a Vinay equation of states. There's always been this problem that at extremely high compressions, these equations of state do not join on to Thomas Fermi electron gas type behavior. It's a well-known problem in these equations of state. And Wilfried Holzapfel looked at this a lot 20 plus years ago and came up with this APL, adapted polynomial of order L equation of state, which does naturally merge into Thomas Fermi behavior at extreme conditions. And the nice thing is you can integrate it and get out free energies and other parameters from it. And most of the time we would just fit this second order AP2 form, therefore having the usual parameters we would fit in a Vinay equation of state, V naught, K, K prime. But the nice thing is you can linearize this equation of state. We're using this equation here, and you get this beautiful behavior. This is from Agnes de Val's really good data on these elements. And the thing is that, you know, on simple materials like aluminium, copper, and platinum, it linearizes and extrapolates to 0, 0. This is the great thing about the AP, adapted polynomial equation of state. Not only that, you can look at deviations from this linear behavior. It's telling you something about how the material's behaving. So I'll leave this up here for you to read. But basically for simple materials such as these, when you do this linearization, you get linear compression data, which with curves or straight lines that are parallel to that expected for an ideal solid. So we call this simple behavior. Then we would get regular behavior where we get straight lines, but they're not parallel to this ideal solids curve here, dotted line shown here. And then we get the anomalous behavior, so such as the group 2 materials, where we see breaks, clear breaks in the linearized compressibility that's telling you that something odd is going on, probably because of electronic transitions in these materials. So if the gradient is positive here, that's telling you the material is more compressive than you would expect from its atomic number and its ambient volume. And then above a certain transition into phase 4 and 5 here in barium, you get this linear behavior, which if you extrapolate it, will extrapolate to the origin. And then it becomes a regular metal compressing as other regular metals do. So let's have a look at samarium. This is our compression curve up to above 220 GPa. And you see if you fit the lower pressure phases, then and extrapolate that samarium becomes a lot less compressible once it enters the HP3 phase. So you can't really fit this with a single second order equation of state like a Vinay or a Birch-Murnhen. And what's clear is when you plot this in this linearized form, here is the compression here, positive gradient, therefore more compressible than you would have thought. And as you go through the HP3 and then into this OF8 phase, samarium compresses like a regular metal. Whatever electronic transitions were going on at these higher pressures has stopped, and samarium is behaving like a standard metal once it gets into the OF8 phase. If we, did I jump metal? No, if we look at the yttrium I showed you earlier and I plot that, here's the yttrium data here, along with samarium and simple metals, copper, gold, platinum. Again, you can see this positive gradient, and then you get this straight line here, again, pointing towards the origin. The scale here is essentially, the X scale is logarithmic in pressure. So you need to go up to very high compressions in order to see this behavior in these materials. Whoops. And then go into neodymium. Again, very similar phase transition behavior to samarium. And again, I've scaled this of the Wigner-Zeitz ratio against the 5p ionic radius just so I can get samarium and neodymium on the same graph. But again, you see both neodymium and samarium are more compressible than we would expect at lower pressures because of this SD electron transfer that's known to occur in these elements at low pressures. But once they get into this OF8 phase and the alpha uranium OC4 phase, then both of them have a linear compressibility when plotted this way, and they extrapolate towards the origin, as you would expect of a normal metal. So I may have gone through that more quickly than I planned, but to summarize, cerium is the only lanthanide with the MC4 structure. Previously, it was thought to have been the first lanthanide determined to have the MC4 structure. And then there was a kind of, the systematics, I would have said, were built up by people comparing diffraction patterns. Well, that diffraction's the same as that one, and that one's the same as that one. Therefore, they all have the MC4 structure. And what got us onto thinking this wasn't correct was that weak shoulder, and then as we got better and better data, this clear peak that was at high angles, which simply could not be accounted for by the MC4 structure. So the MC4 structure in neodymium and samarium is OF8, orthorhombic, face-centered cubic, 8 atoms per unit cell, and is identical to the gamma plutonium structure at ambient conditions and the high pressure structures seen in americium, cubium, and californium at high pressures. The MC4 structure in gadolinium to technetium is OF16, not MC4, and this structure hadn't been seen in the elements before, but has an identical space group, FDDD, with gamma plutonium and the high pressure phases of neodymium and samarium. The OF16 structure is also seen in yttrium itself and is the phase of yttrium that people are compressing into, but before zapping it with a laser to make yttrium hydride superconductors. The HP3, OF8, and OF16 structures form this new family of 10 coordinated quasi-HCP structures. So you have these layers, but instead of one atom being above 3 atoms in the layer above, it's between 2 atoms in the layer above. So the coordination is 6 plus 2 plus 2. The compressibilities of all of these elements are anomalous at low pressures. They are more compressible than you would expect from their atomic number and their atomic volume at ambient conditions, almost certainly because of this S to D electron transfer that goes in. But once you get into the higher pressure phases of these materials, in particular the OF8, OF16, and OC4 structures, then they all compress as normal metals. And if you wanted to, you could extrapolate those compression curves to very, very high pressures. And the key thing is then that the structural systematics of the lanthanides and actinides are much closer than we had previously imagined because of this gamma plutonium structure that we're now seeing at high pressures in both the lanthanides and the actinides, and the fact that OF8 is a member of a family of structures which we see in the lanthanides and the actinides. So I think that was my last slide. Yes, it was. So I'd just like to thank all of my colleagues in Edinburgh who worked on this. I say this project goes back a good many years to people who have long left, who collected that original data on terbium, which we worked on for so many years. My computational colleagues at King's, and then the experimental facilities and the provider of our samples, Uli Schwarz in Germany, our funding, and all of this diffraction data was either collected at Petra in Hamburg or the ESRF. And with that, I'd like to thank you all for your attention, and thank you once again for inviting me to speak to you today.
Thank you, Professor McMahon, for taking to the time. And now the talk is open for discussion. If there are any questions from the chat box, probably respond as well. Open up the chat box, please. Yeah.
Your question was there.
Go ahead.
Dr. McMahon,
Yes.
this is Raju from ICREACH. I need to get one clarification from you. You said, most of the existing equation of state, they do not extrapolate to that, what do you call that, Thomas Fermi limit at extremely high pressure. I agree that if you were to believe that the system retains its metallicity, then at the P tending to infinity, it must mimic that Thomas Fermi form. But first of all, where is the compulsion to think that the system would retain its metallicity, and there is a perforce necessity to mimic that equation of state? For half an hour, we would terminate up to 100 GPa, 250 GPa, where we study the structure. And most of the equation of state, the relative accuracy borders the limit of our ability to differentiate delta V. I still, I have been studying this problem for quite some time, and I'm unable to digest this fact. Is it absolutely necessary that you should reproduce the Thomas Fermi form? For all practical purposes, you can retain with this finite strain equation of state.
Okay, what I thought was interesting, there was a paper from Livermore recently on, they had used NIF to ramp compress, I think it was copper, up to extremely high pressures, well above a terapascal. And if you take Agnes de Val's DAC data up to about a megabar, do this linearization, and then add on the NIF data, it is perfectly on the extrapolation of that data. In fact, one point wasn't on the line, and then I spotted there was a problem with it. So, it may be for many materials that that people aren't probing at pressures high enough to see these misfits between the equations of state. But I say one of the other nice things about this APL form that Holtzapfel developed is you can integrate it numerically and come out with internal energies, and therefore, via thermodynamics, a lot of other physical properties, fairly easily.
Thank you very much.
What is the bearing of the lanthanide contraction will be there, right? Lanthanide contraction, will it have a bearing on, should be having a bearing, apart from ytterbium, divalent ytterbium, other things should have a bearing on the structural transformation. It is equivalent to chemical pressure. Now in the middle of
Yes, I mean, the lanthanide contraction is there. Of course, the ones that stand out are europium and ytterbium, because they're more chemically, they're more like barium, or the group 2 elements. If you compare the compressibility of europium, it's remarkably, it's very compressible, and its compressibility and behavior, even its crystal structures are more like barium than the rest of the lanthanides.
Are they very different from what was written long back by Scriver? Scriver gives a structural sequence as a function of pressure for almost all the solids, way back some 20 years back. In what way your things are different from what Scriver gave?
I think I can't remember that reference offhand. I mean, could you email me that reference? It would be interesting to see. Remind myself.
Okay.
No, that would, or put it in the chat.
Write you and see you at Edinburgh, because I have been to your laboratory, and so I have come to Edinburgh. Okay, I'll meet you in person soon. Thank you.
Thank you.
Thank you.
Any other questions from the audience? There are no more questions. Once again, I thank Professor Mohan for this wonderful and interesting lecture. Thank you very much, Professor.
Okay, thank you very much.
And I'll finish this session with the formality. Probably this memento, which is I'm showing out here on the screen, presented to you. Maybe they'll mail it to you personally later.
Okay, thank you. I look forward to seeing it.
For the wonderful lecture.
Okay, thank you.
As we move on to the next lecture. So we have another invited lecture, probably by K. Irshad.
Hello.
Irshad.
Hello. Am I audible?
Yes, you are audible.
Okay.
I have a video.
I have shared it.
Oh, your video.
We are not able to see your video nor the PowerPoint presentation.
Excuse me 1 minute.
I'm seeing the PowerPoint presentation though. But we'd like to see your face if possible.
Okay. Yeah. Sure. Let me figure out. Is it? Yeah. Hello.
Yes, we can see.
Irshad, happy to see you.
Yeah. Yes, sir. I thank you. Thank for the organizers of this conference for providing this opportunity, and also I'm happy to see you, sir. And today I will be presenting some of the work which I have carried out at while I was in ICREACH. So the title of this talk will be.
Irshad, just I want to remind you, you have 25 minutes to make the presentation. After which we'll put 5 minutes for the question and answer session. Thank you. Please go ahead.
Sure. Thank you, sir. Thank you. So I'll be presenting some work on high pressure, high temperature structural studies that I have carried out on zeolite materials. So presently I'm working at high pressure diffraction beamline at Express, electrosynchrotron trace day. So the outline of my talk will be briefly, I will introduce the Express facilities which users can use for their user can get the beam time and use their facilities. And then I will introduce the zeolite, a brief introduction I will be providing. and the pressure effects on these zeolites materials, and zeolite A, and it's a high pressure, high temperature studies. Generally, these zeolite materials are having a vast variety of applications, but I focus on the nuclear perspective, where this zeolite A has been used as a host matrix for different nuclear waste host materials to load the nuclear waste host host. And okay, so this is the contributors to the present talk, and M. Mahima Kumar and Dr. N.R. Sanjay Kumar and Dr. Hidananda Chena, they are the contributors to this present talk. And presently I am at Express team at Electra. These are the team Electra team. And I would like to give a brief glance of these express facilities which can be used for high pressure, high temperature and low temperature studies. And this, what we have seen, what is shown here is the control room of express, from where you can control all the facilities which are in the express. So it's a mouse click away. And what is shown here is the low temperature heliocryostat, which can the experiments of diffraction experiments with 50 GPa and down to 20 Kelvin can be collected using this setup. This has been recently commissioned. And this is the Express experimental hutch, where we have the new Pilatus detector for high-speed counting. And now this facility is recently commissioned for doing high pressure and high temperature setup, which can do diffraction measurements at high pressure and high pressures of 50 GPa and temperatures of 1000 Kelvin. And we have also a Raman spectrometer, which we can use it for the measuring the Raman spectroscopy. And these are the different diamond anvil cells which we have in Express, and this is the recently commissioned HPHT Lotto membrane diamond anvil cell. And if you look at here, this has two different heater assemblies, one at the external heater and another one in the internal heater. And the external heater can be available for usually the users who brings their own DAC, and this can be the high temperature measurements can be possible at Express. And these two cells also we are using in Express. And we also have a cryoloader facility for loading cryogenic loading the gaseous medium in liquid form. Argon, nitrogen, oxygen, and methane and carbon dioxide, all these gases can be loaded using this facility. And I would like to give an announcement. These users are all welcome to discuss their proposals well in advance. So the next deadline, so that you can find out whether the experiment is feasible with Express beamline or not. And next deadline for this proposal submission is on March 15. And so now we'll come to the HPHT studies on zeolite materials, zeolite A. So zeolites are generally silicon SiO4 and AlO4 tetrahedral connected in a three-dimensional way, which makes a porous network in 3 dimensions. So which I have shown here a silicon tetrahedron and an aluminum tetrahedron here. They are connected through corners, and they can in the way they are connected through connected in 3 dimension can bring a different variety of zeolite frameworks. A total of 235 distinct zeolite framework types has been till now has been found out. And these if these two tetrahedras are connected in a square fashion, which are known as four-membered ring, on these corners the silicon or aluminum will sit. And if these two four-membered rings are connected in a cubical fashion, they are called as double four-membered ring. And also in the same fashion, if it is in the hexagonal form, this is known as the six-membered ring. And if these two six-membered rings are connected, they are known as the double six-membered ring. And if you see over here, if the beta cage so if the four-membered rings and six-membered rings, they are connected, if they are connected, they can form a beta cage. This contains 8 six-membered rings and 6 four-membered rings. And these beta cages, they are the secondary building blocks of these zeolite materials. And if you see the beta cage and the double four-membered rings, if they connected together, this zeolite A structure is formed, which is the generally LTA structure type. And this produces another large cage at the center of this and which is the alpha, known as the alpha cage. And on the other hand, if the beta cages are fused together, they can form a sodalite cage, and this is known as the sodalite without the double four-membered ring. And if these sodalite, when they form with they couple with the double six-membered ring, they can form a zeolite X or Y. They are the FAU, that is Faugesite structure type. Network structure. And these, according to this, their largest pore windows, these are the pore windows in these structures, and these according to the largest pore windows, they can be classified into small pore, which is less than 8 ring, and medium pore, which is 10 ring, and large pore around 12 rings, and extra large pore zeolites, which is greater than around 12 ring. And as I have shown here, the aluminum tetrahedron, which has a net negative charge, because of this net negative charge, the framework is has a full negative charge. So this can be compensated by extra framework monovalent or divalent cations. So the pressure effect on this zeolite A is studied in detail, which has been a pressure-induced amorphization. The zeolite materials shows a amorphization at sufficiently large pressures. And another important thing which we would like to discuss is the pressure-induced penetration of external molecules in these zeolite A materials. This was accidentally observed when Hazen et al. Has studied these zeolite A materials with different pressure transmitting mediums, water and alcohol. So in water medium, we do not see any discontinuity in the compressibility curve. However, in alcohol, when he studied, there are different discontinuities are observed. So he has qualitatively explained this because the water molecules are present. Water molecules directly enter into the pores of the structure, that makes the structure rigid, and the compression here is almost due to the compression of the tetrahedral. However, in the case of alcohol, there is no compression is the alcohol does not enter into the pores of the structure, and then so this compression here is due to the compression of the cages also. So this discontinuity is not because of the structural phase transition, because he has not seen any change in the symmetry. And later this has been proved through ritual structure refinement of the X-ray diffraction data, where you can see that at around a 0.37 GPa, the oxygen occupancy belonging to the water molecules has increased. So, and there are not much high pressure and high temperature studies are reported in these zeolite A materials. So one report which is I have seen is the carbon dioxide filled pure silica LTA zeolite. This pure silica LTA zeolite is the one which does not have aluminum content in this. And the high pressure studies on this material has shown that at around above 5 GPa, there is a cubic to rhombohedral displacive phase transition, and further increasing pressure does not show any phase transition, and also the amorphization was not seen in this material up to this highest pressure. And this was in contrast with the earlier observations where they have seen at 1.2 GPa and 3.2 GPa phase transitions are present. So the incorporation of the carbon dioxide in the pure silica LTA zeolite the phase transitions are also suppressed, and the amorphization also suppressed in this case. And further, this they have studied the different PT space for this material. They have compressed up to 6.8 GPa, well above the cubic to rhombohedral displacive transition, and then they have heated up to around 600 degrees centigrade, and the pressure was dropped into this around 1.3 GPa, where the rhombohedral structure has come back to came back to the structure. It has transformed to the chord structure, quasate structure, and then further treatment in the with the temperature, they have shown that it's transformed to the stishovite structure. And the framework density, and there is a relation, there is no structural, no correlation between the compressibility and framework density of this in this materials. The framework density is defined by the T by 1000, which is T is the aluminum or the silicon atom in this structure. So the applications, coming to the applications of the zeolite materials, there are plenty of other applications. However, they have also used as the material for radionuclide removal. Due to the cation exchange capacity, these zeolite materials have been certain selectivity to radionuclides like cesium and strontium and chromium. If you recollect the Fukushima and Chernobyl nuclear accidents, these materials, zeolite materials, has been extensively used to decontaminate the radioactive water and the soil. And also it has been found applications in the plants when the zeolite has been added to the soil, there is a decrease in the absorption of the cesium by plants. And so being this in mind, we have studied the zeolite A materials at high pressures and high temperatures. These are the materials which are the host metrics for nuclear waste. So the structure of this zeolite A has been already discussed. The beta cages are connected through a double four-membered ring, and this produces a large alpha cage here. And this center of this alpha cage act as a cation site, and the another cation site is the center of the six-membered ring. And these materials, these cations are exchanged with the cesium, radioactive cesium or strontium material, and this can, when these materials deposit on the deep borehole repositories, they can experience high temperatures and pressures. So there is a necessity to study these materials at high pressure and high temperature to understand the structural stability of this material. So this synthesis of zeolite A has been carried out from the kaolin in a two-step process, where the kaolin has been, which is a natural clay which has been used for synthesizing the zeolite A. So the kaolin has been treated at 500 degrees centigrade for 2 hours, which converted into amorphous metakaolin, and which can be which has been treated at different concentration of the alkali solutions, and we have under hydrothermal conditions, and we have seen that at 3 molar solution for 3 hours at 90 degree centigrade in hydrothermal conditions, we could get a reasonably good crystalline zeolite A. And the ion exchange reactions has been carried out with strontium and cesium chloride solutions, and we could see that we have obtained a phase pure materials of cesium and strontium loaded zeolites. And we have carried out high pressure and high temperature diffraction measurements using the diacyl Helios membrane DAC and the Genix HT XRD diffraction facility, which was available at IGCR. And this shows the structural studies at high pressures, which indicates that there are no structural phase. We have carried out high pressure diffraction measurements on all these pure zeolite and strontium zeolite and cesium loaded zeolites, and we see that there are no structural phase transition in any of these materials, which indicates that the structure is stable at least up to the 10 GPa of pressure, and above which the peaks were almost disappeared, and possibly there a pressure-induced amorphization is happening in these systems. The pressure-induced amorphization has been earlier studied by atomic pair distribution study, where I have shown here the structure of the zeolite A material and their cation sites. And these are the different double four-membered rings and their atomic pairs in the double four-membered ring, and the atomic pairs in the six-membered ring, and the atomic pairs in the eight-membered ring. And this is the atomic pair in the double four-membered ring. And this is the cation site in the six-membered ring, and their coordination with the different atom nearest neighbors. And the studies has been carried out. The sample has been recovered at 8 GPa and 2 GPa, and they have compared this pair distribution function at these different the samples which are recovered at different pressures. So the 8 GPa sample is completely amorphized, and it will not revert back to the crystalline material. And they have observed a few different differences in the peaks, which the first one is corresponds to the sodium, the cation site linked to the silicon site at the double four-membered ring, and the second peak, which is corresponds to the four-membered ring in the silicon oxygen distance in the four-membered ring, and the third peak is corresponds to the silicon distance in the corresponding to the in the double four-membered ring, and the fourth one is corresponds to the silicon distance in the double four-membered ring, and these peaks are found to be weakening with the amorphization, and which indicates that these mainly due to the weakening of these double four-membered ring. So we have also carried out, we have estimated the equation of state of these nuclear waste loaded zeolite materials. We have seen that higher compressibility for zeolite A compared to the cesium and strontium zeolite loaded zeolites. So this higher compressibility of zeolite A is due to the presence of these pores in the structure. When the cesium and strontium is loaded into the pores of the zeolite A, the structure becomes dense, which leading to the reduction in this compressibility. Further, we have studied this material at higher temperatures where we could not see any structural phase transition. However, we see a relative change in the intensity of these materials, a relative intensity of the 220 and 420 peak, and the relative intensity increases up to 300 degrees centigrade, and further it shows a reduction, further it saturates. And with our TGTTM measurement has shown that till 400 degrees centigrade, there is a reduction in the weight. There is a weight loss at till 400 degrees centigrade, and this is due to the loss of water molecules. Taking this into the consideration, we have carried out extensive ritual structure refinement on these high temperature data, and we could see that the difference in the intensity is due to the loss of structural water, which we have estimated from the occupancy of the oxygen atoms which belongs to the water. And so the observed changes in relative intensity are the indication of the temperature induced liberation of the water molecules from the zeolite structure. And we also carried out the thermal expansion measurements. So we have extracted the thermal expansion value, lattice parameter variation with the temperature, and we see three different regions. A non-monotonous behavior is observed. So a drastic reduction at around 100 degrees centigrade, and then further it increases to 300 degrees centigrade, and after that it shows a reduction in the lattice parameter. So the negative thermal expansion in this region is well known in these materials due to the rotation of these tetrahedral networks towards the 8-membered ring, and which will lead to the these silicon atoms to come closer together, and this leads to the negative thermal expansion at higher temperatures. However, this rotation is not favored when these cages are filled with water molecules, and this limits the rotation of this tetrahedral behavior, tetrahedras. So this reversal in thermal expansion behavior is due to the temperature-induced dehydration in this material. And further, we have studied this at higher pressures, and we could see that there is an amorphization at around complete amorphization at around 6.9 GPa in a non-hydrostatic condition, where we have studied also this in hydrostatic condition. We see it still peaks at around 10 GPa. So the complete amorphization in under a non-hydrostatic condition is advanced by a factor nearly 4 GPa. The non-hydrostatic is also evident in the compressibility curve, where we could see that the compression is higher in the non-hydrostatic region. And high temperature, we have also carried out high temperature structure studies at higher pressures at 1.3 GPa. We could see that there up to 250 degrees centigrade, there are no structural phase transition observed, but at around 300 degrees centigrade, we could see the complete disappearance of the peaks belong to the zeolite. Several of new peaks has been appeared. So this we have compared with the non-literature values, and we have found that these peaks belongs to the two different phases, soda sodalite and zeolite NaP1. So we see that at 300 degrees centigrade, this concomitant, the zeolite A concomitantly transforms to the sodalite and zeolite NaP structure. And the release of temperature, with the release of temperature, the structure was stable. And here I have shown the zeolite A and sodalite and ZnP structures, and we could see that the zeolite and sodalite has resemblance in structure, because once the D4 double 4-membered rings are not there, then it is the sodalite structure. So we have seen the infrared spectroscopy measurements has shown that the weakening of D4 are double 4-membered rings with respect to the pressure, which is leading to the amorphization of the material. So here we could see that at amorphization, we did not see any amorphization, but temperature might be favoring the transition from zeolite to sodalite gauge. However, there are no structural resemblance between the zeolite A and zeolite NaP structure. And we have characterized the high temperature phases with doing labile fitting has been carried out, and the structural parameters has been found out, determined. And also we have seen that positive thermal expansion behavior of zeolite A even at 1.3 GPa. And the interesting thing is that there is no difference in the thermal expansion coefficient at ambient pressure and at around 1.3 GPa. So the pressure has a marginal effect on this thermal expansion coefficient. And we have further carried out high temperature structural studies at around 2.7 GPa. The behavior was completely different at around 250 degrees centigrade. There is a complete amorphization has been seen. This is entirely different behavior from the one we have seen at 1.3 GPa, where we see a transition to sodalite and ZnP structure. And so we see, we conclude that there might be existing a threshold pressure above which the temperature drives the zeolite A to an amorphous structure. And here I have shown the pressure evolution of the high temperature phases, which we have obtained at 1.3 GPa and 300 degrees centigrade. We could not see any structural phase transition up to 5.9 GPa pressure. And these are the pressure evolution of the unit cell parameters and unit cell volume. And we have calculated the bulk modulus values for these two SOD phase and ZnP phases, and which is shown here. And we see that SOD is higher compressible compared to the ZnP structure. And we have compared these values with the non-literature values, and the SOD values, sodalite values are in more or less in a good agreement, whereas for ZnP we could not find any studies, compression studies in the literature. So we have compared with the Gismontaine structure, which is generally which shares the same framework structure as the ZnP structure. So these values are also in good agreement. And we have at 5.9 GPa, we have carried out a thermal cycling of this material, and we see several interesting phenomena here. At around up to 300 degrees centigrade, we could not see any structural changes in these two structures. However, at around 400 degrees centigrade, the zeolite ZnP has completely disappeared. Only the sodalite phases are only present. And even at when increased to 500 degrees centigrade, the sodalite peaks has also disappeared. However, there are some new reflections has appeared, but we could not determine which phase this is, and because the literature, we compared with the literature data, but we could not determine the structure type of this. So we suspect that there could be a novel phase has been formed, and we on reversal of pressure and temperature, this structure has been preserved. And we have carried out the thermal expansion behavior of the sodalite and the ZnP structure at 5.9 GPa is shown here. And we at 5.9 GPa, we see that the sodalite shows a negative thermal expansion behavior, which is completely in contrast with the thermal expansion behavior, which is shown at ambient pressure. So at ambient pressure, the sodalite shows a positive thermal expansion. So the pressure induces a negative thermal expansion in this soda-like kind of material. On the other hand, ZNP shows a positive thermal expansion along the C-axis. Okay.
Yeah.
Hello.
Wind it up quickly. Because
Yeah,
already
sure, sir. And positive thermal expansion along the C-axis and a negative thermal expansion along the E-axis. So this expansion along the C-axis is compensated by the compression along the A-axis in the ZNP structure that leads to almost no change in the unit cell volume. So finally, we have from our studies has been consolidated into a phase diagram for zeolite A. This the cubic structure of zeolite A has been shaded in the gray region, and other phases are marked here. So the transition to the carbonate phase at high pressure, high temperature, and atmospheric pressure has been hindered by the transition to an amorphous structure at high pressure or high pressure, high temperatures. So in summary, zeolite A and nuclear waste loaded zeolite A zeolite has been studied at high pressures and structural stabilities are compared. High pressure, high temperature studies on zeolite A indicated several phase transitions and amorphization at different pressures, temperature conditions. A pressure temperature phase diagram has been proposed for the zeolite A interval. And in acknowledgement, I acknowledge ICTP for the fellowship and Department of Science and Technology for this fellowship, and Indira Gandhi Center for Atomic Research for providing the access to the facilities.
Thank you, Mr. Rishabh. It was very interesting results, and now the talk is open for discussion. We can have a couple of questions. I have a question myself.
Yes.
Essentially, when you talk about the sodalite and the ZNP, the
Yes.
difference is only in the D4R. So
Yes.
essentially, you feel the sodalite is resistant to amorphization more as compared to ZNP. So essentially, if there's a way we can strengthen the D4R groups, then probably you can enhance the pressure resistance or the extent to which amorphization can be brought down. ZNP as well. What is your thought about it?
Probably, actually, this the structure of this has been stable at. It has been seen that the structure becomes stable when these cages are filled with some other host materials. So maybe
Essentially,
yeah.
Either you physically strengthen it or the bonding at the D4R has to be enhanced. So if you can synthesize a zeolite, ZNP material, which is having a stronger bonds at the D4R groups, then probably you've done it.
Okay, probably.
Do you have any thinking about it?
Okay, I haven't thought about the synthesis material, because this synthesis of this material has been carried out by Mahima Kumar. He was well experienced with that, so I have got this.
All right. Thermal cycling and but degradation of zeolites is well known. So what is new from your work? I mean, what are the new finding you made?
No, these materials, actually, the structural stability of this material has not been studied at higher pressures and temperatures. So the structure, when we load this material, sir?
These were the first results on this material. Good work.
Yes. That is, there are not plenty of works on the high pressure and high temperature studies are not carried out much on these zeolite works.
Yeah, Dr. Kamali wants to ask a question.
So, Isha, a very good work. I have a simple fundamental question. So, is it possible to retrieve the sample that you got a negative thermal expansion coefficient at 5.4 GPa?
Yes.
And the temperature dependent measurements has been done. So, whether we can, but is it a irreversible transition?
No, actually, after that, we have carried out other measurements on that sample. We haven't checked the reversibility of this material.
Okay.
So probably we have
please
seen
check
some
it.
new reflections in that material, and so that was retrievable.
Oh, okay.
And you know, its sample quantity was very less, so could not be carried out some other measurements on that.
Okay. So how the temperature dependent measurement has been done at 5.8 GPa?
Yeah, at 5.9 GPa, and then temperature rise. within the diamond anvil cell.
Within the diamond anvil cell. Okay, thank you, Isha.
Okay, sure. Thank you.
There are no more questions. Once again, thank you very much, Irshad, for presenting wonderful piece of work, and
Thank you, sir.
wish you well. And thank you very much for accepting the invitation. It's
Thank you,
my
sir.
honor to present you with this small memento, which will be sent to you separately.
Okay,
on
thank you,
behalf of
sir.
Calvin.
Thank you.
Thank you very much.
Thank you all for listening.
Thank you, sir. Now we have 4 oral presentations. The first one is by Ms. Gayatri V from IGCR Kalpakkam, and the title of her talk is High Pressure Studies on Pristine and Lead Substituted Bismuth Based High Temperature Superconductor. Gayatri. Going to talk on my work on high pressure studies on pristine and lead substituted Bi based high temperature superconductor. I'm Gayatri V, Senior Research Fellow working in Indira Gandhi Center for Atomic Research, Kalpakkam, India. I would like to acknowledge my collaborators, Dr. A.T. Satyanarayana, Dr. Balmukund Shukla, Dr. T. Geeta Kumari, Dr. N.R. Sanjay Kumar, and Dr. Avdesh Mani for their valuable contribution. Let me start the talk by introducing the sample. Bismuth-based high-temperature superconductor was discovered by Mehta et al. In 1988, and they are the first cuprate high-temperature superconductor we discovered which did not contain a rare earth element. They have a general formula of Bi2SR2Ca(n-1 CuNO2n plus 4, where N represents the number of copper oxide plane. They are generally called bisco. The typical crystal structure of bisco consists of a layered arrangement of crystallographic planes, where the charged reservoir layers comprising of bismuth oxide, strontium oxide layers sandwich the superconducting slab comprising of copper oxide, calcium, copper oxide planes. And here the superconductivity is due to the doping of holes in these copper oxide planes. Depending upon the number of copper oxide planes present in this superconducting slab, there are 3 members belonging to the family. For n equal to 1, that is, having one copper oxide plane in the superconducting slab, it is Bi2201 phase having a Tc of 20 Kelvin. For n equal to 2, it is Bi2212 phase having a Tc of 80 Kelvin. And for n equal to 3, it is Bi2223 phase having a Tc of 110 Kelvin. So clearly, Bi2223 is the highest Tc phase among the family. However, the greatest challenge in the synthesis of the sample is the coexistence of the 3 phases. Now let us see the motivation behind performing high pressure measurements on this sample. So achieving higher values of transition temperature in cuprate superconductors have always remained a great challenge. And there are literature reports that higher pressures can lead to increase in Tc due to increase in the density of state at the Fermi level by charge transfer between copper 3d and oxygen 2p bands. And for overdoped samples of bisco, with increasing pressure, the Tc is found to initially decrease, and further, very high pressures of nearly 20 GPa are required to observe a resurgence in Tc. As the distance between the charged reservoir layers and inner copper oxide decreases with increasing pressure, the doping level of inner copper oxide layer is found to increase. And higher pressures have also effectively induced carrier doping into multi-layered cuprate superconductors. Having motivated by these literature, we have synthesized pristine and lead substituted bisco with the starting composition Bi2SR2Ca2Cu3O10 and Bi1.75 Pb.25 SR2Ca2Cu3O10 using standard solid-state reaction method. The precursors used were oxides and carbonates. This is the temperature profile for synthesis. The precursors were first precalcinated at 800 degrees Celsius for 12 hours. The stoichiometric amounts of the precalcined powders were then ground together in agate mortar and pestle, and they were heat treated at 840 degrees Celsius for 24 hours. The calcined powder was then pelletized in a die and plunger using hydraulic press, and then they were heat treated at 840 degrees Celsius for 24 hours to increase the grain-to-grain contact. Further, it was quenched in liquid nitrogen. And this final step was repeated several times to obtain the sample of requisite property. Thus, we have 2 samples, Bisco 24 and lead substituted Bisco 30. Here, the bracket represents the phase fraction of the highest Tc, Bi223 phase, We have carried out high pressure temperature dependent electrical resistivity measurement on these samples using a home built Bridgman opposed annual high pressure lock cell in the pressure range of 0 to 8 GPa, the temperature range of 4.2 to 300 Kelvin, and steatite was used as a pressure transmitting medium, and gaskets were made up of pyrophyllite washers. The sample assembly area was provided by the 4 mm flat face of two opposed anvils made up of tungsten carbide. On this 4 mm flat face of the tungsten carbide, two pyrophyllite washers of 4 mm outer diameter and 1 mm inner diameter, and each of thickness 170 micrometer, provided a sample volume of 1 mm diameter and 340 micrometer thickness. In the sample volume, two steatite discs of 1 mm diameter and 130 micrometer thickness each, sandwiching the sample, was loaded. After mounting the sample on the anvils, and copper leads were electrical contacts were made using 48 gauge copper leads on the bottom pyrophyllite washers. After mounting the sample on the anvils, the anvil was loaded inside the guide tube and the electrical leads were taken out through the lids. The pressure was applied on the piston and it was locked by rotating the lock pin. And the high pressure cell was then attached to the bottom of a dipstick setup used for the electrical resistivity measurement, which was dipped inside the liquid helium storage devar. And by exploiting the natural temperature gradient present inside the devar, temperature dependent electrical resistivity measurement was done from room temperature down to 4.2 Kelvin. The pressure calibration in the cell was performed by measuring the TC of lead. The TC of lead was found to decrease with increasing pressure. Hence, in the sample volume, along with the sample, a small strip of lead manometer was also loaded. Now let us see the results obtained for the pristine sample. The composition of the pristine sample obtained is shown here. Clearly, the sample lies in the overdoped regime. The temperature-dependent resistivity measurement showed that with increasing pressure, the TC monotonically decreases. And this is the characteristic behavior of an overdoped sample. Further, we also see that there is a change in the normal state behavior from metallic to semiconducting as a function of pressure. This can be explained as follows. When pressure increases, the volume of the lattice decreases. As a result of that, there can be an increase in the coupling of the copper oxide planes, and this will result in the evolution of a band structure with decreased bandwidth, which tend the sample into a semiconducting state. Further, to check if there is any structural phase transition associated with pressure, we have carried out high pressure X-ray diffraction measurements on the sample at ambient temperature, and we found that there is no structural phase transition sample. Obtained PV curve was further analyzed using third order Birch-Murnaghan equation of state, and we calculated the bulk modulus. For BI2212 phase, the bulk modulus was found to be 89 GPa, and that of BI2223 phase was 76 GPa. Thus, we see that there is no structural phase transition in the sample. However, the volume of the lattice is apparently compressed, and the superconducting to insulating state obtained in the sample is not due to any structural phase transition. Now, let us see if there is any change in the behavior with lead substitution. The composition of the lead substituted sample is shown here, and this sample is also clearly in the overdoped regime. The temperature-dependent resistivity measurement shows the presence of two transitions. It is found that with increasing pressure, the TC initially decreases and then up to 4.5 GPa, and with further increase in pressure, there is an increase in TC. Usually in literature, pressures as high as 20 GPa are required to observe this increase in TC. So this observance of resurgence at TC at very low pressures of 4.5 GPa can be attributed to the effect of lattice pressure created by the chemically doped lead, the bismuth site. Also, this is confirmed from the ambient temperature ambient temperature X-ray diffraction measurements, where we found that there is a decrease in the C lattice parameter by nearly 0.2 Armstrong with lead substitution. And from literature, we know that the decrease in the C lattice parameter can effectively increase the doping levels of the inner copper oxide plane. They can also increase the density of state at the Fermi level by charge transfer between copper 3D and oxygen 2p band. Further, we have carried out high pressure X-ray diffraction measurements on these samples, and we found that there is no structural phase transition in the sample.
and the obtained PV curve was analyzed.
Ms. Gayatri, you have to wind up quickly. Almost taken a time.
An equation of state, and we found that with lead substitution, there has been an increase in the value of the bulk modulus. Thus, we see that there is no structural phase transition in the sample, and the volume of the lattice is apparently compressed. And an increase in the value of the bulk modulus was observed with lead substitution. And we confirm that the TC resurgence observed is not due to any structural phase transition. As I conclude, in pristine sample, pressure-induced change in the normal state behavior from metallic to semiconducting was observed. And in lead substituted sample, a resurgence in TC at 4.5 G was observed, which is very less compared to the literature value. And an increase in the bulk modulus was observed with lead substitution. And there was no structural phase transition in the sample. However, the lattice volume was compressed with pressure. I acknowledge the Department of Atomic Energy, Government of India, for the funding provided for my research work. The references. Thank you for your attention.
Ms. Gayatri, and now the talk is open for discussion. I invite
Okay, Ms. Gayatri, you showed on our slides, you talk about density of states. Now, density of states doesn't play any role. They are not BCS superconductors. They are unconventional superconductors where the density of states does not come into play, number one. Then again, the density of states, you say it is increasing, should be increased. Now, the TC, the mechanism not known in the unconventional superconductors, and so don't talk about density of states, okay? That is not, absolutely, the first page slide, you should remove that. You don't worry about the density of states. And in the later stage also, density of states will not come into play. Only for the BCS superconductors, it will come into play, okay? That those things are to be removed when you are talking about unconventional superconductors where the mechanism is yet to be known, okay? The BISCO and all the IPO and all the copper oxide layers in the superconductors, they are unconventional. So the remove those things, okay? Okay, thank you.
There are no further questions. Thank you, Ms. Gayatri, for the wonderful work. Wish you all the very best.
I move on to the next oral presentation by Mr. Kannan Murugesan from Bharati Dasan University, Tiruchirappalli, India. And the topic of his presentation is pressure effect on magnetic transport properties of non-centrosymmetric NbRH2b2 superconductor. Murugesan. Mr. Murugesan, are you present? You can unmute yourself. Mr. Murugesan, you can unmute yourself.
Mr. Kannan?
Mr. Kannan Murugesan, will you please share your presentation?
Sorry, I have Can you hear me?
Yeah, we do hear you.
Yes. Thank you for all.
Proceed with your talk.
First of all, I would like to thank for the committee members.
Mr. Kannan, before you proceed with your talk, I want to tell you, you have about 10 minutes which is allotted for your presentation and 2 more minutes for the discussion.
Okay, sir. I will conclude within 7 minutes also.
Thank you so much.
Okay. Today, my topic is pressure effect on magnetic and transport properties of non-centrosymmetric NbRH2b2 superconductor.
And this is my plan of talk. First, I would like to introduction of superconductivity and experimental techniques, what were used to measure the electrical resistivity and magnetic properties of this NBR-H2P2 superconductor. And finally, we'll discuss about the result and discussion about the magnetic properties and transfer properties at ambient and at pressure also. This is a general introduction about superconductivity. In general, there are two phenomena which confirms the superconducting phenomena which occurs in the superconducting materials, that is zero resistance and diamagnetism. Apart from these, there are other properties also there. That is vortex spinning, which confirms the maximum magnetic field inherent in the superconducting materials. That includes the del Tc and del L pinning mechanism, in which del Tc depending on the various critical temperature, and the del L pinning mechanism on the variation in the mean free path. So this is mainly depends on the Lorentz force and the critical transitivity and the magnetic field of these sporadic materials. So the maximum field in the magnets is also determined by this vortex spinning mechanism also. And I'm not going to discuss about what is the structure of non-central symmetric, but I would like to share some slides of these non-central symmetric superconductors. These are a list of some non-central symmetric superconducting materials in which the superconductors with the inversion singlets possessing either spin singlet or spin triplet pairs. But in the case of non-central symmetric superconductors, there are mixing of spin singlet and spin triple pairing mechanism. That's why conventional Cooper pairs can no longer form this in this non-centrosymmetric structure. Fermi surface in these NCS materials split due to the lack of inversion symmetry. So that's why there are a mixing of spin singlet and spin triplet pairing mechanism occurs in these non-centrosymmetric superconductors. This is the physical property measurement system in which we measured the magnetic properties of these NBRS2B2 materials. It can go up to 2 Kelvin, and the maximum field played is 9 Tesla. Anyway, we measured the pressure dependent magnetic measurements for this NBRS2B2 material, and MT, that is a temperature dependent and field dependent magnetization with the under pressure. And also we measured the resistivity under pressure with this PPMS physical property measurement system available at Center for Research, Bharat University. And this is also another important work in this talk. This is a piston centrifugal cell, and this in which the hydrostatic pressure is applied on the sample, in which we have used the Daphne oil. It can go up to 1 GPa pressure, and this is made up of beryllium copper and other things also zirconio discs. In this, the sample is imaged with Daphne 733 oil, so that the pressure are applied in all directions to the samples. So we can expect the exact hydrostatic pressure in these conditions. This is also another pressure cell which is used to measure the electrical resistivity measurements under pressure. In this, we use the 7373 ion. So there is also several parts of this hydrostatic pressure cell, in which also we have used Teflon capsules and beryllium rubber rings also, so that we can expect pure hydrostatic pressure up to 3 GPa for electrical resistance measurements. And this is a general introduction about NBRH2P2. And we got this sample from our collaborator, Professor Geeta Palakrishnan Research Group, University of Warwick, UK. And this is it has triconal P3 structure, and they synthesized this material by the solid state synthesis method. And this sample shows the superconducting transition temperature at Tc is equal to 7.6 Kelvin, and we can have zero resistance also there. And we measured the pressure dependent magnetic measurements, that is temperature dependent magnetization and field dependent magnetization. From that, we calculate the critical current density under pressure, so that from these measurements we conclude some pointers. Coefficient is minus 0.41 Kelvin per GPa. This is a very small amount of pressure coefficient, and it shows the robust nature of this superconducting material. We can calculate the critical current density from the Bin's critical state model. Maximum field of JC at very low field. So it is a general in superconducting materials. And this JC and low field and higher field also, it's higher than that of the sister compound of TRH2B2 at both and low fields. This is another important measurement for this material. High pressure, pressure dependent electrical resistivity measurements. From this, we have calculated the upper critical field and pressure. So this is the pressure dependent without field. By this measurement, we can calculate the pressure dependent TC. This is also shows the nearly minus 0.3 Kelvin per GPa. This is also shows a very small amount of consolidated coefficient. It also shows the robust nature of these samples. In the case of normal set resistivity at 300 Kelvin, it decreases with increasing pressure 2.7 to 2.1 million centimeter, and the ratio also increasing with the increasing pressure. So it's suggesting some effect of combined effect of weak grain boundary and the disorder in spin orbit coupling of materials. These are somewhat other robustness of this superconducting material. And the field dependent, these three pressure dependent, at the fixed pressure, we measured the field dependent electrical resistivity measurements. From this, we can calculate upper critical field for these samples. So we used the GL for equation for calculating the HC is zero, that is zero temperature upper critical field. From that, we can have some scenarios of this type of scenarios, so that here exceeding the Pauli limit is an application of heavy pinning or exotic nature of these superconducting materials. So from that, we can conclude some pressure induces some pinning centers in this superconducting material.
Anand,
so
you need to wrap it up. You're taken 10 minutes now.
Only two slides, sir. Only two slides.
Finish it up fast, please.
Yes. This is also another we can use the Arrhenius equation to calculate the activation energy. So the activation energy decreases with increasing pressure up to 3 GPa at a constant field. At a low field, there is some pinning mechanism also there. That's why the very small changes at the low field. And this is pinning mechanism present in this material. We used the collective pinning theory to determine what is the main pinning mechanism in this material. At ambient pressure, it shows the del L mechanism, del L pinning mechanism. Further increasing the pressure, it moves towards the del TC pinning mechanism. And another, there is some other phenomena also occur in this materials, that is both the surface and volume pinning mechanism in this NBRS2B2 in similar to the sister component of T2 RH2B2. So finally, conclude my session. The effect of pressure on magnetic and transport properties of these materials is studied. And superconducting transistor pressure decreases with increasing pressure, and the critical current density estimated using the Bin's critical state model. reduced with increasing pressure. And finally, the activation energy is measured using the thermally active flux flow motion at both ambient and high pressure. It significantly reduces the increase in pressure. So it induces the crossover pinning mechanism from del L to del C pinning mechanism. And thank you for my invitation. Thank you, sir.
Yeah, thank you, Mr. Kannan. Is there any? Now the talk is open for discussion. Invite questions from the floor.
These are BCS superconductors, is that right? Hello?
Hello, sir?
These are all BCS superconductors, is that right?
Yes, sir.
If they are BCS superconductors, that will mean the pairing will be singlet pairing, not triplet pairing.
Sir, I'm telling this general.
The inversion center doesn't come. Or what is the irrespective inversion center? It may, it will be S equal to 0 state, up, down, not triplet pairing. Triplet come when S equal to 1. Okay, you check anyway, verify this.
So this is not for non-NCS material. This is general. It's for centrosymmetric superconductors. I don't know about the idea about the non-centrosymmetric structure of this moment and others also. I will check anyway. I will check it.
Okay, if there are no further questions, once again, thank you very much for the interesting talk, Mr.
Thank you,
Kannan.
sir.
We'll move on to the next talk in the.
The next oral talk is by Mr. Satish Kumar Mariappan from Bharati Dasan University, India. And the title of his talk is Hydrostatic Pressure Effect of Superconducting and Normal State Properties in the Non-Centrosymmetric RE 5.5 TA. Mr. Satish Kumar.
Yes, good evening.
Mr. Satish Kumar.
Yes, sir, I'm here.
I have a couple of instructions for you.
Yeah, please.
You're given 10 minutes for the presentation and 2 minutes for the discussion.
Okay, thank you.
Talk 10 minutes. Thank you.
Okay, thank you for the opportunity. So, as like I'm going to explain, talk something about the hydrostatic pressure effect of the rhenium tantalum non-centrosymmetric superconductor, which was recently reported by my collaborator from ICREACH2022. So now the motivation of this talk, I mean the outline of overall talk is the motivation and the experimental techniques, which are the things I used to collect the data. Sorry again?
Yeah, your slides are not shared, sir.
Oh, really? Just a minute. Thank you. Now is okay? Is that fine now? Hello? Hello?
Yes, visible.
Fine.
Is that okay now?
Fine, fine.
Thank you, sir. So actually, this is the collaborative work with Institute of Solid State Physics, University of Tokyo. So we received the sample from our collaborator from ICREACH2022. So these are the overall outline of the talk. First of all, the motivation, why this material is quite important compared to the others. Then the experimental techniques, which was I used to data for the data collection and all, then the resultant discussion, and finally conclusion, what I have from the overall samples. So the motivation is mainly most of the non-centrosymmetric superconductor, we know, even from the selenium-based magnetic or non-magnetic rhenium-based many non-magnetic systems, they showing the lack of inversion symmetry. So due to that, in many samples, the antisymmetric spin order coupling was observed. And moreover, the large upper critical field than the Pauli limit was observed in the various non-centrosymmetric superconductors, including the magnetic or non-magnetic things. So also in many papers, they reported the possibility of spin singlet and spin triplet state, including this sample. And apart from that, time reversal symmetry breaking is one of the main thing. Breaking at the superconducting state is the major thing was observed in the many non-centrosymmetric superconductor, and it was considered as a signature for the unconventional superconductivity. Then the synthesis of the sample is done by the arc melting method, and the lattice parameter and space group was done by the X-ray diffractometer, and the sample was reported at 2020 at PRV from our collaborator Ravi Prakash Singh. So this is the resistivity. So the ambient resistivity was basically the resistivity was done using the 4-probe method, and the ambient resistivity and the high pressure resistivity up to 3 GPa, sorry, up to 2.5, sorry, 1.7 GPa was done using the PPMS. And the high pressure, this is the high pressure resistivity cell. So I can reach up to 2.5 to 3 GPa in this pressure cell. But due to some things, I can only reach 1.7 GPa for this sample. So here we use the Define oil as a pressure medium and lead as a calibrant. Actually, I mounted the lead along with the sample. So for each measurement, I should check and I make sure either it is reaching the exact pressure or not. So same thing, this cell was measured using the PPMS. And the 8 GPa, I mean the resistivity up to 8 GPa was done using the cubic annual cell. This is one of the special technique only available at Japan and I think recently some countries, South Korea and China, I think. But moreover, this is a purely hydrostatic process. So I checked the sample up to 8 GPa. Then the micro type piston cell, actually the maximum limit is 1.5 GPa, which was completely made up by the ISSB, University of Tokyo. So that the magnetic measure was done using the MPMS. So this is the overall measurement. Actually, the resistivity shows the exact TC around 7.99 Kelvin, and the TC was decreasing with the pressure. And moreover, the residual resistivity ratio, which means triple RR, is almost similar. So we can see the consistency of the sample with pressure. Even though it is consistency, the metallic behavior was observed with pressure because the overall resistivity was decreased with pressure from 0 GPa to 8 GPa with linearly. And the magnetization measurement also supports the resistivity data, so which shows the similar transition point for us like resistivity. And this is the field dependent resistivity data. So from here, as usual, the TC was decreased with field also. Also the broad transition with increment of with magnetic field suggests the dissipation energy, which may be induced by the vortices. And moreover, this is the upper critical field. The upper critical field was calculated using the Ginsberg-Landau equation. So that we calculated upper critical field from the data which the data extracted from the field dependent resistivity. So that we found the upper critical field which was slightly larger than the Pauli limit. So again the same claim as I mentioned earlier. So again the same. And moreover, this is the field dependent magnetization data. So here it shows the type 2 behavior. So overall with pressure also the magnetic moment was slightly changed, but even though it's changing slightly, so that the lower critical field was calculated again using the Ginsberg-Landau theory. So again, this is a fitting, and the inset of the figure shows the pressure dependent lower critical field. So that the again the as like upper critical field, the lower critical field also suppressed, I mean, or decreased with the pressure. And moreover, the log rho versus 1 by T curve obeys the Arrhenius relation. So that using the TAF model, just I plotted the log rho versus U naught, I calculated the activation energy. So with that, the plotted with a magnetic field for each pressure. So just here for your, for the due to the timing, I just here separated only two data. So the double linearity suggests the single and collective vortices. So that the vortex may be not single vortex, it may be collective pinning also. Again, the collective pinning, using the collective pinning theory, I calculated the JC. So the JC again suggests the JC was using the Bean's critical model, so that from the isothermal, from the MH magnetic field dependent magnetic curve. So again, the JC drops with the magnetic field slightly. Also, the JC was drops with the pressure. So which was shown in figure E. It was quite clear. And moreover, the using the collective pinning theory, the JC versus TC, JC versus TC fitting was done. So it suggests the del TC pinning and del L pinning. So with field, magnetic field at 0 Tesla, the del TC pinning was observed, was more dominant, and once the field is increased, the Delel pinning was more dominant, even though apart from the field, the pressure also here plays the minute role. And from the JC versus Hertz, I calculate using the scaling power law, I fit the linear fitting so that from here I calculated the beta value. Again, the beta value suggests the non-interacting vortices and core pinning mechanism. Also, here the surprise thing is here we observed that beta value more than 1.5. So the value below one, beta value below 1 is suggests the non-interactive vortices, and above 1 point, above 1 to below 1.5, it suggests the core pinning mechanism. So, and apart from that, here we can see very clearly with field the beta was increasing more than. Apart from that, even though with pressure also beta value is increasing very slightly. So again, the pressure and field both are the reason for the single to collective pinning vortices. These are the conclusion. The TC is the TC was decreasing, and also the overall TC rate is 0.52 Kelvin. So it is very slight amount compared to the normal superconductors and all. So it's very 0.0639 Kelvin per gigapascal. So here I measured up to 8 GPa. Moreover, it shows only linear behavior. And the HC2 also is observed from 16.91 to 16.56. Actually, this value from 0 to 1.7 gigapascal. So again, this suggests is always higher than the Pauli limit. So again, the HC1 also is decreased. The coexistence of single and collective pinning vortices was observed from the TAF studies and collective pinning theory. And I acknowledge the SCRB OVD.
Thank you very much. Now the talk is open for discussion.
In general, when apply pressure, TC decreases or increases? Hello, are you able to hear me? Are you, the speaker, are you able to hear me?
Hello, Mr. Satish Kumar. Mr. Satish Kumar. No, Professor Ashok Mani, I think that Satish Kumar has lost connectivity.
Okay, it's all right then.
Okay.
Okay. His friends can tell. He made a statement strongly correlated. I mean, something like unconventional superconductor, time reversal symmetry. These are all conventional superconductors. I don't know why he is bringing the time reversal symmetry here.
You can put your comment in the chat box. Maybe he can respond as and when is convenient to him.
Okay, I will try to do it, and maybe he has to read more. That's what I.
We'll move on to the next speaker.
So the next oral presentation is by Dr. Devdutt Lahiri from BRC, Mumbai, India. The title of his talk is Correlation between FeAS4 structure and 3D electrons of PRO P0.9 CO.1
Yes,
case
now
under high
it's
pressure.
audible. Now it's audible. Thank you.
Mr. Lahiri, you can continue.
Hello, Mr. Devdutt Lahiri.
Yeah, can I start?
Yeah, one moment. Yeah, I just have only one instruction. Yeah,
yes.
You make a presentation for 10 minutes. Following this, there will be discussion for 2 minutes. Please restrict your presentation to 10 minutes. Thank you.
Okay, sure. Okay, I will be presenting my work on nictide superconductors, where we use high pressure to tune the structure and subsequently the electronic structure. Next slide, please. Yeah. So nictides are the recently discovered superconductors, high TC, and the highest TC is reported to be around 55 Kelvin. Next slide, please. Yeah, the structure of nictides is very similar. This is the generic formula of nictides, where R is a rare earth. So the structure is very similar to cupret. It's a layered structure where the rare earth and oxygen form the reservoir layer, and the conducting layer is formed of iron and arsenide. And iron and arsenide, they are in a tetrahedral configuration, interconnected.
So what is practical difference from cuprate is that this conducting layer is more tolerant of disorder. In the case of cuprates, if you dope this conducting layer, within 3% of doping, a TC is destroyed. But in pnictides, we see that it can sustain TC up to 30%. So this certainly gives the pnictides an edge in terms of adaptability and also flexibility of synthesis, for which it is of interest to us. And the reason behind this difference between the two classes of compounds is the 3D electron itinerancy of pnictides. This is a hypothesis. We are yet to completely understand this. Next slide, please. So although we don't completely understand it at this point, but it is clear that manipulation of 3D electrons is at the heart of this problem. And it is proposed that the tetragonal, the geometry of this tetrahedron is crucial to the TC, and the pathway is by modifying the iron and arsenic orbital overlap. So it is said that when the tetrahedron has a regular shape, that is, the angle is about 109.4 degrees, the TC is maximized. So what is the experimental status of this proposal? So several experiments have been done, and it has been indeed shown that when the angle is around a regular tetrahedron, the TC is maximized. So this is not my work, but from selected from other works. So we have been, the experiments have been able to establish a correlation between the endpoints of this route, that is the angle and TC. And this is an empirical conclusion. But this doesn't clarify what is the mechanism of control. And for this, I mean, how the structure modifies the electronic structure and then it goes to TC. So this is where it is lagging right now, and this is the objective of our present work, where we see how this structure is controlling the electronic structure. So we measure structure with XRD and the electronic structure with XANES. Next slide, please. So the now on to our experimental plan. So we have selected a 10% cobalt doped pnictide whose TC is 14 Kelvin at ambient pressure. Now the purpose of our work is establishing a generic correlation between the geometry, a tetrahedral geometry, and electronic structure, and the superconducting phase is not of immediate interest to us. So we have done the measurements at room temperature. So we have used pressure as the medium to control structure. So we monitor the structure as function of pressure, and correspondingly we measure XANES as a also as a function of pressure over the same pressure range. Next slide, please. So before I go to my results, I will go through a couple of slides explaining what XANES is about. XANES is X-ray absorption near a structure. Next slide, please. It's an integral part of EXAF spectrum, that is X-ray absorption fine structure. These are essentially absorption experiments where you stick the sample in the pathway of X-rays, you measure the incident intensity, you measure the transmitted intensity, you take the ratio and measure the absorption. Now, how do I select the energy of the beam? Suppose this sample has two elements, A and B, and I want information on A. So then what I do is, I tune this energy to the binding energy of this particular atom, A. So suppose the binding energy is E0. So when the X-ray energy is around this value, we see a huge jump in absorption. Then we slowly keep on increasing the energy up to 1000 eV beyond this edge, and we start looking this wiggles. So the first part of the spectrum is XANES within 30 eV, and later this is EXAFs, which is responsible for structure. Next slide, please. Okay, what is the science of XANES? In XANES, what happens that when you are exciting this electron with sample with X-rays, so around this edge value, a photoelectron is ejected, which amounts to the absorption. So and around this energy, say within 30 eV of this edge, edge plus 30 eV, you say the kinetic energy of the photoelectron is quite low, so it becomes sensitive to the surrounding potential, from which can be used to detect important properties like charge transfer, etc. Now we have to let us focus on 2 points. One is that absorption is dominated by dipole selection rule. So when we are exciting around the k level, so the electron, the initially it will be in s orbital, so it can go to a level where it has p orbital. So it is a delta L plus minus 1, that is the transition. The next point is that the probability of this transition will depend on how many vacant p states are available. So in other words, the more p states are empty, or the higher, we can say, higher the p hole density, the sharper will be this absorption. So this feature post just above the edge is called white line, and we see that it is proportional to the number of empty states. Now p hole density, in other words, it means that or empty p states, it means that electrons have moved out from there. So that can be also interpreted as charge transfer or loss of electrons. In other words, higher p hole would be in a higher oxidation state. So this comes down to sharper the white line, we can deduce that higher is the oxidation state. So an example is shown here. Previous slide, please. Previous slide. Yeah. See, this is gold metal without much white line, and this is in +3 state with a very sharp white line. So we can use in our work, we will be using this white line to estimate charge transfer. Next slide, please. So in our work, we are interested in iron 3D information. So for that, we cannot use iron or say cobalt K edges, because here it will give information on the p state of iron, which is not of interest to us. On the other hand, instead, if we use the arsenic edge, this will also give information on arsenic p state. But because arsenic is hybridized with iron 3D, so indirectly we can get the 3D information. So in our work, we will be basically monitoring as a function of pressure. We will be quantifying this white line feature. Next slide, please. So the XRT experiments were done at BL11 of Indus 2 and Zanes at 6th beamline of Petra 3. Diamond anvil cell based experiments. Thickness of diamond total was 1.5 millimeter. Next slide, please. Now on to the results. Okay. So the high pressure XRD experiments and results were taken care of by my colleagues, Dr. Nandini Garg and Dr. KK Pandey. So the essence of this XRD results was the compression naturally of the cell, but there is a transition seen at around 6 GPa. It becomes more tetragonal. Now when we go to, we specifically go to iron arsenide.
Excuse me, madam.
That what happens?
Excuse me, madam. You're taking 10 minutes. Wind it up quickly, please. Yeah.
Yeah, this becomes this reaches its shortest limit, iron arsenic bond length, and okay, then this tetragonal geometry undergoes a reversal. So beyond 6 GPa, what happens is there is more of the situation is more in favor of PD overlap. So the bond length is also short. The angle is also towards the regular tetrahedron. Next slide, please. So we see the reflection of this in high pressure Zanes. Even in Zanes, I'm not going into the details, around same transition pressure 6 GPa, we see a very high increase in the white line area. That means p holes increase dramatically, or in other words, the electrons are delocalized from p to d, which means that increased PD hybridization. Next slide, please. So the summary of our results is that with XRT and Zanes together, we could establish a correlation between structure and electrons, and it was effectively done with high pressure agent. And I thank all my collaborators. And just one extra slide. Next slide, please. Where I present this slide to introduce that we have installed our high pressure exhaust beamline at Indus 2, and we have already demonstrated high pressure induced Zanes and exhaust changes. Thank you.
Madam, thanks for the good talk. It's a good data that's presented. We'll move on to the next paper now. We're running out of time.
Yeah, sure. Thank you so much.
Now we have 8 flash presentations. The first one is by Dr. Brahmanand Chakrabarti, Nava Atomic Research Center, Mumbai, India. And the title of his talk is Influence of Transition Metal Dopant Cobalt Manganese Copper on High Pressure Behavior of Zinc Oxide, Perspectives from Density Functional Theory Simulations.
स्लाइड शेयर कर सकते हैं? Can you share the slides?
Sir, we are doing it. Sir, you can start.
There is some problem इसमें आ रहा है desktop पे.
Check whether he is able to.
Okay, thank you. Okay, myself Dr. Bharat Bhushan, and I am presenting this talk on behalf of Dr. Brahmanand Chakrabarti, and thank you for giving me an opportunity. And the topic of my talk is influence of transition metal dopant cobalt, manganese, and copper on high pressure behavior of ZNO. Perspectives from density functional theory simulations. Next slide, please. Okay, so why we are studying zinc oxide? Zinc oxide is a direct band gap n-type semiconductor which has a band gap approximately 3.3 electron volts. Here we have calculated the band gap from density of state, and now our calculated band gap is around 3.12, which is matching with the experimental values. And due to the band gap of 3.3, it has the potential applications in photocatalyst, UV lasers, and lithium-ion battery materials. So, and crystal structure of ZNO belongs to Woodside structure, space group P63 by MC. So, what was our motivation to study ZNO with these dopings? We wanted to study the stability of structure under pressures, specifically when we dope transition metal elements in these structures. So, in pristine form, ZNO has a transition pressure around 10.1 as a theoretical calculation, or 9.1 as experimentally. So, we wanted to see what happened when we dope these elements into the structure, and we carried out experimental studies and DFT simulation study with 6% doping of copper, manganese, and cobalt elements. So here are the lattice parameters of ZNO, and it is experimental values, and we have computed are exactly matching. So our calculation has taken is pretty good in this system. So we carried out high pressure study in optimized structure. Next slide, please. So what we saw when we have a 6% doping of copper in ZNO, we calculated pressure versus volume. Here it is shown. Now we used the WASP code and with GGA corrections, and we found out that at 9.4 GPa, we observed the Woodside to rock salt phase transition. We know that in pristine form, there is a phase transition at 10.1 GPa. When we have a copper doping, that means due to the doping of copper, the transition pressure slightly reduces. theoretically, and we also know by experimental result that experimentally it is coming more around 6.4 GPa. So we can reduce that by the doping of copper, the transition pressure decreases, and same is found to be happen at when we dope manganese and cobalt also. So here we have plotted the enthalpy curve. We can clearly see that enthalpy of rock salt and woodside structures is crossing each other at 7.5 GPa, and so what our motivation was to see what are the causes that which are making this structure unstable, and also there is change in the band gap due to the doping also. So this whole study can have a potential application in industries also. If we can reduce the band gap, we can use these materials with different kind of applications. So next slide, please. So we calculated our motivation was to see why there is a change in doping of copper, because we know by when we dope Mn and cobalt, there is a decrease in the transition pressure. So the decrease was found to be not as it was found to be around 9 GPa, which was not very less than 10 GPa, which is in pristine form. But in experimental form, when we dope copper, we found out that our transition pressure dropped around 6.7 GPa, which is found to be experimentally, and in theory, which have found to be around 9 GPa. There can be mismatch with theory also, but it is more or less than compared to Mn and cobalt dope. So we plotted partial density of the state, and we found out that there is a charge transfer from dopant element to the Zn element. So this is the cause of instability in the structure. Whenever we have a large transfer from the dopant element to the Zn or zinc element, zinc atom, so the instability increases. So here we have plotted the partial density of state. We can see that there is a large partial density state in copper compared to Mn and cobalt. So we have deduced that this is the cause of instability. Next slide, please. So our charge density plot of charge density difference between ZnO and copper is a cause of instability, and copper with charge density isosurface greenish blue color is plotted here. Here we can see there is a large transfer from copper to Zn atom, and here we have shown the charge loss by dopant. When we dope copper, there is a 1.1 electron, and Mn. So as the charge transfer is increasing, the instability is increasing. So there is a reduction in the lattice parameter of in A and B in the all direction. When we dope all three elements, there is a slight elongation in the C direction in copper and cobalt doping, and also with doping, non-magnetic ZnO become magnetic. And as a conclusion, we have a transition pressure which can be lowered by substituting the doping of copper. And similarly, copper, cobalt and Mn doping, the transition pressure can also be lowered, and reason may be that the charge transfer mechanism for copper doping is same as a cobalt and Mn doping, and dopant atom losing charges. And theoretical support the experimental findings which have carried out by me by the X-ray diffraction studies. Thank you.
Thank you, sir. So the next flash presentation is by Ms. Nisha Yadav from MNIT Jaipur, and the title of her talk is Effect of Copper Ion Implantation on the Structural, Compositional and Electrical Properties of BiSB-TE3 Single Crystals. You may start.
Good evening, ma'am. Good evening, all of you. Can I share my screen?
Yes. Go ahead.
It's already shared.
Is this visible?
Yes, visible.
Okay. Myself Nisha Yadav from MNIT Jaipur. The topic of my today's presentation is effect of copper ion implantation on the structural, compositional and electrical properties of BiSB-TE3 single crystals.
Ma'am, you can make it full screen.
Okay. Just a minute. Is it fine now? First, I will talk about what are topological insulators. Topological insulators are material with insulating bulk and conducting surface states. Here, this is diagram of quantum Hall insulator. Here we can see that when magnetic field is applied, there is a motion of upspin and downspin in opposite direction, as we can see from this diagram. But in case of topological insulators, there is no need to apply an external magnetic field, because in TIs, the role of magnetic field is played by spin orbit coupling. Here, this is the band diagram. Here we can see that the surface states are arised in topological insulators due to the spin orbit coupling induced by spin momentum locking. And some of the characteristics of topological insulators are that they are immune to defects, no backscattering is there in, and they also conduct on surface. Next slide. I'm not able to move. Sorry. Yes. Now, what happens when implantation occurs in these topological insulator? As we all know, when implantation is done, there are electronic as well as nuclear energy losses are there. Here we can see that when light ions are implanted in a material, then they will go deep inside the material, while when heavy ions are doped, they will go less into the material. Only surface part is affected. So why we have chosen implantation? Because in implantation we have control over the bulk charge carriers, and we can also select different ions as well as different energies. Now, here I am showing what I have synthesized. First, I have synthesized BiSp-Te3 crystals, and as I have chosen this because in BiSp-Te3, the Fermi level and the Dirac point lies in the bulk band gap, which is important for device application point of view. So first, high purity elements of Bi, Sb, and Te were taken in desired stoichiometric ratio and put it in these ampules, and they are sealed under vacuum of the order of 10 raised to power minus 3 millibar. After that, these ampules were sealed, and the sealed ampules are placed in furnace where proper heat sequence is followed, with further slowly cooling them to room temperature to get the crystalline lump. This is the as prepared polycrystalline lump, and here is a single crystal cleaved from this lump, and this is an image of a big piece of crystal cleaved from this polycrystalline lump. And here I am showing that when copper ions are implanted, that they disturb this crystal lattice, and we further study how these copper ions affected the crystal of BiSb-Te3. This is the SEM image. Here, these two are pristine. First one is the pristine image of BiSb-Te3, and this is the implanted one. Here we can see that there is not much reasonable any reasonable effect on the surface of the crystals. And here's the figure C and D. Here we can see in figure D that copper ions are implanted well in the BiSp-Te3 crystal, and they are also homogeneously distributed on the surface of the crystals. Further, we have done the XRD measurements on this. We have seen that with ion implantation, there's not much variation in the crystal, but lattice parameters are decreased with ion implantation, and thereby decreasing the lattice volume, which might be due to the tensile strain generated in the material with implantation. We have done the resistivity versus temperature plot. Here we can see that with implantation, the resistivity is increased, which can be attributed to defects generated in the system with implantation. These are the XPS measurements. Here we can see that in pristine sample, the BiSb-Te3 is in stoichiometric ratio, but when ion implantation is done, we do not get the stoichiometry is disturbed. I have not shown the figure as the copper implantation XPS is not fitted well, because there is a very little amount of copper implanted in the crystal. Now concluding, the XRD measurements which we have done revealed that there is a decrease in lattice parameters with ion implantation, confirming the implantation of copper in pristine sample. The SEM image confirms that there is not much variation detected on the surface of crystals. The EDX measurements demonstrate that the homogeneous distribution of elements on the surface of the crystal. The X-phase measurements on the pristine sample confirm the composition of BISBD3, and the resistivity was increased with copper implantation, which is due to the defects or disorder generated with copper ion implantation. And I will acknowledge Department of Physics, MNIT Jaipur, for giving me opportunity to do PhD there, DST New Delhi for giving me fellowship, IUAC New Delhi, UGC DAE CSR Indore for financial support, and Material Research Center, MNIT Jaipur, and Hiroshima University, Japan for providing the characterization facilities. These are the references. Thank you.
Thank you, ma'am. Now we move on to the next speaker, Mr. Debrat Samanta from ICER, Kolkata, India. And the title of his talk is Pressure-Induced Emission Enhancement and Bandgap Narrowing, Experimental Investigations and First Principles Theoretical Simulations on a Model Halide Perovskite CS3SB2BR9. Mr. Samanta.
Hello.
Hello, yes.
Yes,
Hello.
you can start.
Okay, should I start now?
Yeah.
So today I want to talk about my recent work, and the title of my work is Pressure-Induced Emission Enhancement and Bandgap Narrowing, Experimental Investigation and First Principle Theoretical Simulation on a Model Halide Perovskite CS3SB2BR9. So as you see here, I shall be talking about a lead-free halide perovskite CS3SB2BR9 in the next few minutes. The CS3SB2BR9 has a trigonal structure, space group P-3M1. It is found to be a good photovoltaic material with outstanding photovoltaic properties like direct band gap, high absorption coefficient, high electron hole mobility, etc. Despite several photovoltaic properties, wide bandgap of the material prevents itself in the application of solar cell. Usually, the researcher try to tune the bandgap using traditional way like chemical manipulation, different processing condition. But here we have investigated structural, electronic and optical properties by applying pressure. As you see here, at ambient condition, we have observed 6 Raman active modes. Out of those, 2 are assigned to A1G and EG symmetry based on our theoretical calculation. So, as you all know, the absorption and emission are the key of the photovoltaic material. Therefore, I want to show you the emission and absorption spectra, and this is what you see here. The emission and absorption spectra appears with a large stroke shift of about 1 electron volt, and the strong electron photon coupling leads to a broad emission, and the broad emission is attributed to self-trapped exciton recombination. And the initial blue shift followed by a red shift may be an indication of structural or electronic transition at 3 GPa. And the ST emission get enhanced up to around 1.4 GPa due to an increase of population of exciton at the excitonic level, and then again it start to decrease. So here you see the outcomes of high pressure Raman scattering measurements. In the high pressure Raman scattering measurement, we have observed a new Raman mode at around 3 GPa and a signature of disorder beyond 14 GPa. And the disappearance of all low frequency mode at about 8 GPa suggests a structural transition. The unusual behavior in the FWHM of Raman mode and the integrated intensity mainly caused by an electronic transition and the change in internal polarization of the sample respectively. So to investigate the observed anomalies in the photoluminescence and the Raman measurement, we have also carried out high pressure X-ray diffraction measurement, and we have observed a structural transition at 8 GPa, which is from trigonal to monoclinic. The XRD pattern at 20 GPa confirms the signature of disorder observed in the high pressure Raman measurement. And the variation of C by A ratio, which measures the internal strain of trigonal structure, are very consistent with each other that we have got from theory and experiment. The evolution of linear compressibility reveals an anisotropic compression up to around 5 GPa. So to shed light on the evolution of band gap, we have performed density functional theory calculation under pressure. And the theoretical calculation predict a direct to indirect band gap transition at around 3 GPa and also a 27.5% band gap narrowing just 0 to 8 GPa pressure range. And here you see the group members, here you see our group members, and we have also 2 collaborators. And finally, I acknowledge the fellowship grant from INSPIRE program, Department of Science and Technology, Government of India. Thank you for your kind attention.
Thank you, Mr. Samantha. The next talk is by Miss Aishwarya T. from University of Hyderabad, India, and the title of her talk is High Pressure Study of Semi-Metallic Pyrite SiP2.
Can I share my slides?
Please share.
Are you able to see?
You can make it full screen. Okay. Start, ma'am.
Good evening, everyone. I'm Aishwarya from University of Hyderabad. I'm doing PhD under the supervision of Dr. G.S. Vaitishwaran. My presentation topic is high pressure study of semi-metallic pyrite SiP2. And SiP2 is the one of the few compound with a non-transition metal atom that crystallizes in pyrite structure, which is crystallizes in a Pa3-205 space group and was recently discovered to be a promising negative electrode material for lithium and sodium ion batteries due to its outstanding capacity. SiP2 is a magnetoresistive material and topologically trivial and incomplete compensated semi-metal. The magnetoresistance material used as a magnetic field sensors, which are used to read the data in hard disk drives, biosensors, micro-electromechanical systems and other devices. This is the paper which give the result as SiP2 as a magnetoresistive material. Now let us move to the structural properties of SiP2. SiP2 is a cubic pyrite structure with space group Pa3, and the symmetry of the pyrite structure is described by the non-symmetric nature, and the cubic unit cell which is contained the 4 formula unit, and the silicon atom is octahedrally coordinated to 6 phosphorus atom, and the phosphorus atom is tetrahedrally coordinated to 3 silicon atom and 1 phosphorus atom. The phosphorus-phosphorus bond distance in SiP2 is considerably smaller than that expected phosphorus-phosphorus single bond. And now let me go to the structural properties under the high pressure. Like we did the calculation till 15 GPa and studied the structural parameter here. So we have performed structural optimization as implemented in VAST code, and the bond distance between the silicon and phosphorus atom is given in the table, and from that we can clearly see that there is no much change in the bond length till 15 GPa. So we compiled pressure and relative volume curve along with the experimental data, and which is given in the figure. The compiled pressure volume data have been fit with Murnaghan equation of state, and the compiled bulk modulus is found to be 108.6 GPa. And SiP2 does not undergo any structural phase transition under pressure up to till 15 GPa, and we do not observe any significant volume discontinuity in the pressure volume variation, and which is also given, which is we can understand from this curve. And now move to the electronic structure. The electronic band structure of from the this is the ambient condition electronic band structure. From this, it's revealed that it's a semi-metallic nature of the SAP2 and with a weak overlap between the valence band and conduction band. And the state across the Fermi level are near it's due to the silicon and phosphorus p state. When we increase the pressure till 15 GPa, the band shift is gradually, but still it's remain as the semi-metallic nature. So from our calculations, we concluded that the computed bulk modulus is found to be 108.6 GPa. When we increase the pressure till 15 GPa, the band shift gradually retaining its semi-metallic nature. And from our calculation, we found that the compound is still stable till 15 GPa, which will be useful for the several applications like magnetoresistance and battery material. And these are the reference. And I'm very thankful to the PMRF for my fellowship and CMST for the computational facility. Thank you.
Thank you, ma'am. The next presentation is by Dr. Shweta Gumula from MIT Madanapalle, India, and her title of talk is High Pressure Studies of SC2 CRB6 from First Principles Calculation. Dr. Shweta.
Hello, can I share the screen?
Yes, you can share.
Yes, sorry. Yes. Yes, so this is Shweta. I would like to present on the topic High Pressure Studies of SC2CRB6 from First Principle Calculations. I'll start with the introduction which says why this compound is important. If you see the compound, this is a high boron rich compound. We know the boron based compounds have very huge range of applications in various fields because of their physical and chemical properties. Starting from its structure, they adopt different structure from individual atom to three-dimensional, and these are super hard materials. They also have excellent mechanical properties. They'll also show different magnetic properties based on the content of boron and transition metal. And some among them show superconductivity nature, and some shows Dirac material and charge density wave nature. So because of these wide range of applications, the boron based compounds, especially AB and AB2 type of compounds are studied widely. But when I see the high boron based compounds like hexaboride, they are unexplored and there are very little literature about. So I have picked up one of this compound, Sa2CRB6, where it is unexplored. Only a synthesis paper is available. Apart from that, no literature is available. So to study about this compound, we have performed density functional theory calculations by using two codes. One is a VASP code, which I used to perform the geometrical optimization, and I used VN2K code for electronic structure calculations. When I move to crystal structure, it shows orthorhombic crystal structure with the space group PBAM. And if I see the crystal structure here, it shows very interesting crystal structure where I can see the pentagons, hexagons, and heptagons sandwiched between the metal layers. As I told you, this is unexplored cities. So to see the ground state nature, I perform the total energy calculations. And from my calculations, I have seen the ferromagnetic state is favorable when compared to non-magnetic state. When I see this figure, I can also observe that after certain value, these two curves are merging. So give me a hint, there is maybe a phase transition with the pressure. So just confirm that. I also perform variation of lattice parameters with the pressure, and the figure is shown here. From this figure,
We are not able to hear anything.
Oh, Shweta, are you still there?
see this, that's being strategy. From my calculation, I can only say there is a transition from ferromagnetic state to non-magnetic state. To calculate the bulk modulus, I have fitted it to a Bridge-Morgan equation of state, and I found out it to be at 231 GP. To see the nature of the compound, we perform the electronic structure calculations. From these structure calculations, it's shown here, I can see it is a metallic nature where the valence and conduction band crossing each other. If I zoom this electronic structure, we observed an interesting feature here. At X point, both the valence and conduction band meeting at the one point. That means it shows a Dirac cone nature. So the spin polarized Dirac cone nature is observed in this state, where the carriers act as massless Dirac fermions. And we perform the electronic structure with pressure also. What we observed after 30 GPa, we observe there is no difference between the spin up and spin down band structures, which again confirms that there is a phase transition from ferromagnetic to non-magnetic state. In order to see the predominant states near the valence and conduction band, we perform the density of states at ambient case as well as with the pressure. What I observed from here, below the 30 GPa, the density of states shows different behavior. I've shown with the circle here. When I see the density of states after 30 GPa, shown with the square here, they shows a similar behavior, which also confirms the fact there is a phase transition around 30 GPa. From the density of states at the ambient case, we observed the states near valence band is mostly due to chromium D states and boron P states, and the conduction band, they are due to chromium D states and scandium D states. And we also calculated the elastic constant and the phonon dispersion. From our calculations, we concluded it is dynamically and mechanically stable. And from the calculated elastic constant with the pressure, we have seen again hardening of this elastic constant around 30 GPa, which again confirms every phase transition from ferromagnetic to non-magnetic phase. So overall, from our calculations, so we concluded the Se2CrB6 is a ferromagnetic metallic nature compound, and it shows interesting nature, that is existence of spin polarized Dirac cone at X point. We also observed there is a phase transition around 30 GPa from ferromagnetic state to non-magnetic state from our calculations. So I would like to acknowledge Kanchana ma'am, Sastri sir, Vaidishwaran sir, Chandrasekhar sir, Kalavati ma'am, Sharat Chandra sir for their support throughout my research career. Thank you.
Next presentation by Mr. Vikram Mahamia from IIT Bombay, Mumbai, India. And the title of his presentation is Influence of Pressure on the Hydrogen Storage Capabilities of Two-Dimensional 468 Biphenylene Sheet, a First Principle Study.
Should I share my screen?
Yes, sir.
Okay. So is it visible?
Yes, it is visible. You can start.
Okay. So hello everyone. The topic of my talk is influence of pressure on the hydrogen storage capabilities of two-dimensional 468 biphenylene sheet. So first of all, I will briefly discuss why hydrogen energy is important. So because of the continuous depletion of fossil fuel and sharp increase in the global population as well as environmental pollution, hydrogen is considered one of the most prominent alternative of fossil fuel because it is naturally abundant. It has the highest energy per unit weight as compared to any other fuel, and it is also environmental friendly as the product of hydrogen combustion do not harm the environment. But the challenge is how to store hydrogen in a safe, compact and efficient way so that it can be utilized for practical application. In this regard, hydrogen storage can be done in gas and liquid phases, but to store hydrogen in gas or liquid phase, high pressure tanks are required, which are very costly, which have safety and transportation issues. So solid state form of hydrogen storage is considered suitable for the practical requirement. And Department of Energy United States has issued some guideline for the solid state hydrogen storage. According to that guidelines, hydrogen storage should be more than 6.5 weight percentage of the substrate material, and the adsorption energy of the hydrogen should lie in between the minus 0.2 to 0.7 electron volt. And more specifically, for the reversible use of hydrogen, the adsorption energy should lie in between minus 0.2 to 0.4 electron volt. So there are different kind of structures like porous kind of geolite structure, metal alloys, metal hydride, and metal decorated carbon nanostructures which are used for hydrogen storage. Metal decorated carbon nanostructures are considered promising in this regard, but there are some experimental difficulties for doping or decoration of metal atom into the carbon nanostructure, as well as there are difficulties such as metal-metal clustering and oxygen interference when metal is doped or decorated on carbon nanostructures. So these difficulties can be removed by applying high pressure and do not, because in the presence of high pressure, we can achieve high hydrogen storage in the absence of metal atom as well. So we have studied hydrogen storage in biphenyline sheet at high pressure. This is experimentally synthesized material, and this has been synthesized very recently. So we have used density functional theory and WASP simulation package for the calculation. We have used PBA exchange correlation function along with the dispersion correction of Grimm's to incorporate van der Waals interaction between different layers, and we have considered 10 angstrom of vacuum space to avoid the periodic interaction. And we have used 2 cross 2 cross 1 supercell of biphenyline sheet for the calculation, and sufficient convergence limit for force and energy are taken. So this is in figure 1A. I have presented the 2 cross 2 cross 1 supercell of biphenyline sheet, and in figure 1B, I have presented a schematic of 2 cross 2 cross 1 supercell of biphenyline sheet with 6 hydrogen molecules. So 6, as this structure is planar, this can adsorb hydrogen by this structure. And if we calculate the gravimetric weight percentage for this configuration, the weight percentage comes to be 7.7%, which is more than the DOE requirement of 6.5%. Now we have studied the adsorption of hydrogen at different pressure, and we have applied biaxial pressure, and we have found that at ambient pressure, the average binding energy of these 6 hydrogen molecules are only minus 0.11, but which can be improved to minus 0.3 to 0.4 at around 8.5 gigapascal of pressure. So this binding energy 0.2 to 0.4 is very much suitable for the reversible application of hydrogen, stored hydrogen. So we can conclude that at around 8.5 gigapascal of pressure, we can achieve reversible hydrogen storage in this biphenyline sheet, and the gravimetric weight percentage is also more than the DOE requirement. So here I have presented the density of the state for the carbon 2p orbital as well as the hydrogen 1s orbital at ambient and at around 8.5 gigapascal of pressure. And from the density of the state, we have found that at around 8.5 gigapascal pressure, there are some depletion of state for carbon 2p orbital of biphenyline, and there are some enhancement in the states for the hydrogen 1s orbital attached on biphenyline sheet. So we can conclude that at around 8.5 gigapascal of pressure, there is a significant charge transfer from carbon 2p orbital of biphenyline to hydrogen 1s orbital, due to which hydrogen molecules are attached to this structure with strong bonding, and binding energy comes in suitable range. So thank you.
Thank you, sir. The next talk is by Mr. Supratik Mukherjee, University of Hyderabad, India. And the topic of his presentation is electronic structure and vibrational properties of barytes type scintillators, TLXO4, X being chlorine or bromine.
My slides are visible?
Yes. Please make it full screen and start.
Is it full screen now?
Yes.
Good evening, everyone present here. I am Supratik Mukherjee from Advanced Center for Research in High Energy Materials, University of Hyderabad. I am working under the supervision of Dr. G.S. Vaidyanathan. Today, my talk of the topic is barite type scintillators, thallus, perchlorate, and perbromate. So, coming on, what motivated us to study this topic? So, we know that AbO4 type compounds are always interesting due to their dynamical properties and wide range of applications in laser hosts, scintillators, etc. And in search of that, we saw that thallus perbromate, the structure was reported nicely, but for the thallus perchlorate, there was nothing such as reported. So, TLXO4, thallus perchlorate and perbromate was one such kind that lacked theoretical as well as experimental investigations. And single crystal structure of TLCl4 has been missing until now. There was no reported structure of TLCl4 and no properties were ever studied for TLBr4. So how we approach this problem? So we know that TLCl4 and TLBr4 are isostructural. Both crystallize in orthorhombic crystal system and have barite class symmetry, PNMS space group. So what we can do, we can replace the Cl positions by Br positions. We know the Br positions. Now we can put the TlCl positions in place of Br positions as both are isostructural. So we will try to optimize based on this TlClO4 positions, the Br positions. So in brief, so I know the TLBr4 positions, but I don't have TLClO4 positions. But there are some experiments on TLClO4 which have elastic constants and vibrational properties, but no experiments on TLBr4 yet. So our main focus was to optimize TLClO4 to get the accurate atomic positions of TLClO4, predicting the properties of TLBr4, which both were missing, and find suitable application for this class of materials, thallus, perchlorate, and perbromate. So how we succeeded with this problem? So these were the optimized TLClO4 positions. Taking the TLBr4 positions, we optimize the TLClO4 positions. And these TLClO4 positions, when we calculate the elastic constant with first principle calculations, our theoretical elastic constants matched very well with the experiments. And TLBr4 positions we have already, but no experiments are yet done for the elastic constants. Now coming on the TLClO4 IR spectra, there were some experiments on TLClO4 IR spectra, and our DFT calculations matched very well with these TLC4 experiments. So we can finally say that we found out the accurate TLClO4 atomic positions which were not reported in the literature. So coming to the electronic structure and the scintillating properties finally. So this is the band structure of TLClO4 and this is the density of states for TLClO4. So what we see is that TBMBJ band gap for TLClO4 was found to be 4.3 electron volt, whereas TLBr4 was 4.8 electron volt. So what we see is that similar and less dispersive nature of these bands of TLClO4 and TLBr4 in the top and bottom of the valence and conduction band of these compounds. This suggests that there will be electron mobility and hence a large charge transfer character for these compounds, which can essentially provide a good scintillating properties. We can see that TLClO4 is mixed ionic and covalent nature from the density of states. There are Cl and O can be seen as ionic covalent bonding, and TL is exchanged with ionic bonding with ClO4 group. So the conclusions of the studies can be said as like this. TLXO4 is a wide bandgap insulator and the refractive index is 1.55, which is similar to the glass and has a high atomic number, which ensures a very less leakage current and large stopping potential, which are desired for scintillator and detectors. The less dispersive and similar nature of the valence and conduction bands shows charge transfers character, which are typical for good scintillators. And finally, any divalent activators such as europium may be doped with this TLCxO4 to get a high performance scintillator. And lastly, simulating experiments in these compounds can give us potential applications for this thallus perchlorate and perbromate in this material science. So these are the references of TLBr4 and TLClO4. This work was recently published in JPCM where we said this as a possible scintillator for thallus perchlorate and bromide. And thanks for hearing. Thanks for listening. Thank you so much.
Thank you. The next presentation is by Ms. Bishnupriya Nayak from BRC Bombay, India. And the title of her talk is Structural Phase Transition in Calcium up to 50 gigapascal pressure employing DFT and quasi-harmonic approximation. You may start, ma'am. It's visible.
Okay. Now you start. Okay. राहुल ये वाला लेटेस्ट मुझे कुछ पता चलेगा कोई बात नहीं आप good evening. My presentation is on structural phase transition in calcium up to 50 GPa pressure employing density functional theory and quasi-harmonic approximation. Next. So actually all of us know that this alkaline earth metal plays a vital role in bone formation, nerve-to-nerve communication, and in synthesis of blood cells. Moreover, its compounds are widely used in food, pharmaceutical, and chemical industries. Experimentally, people have found the elemental solid goes from FCC to BCC at 19.5 GPa and BCC to simple cubic at 32 GPa. But theoretically, the phonon dispersion relation shows the simple cubic calcium is dynamically unstable, that is, imaginary phonon frequencies along the high symmetry direction. Now, question is on next slide, please. Then now the question is why this discrepancy occurs between theory and experiment. Does any other structure exist in 20 to 50 GPa at ambient condition, or is there any anemoric contribution at room temperature which stabilizes this simple cubic structure? So to resolve all these issues, we have calculated the phase transition in the pressure range 0 to 50 GPa using density functional theory and quasi-harmonic approximation. So at t equal to 0, we found the structural transition occurs from FCC to BCC at 8.01 GPa and BCC to BCT at 32.6 and BCC to simple cubic at 39.53 GPa. But which phase is stable, that is BCT or simple cubic? To understand that, actually, we have calculated the phonon dispersion relation. Next slide, please. Here, this figure is for the simple cubic phase. Here you can see at around 40 GPa, the frequency is negative. Whereas in case of BCT, this is for BCT phase, frequency, these are positive frequencies. So BCT phase is stable, not the simple cubic phase. Then we added the temperature effect in phase transition by using quasi-harmonic approximation. Here you can see this is the phonon density of state. This we have calculated from the first principles. Next slide. So at T equal to 300 degree, we found the phase transition occurs from FCC to BCC at 8.36 GPa, which is slightly higher as compared to the pressure at T equal to 0 K. Then from BCC to BCT at 33.06 GPa and from BCC to simple cubic, that is at 40.01 GPa. And the table shows, this table shows that transition pressures increase with increase in the temperature. And here we conclude that the BCT phase is stable, not the simple cubic phase as reported earlier, even after adding the quasi-harmonic effect to the Gibbs free energy. Next slide. Thank you.
Stop. Thank you. Now we can conclude this session and we can We can thank the chairperson of the session. I request convener ICREACH2022 to please hand over a memento to the chairperson.
Hey, Avdesh. I thank Dr. Ananthashivan for chairing this session and managing the time very well. Thank you very much. On behalf of the organizing committee and Material Resources Society of India, Kalpakam chapter, we present a memento to Dr. Ananthashivan.
So with this, we have come to the end of session of ICREACH conference, and we'll be back tomorrow morning for the next session.